today we'll go to discuss about the introduction to computer networks. Right, so here in today's session we'll see all the basics of these computer networks. So what we have to know about these computer networks and what we are going to learn in these computer networks in the further sessions. Right. So before going to that, we'll go with the definition of a network. So a network is a connection of several computers. A connection of several computers, right? So this is called a network. Now, what is the purpose of connecting the several computers? So the main purpose of this network is to share the resources. Share the resources. Sharing the resources means sharing the files, or some documents from one computer to another computer. Similarly, sharing the printer, sharing the server, etc. All these, to share all these things, will connect several computers, which is called as a network. So in order to connect these computers, we require some medium, transmission medium. That means in order to share the files, or in order to share the printer, or in order to share the server, we are supposed to connect these computers with the help of some transmission medium. Right? Now, there are different types of networks available. Types of networks. So one is LAN, which is a local area network. WAN, it's a wide area network. MAN, metropolitan area network. And based upon the architecture, there are several types of networks. One is peer-to-peer network and client-server network. Apart from this, we will also learn OSI layered architecture and TCP IP layered architecture. All these things we will learn in the further sessions. Next, devices. So we will use a number of devices in these computer networks while going with the further sessions. Those are modem, router, bridge, switch, etc. All these things we will learn in the further sessions, right? Next, based upon the medium, that means how we can share the files from one computer to another computer. Here we'll use coaxial cable, twisted pair cable, or a wireless cable. Wireless networks, right? So all these things, with the help of all these things, we can connect several computers and we can share the resources from the one computer to another computer. Next, protocols. So in order to share some files from one system to another system, we have to follow some protocols. So here mainly we will follow the TCP IP protocol as well as UDP protocol. So connectionless protocols and connection oriented protocols. So before transmitting, or that means, or before sending the files from one computer to another computer, we are supposed to use any one among these two protocols, TCP IP protocol or a UDP protocol. Then topology. So this network follows a different topologies. So there are star topology, bus topology, ring topology. So don't worry about these things. So this is just an overview of our further sessions. So we are supposed to learn all these things in these computer networks. Right. Topology, there are three topologies: star, bus, and ring topologies. And based upon the technology, will learn internet, which is a familiar word. We know, everyone knows about this. Next, intranet, extranet. So this is based upon the technology we can divide this computer. So we will able to learn all these things. So LAN based upon the types, there are three things: LAN, WAN, MAN. Architecture, peer-to-peer, client server, OSI layer, TCP layer. Devices, a modem, router, bridge, switch. Coaxial cable, twisted pair wireless in the transmission medium, and the protocols TCP IP and UDP based upon the topology, star, bus, and ring. Technology, internet, intranet, and extranet. Right? So these things we are supposed to learn in the further sessions. So we'll start our sessions from the next session, right? We'll start with the types of networks. That means LAN, WAN, and MAN. So in the previous session we have seen what is the definition of a network. So definition of a network is a collection of or a connection of several computers is called a network. So here majorly there are three types of networks. One is local area network, which is known as LAN, metropolitan network, which is called as MAN, wide area network, which is WAN. So these are the different types of networks. So different ways we can connect the computers. Now we'll see one by one. So the main difference between all these three is the range. A difference in range. Right? So let us see one by one. First we'll go with the local area networks. So local area network means the name itself indicates that computers will be connected in a specified range. So connection of computers in limited range in terms of in a building or within the college or within the bank, etc. So this is called the local area networks, right? Then the main purpose of this LAN is sharing the resources. See, sharing the resources means the first one, we can use the printer. We can have only one printer which can be shared among all the computers in the specified building or within the college or within the bank. So we can share the common printer. Similarly, some software application. So an application can be installed in one system and that can be shared among different computers in a local area network. And the third one is data. So this is common. So we can also share the data among all the users in a local area network. And it will be having high security because there will be a limited number of computers and the range will also be within the limited range. So we can achieve the high security, but lack of privacy. So there will be no privacy. So once a data is used in the system, that data can be accessed by all the users of a local area network. So data can be accessed by unauthorized users. Unauthorized users means all the users which are available in the local area network. So that is main drawback of this local area networks. Right? So hope you understood this one. So main purpose is within that limited range. This will be established within the limited range. Right? So within the building or a college or a bank. Now we'll go with the second type of network, that is metropolitan area network. See, This is commonly known as MAN, Metropolitan Area Network. So it is a connection of different LANs. So we know that LAN is a local area network, and connecting different LANs is called as this metropolitan area network. So that means it can be connected within the city. Within the city, right? So an example. So example means connecting all the branches in a city. So if you take any bank, okay, any bank, so connecting all the branches in a city will be considered as a metropolitan area network. So the main purpose of this connection is sharing of data. Sharing of data. So the data will be centralized so that any branch can access the data. Right? So this is one best example for this one. So again, it is also having the less security because multiple users will be accessing this one. So it will be having less security. And these LANs will be connected with the help of fiber cables, fiber optics, or cables. So with the help of these transmission media, the data can be shared from one branch in a city to another branch in a city. So communication between different branches in a same city or a town. So that is one example for metropolitan area network. And the main drawback of this one is requires more cables. More cable, because the transmission media is more. The transmission media is cable or fiber optics. So requires a more cable if number of branches are increased in a city. So in order to connect all those things, we require more cable or a fiber optics. So this is all about metropolitan area network, that is MAN. Now we'll move on with the next one, that is wide area network. We all know this wide area network. Wide area network. So that means the range will be high. Now the connection of computers within, in between different cities. Okay, here the connection will be among different cities or states. And here the transmission media is, here the transmission medium will be satellite or telephone cable. And the main purpose of this wide area network is also sharing of data. And it is a connection of MANs, metropolitan area networks. So here with the help of routers, the data is shared. Data sharing will be done with the help of this telephone cable or a satellite using routers. Right? Here also we'll be having less security. Need to have firewall. Need to have a firewall in order to restrict the unauthorized access to this one. And best example for this wide area network is internet. It's a World Wide Web. Internet is the best example for this wide area network. So by using the internet, we can share the data from one computer to another computer, which is available in different states or different cities or different countries. So the data will be transferred in a speed. Okay, so the transmission media will be either satellite or a telephone cables. Right? So with the help of routers, the data will be sent to the destination. Right? So this is all about the wide area network. So I hope you understood these different types of networks. We have seen the local area network, metropolitan area network, and a wide area network. The difference among all these three is range. Local area network means within the building or within the office. So metropolitan area network means within the city, connecting all the different branches. So next, within the wide area network is among different cities, right? So here the maintenance will be expensive in a wide area network, and comparatively in the local area network the maintenance will be very less because all the computers will be within the single building. So easily we can find out the errors. So the maintenance will be very less and the data transfer will be very high in local area network. Right, topologies. So before going to this one, first we will know about this topology. What is meant by this topology? So topology means arranging computers in a network. So we have seen that a network is connecting several computers in order to share the resources or in order to transfer the data from one system to another system. Right. So topology means how many ways we can arrange these computers in a network. So there are different types of topologies. So first one is bus topology. Second one is star topology. Third one is ring topology. Next one is mesh topology. And the last one is hybrid topology. So these are the different types of network topologies. So the difference among all these things is arrangement of the computers. Arrangement of computers. That means the common thing is in all these topologies we will connect the computers in the network. So in all these topologies the data is transferred from one computer to another computer. That means the data sharing is available as well as the resource sharing will also be available. The only difference is arrangement of computers. So how the computers are being arranged in each topology. Now let us see one by one. First, consider this bus topology. We'll go with the bus topology. So in this bus topology, so there will be a communication cable. So this is a communication cable. Right? So all the computers will be connected only through this cable. See. PC1. So personal computer. Let us take it. Okay. PC2, PC3, PC4. Right? So here, a small example, we have connected 4 systems to a single cable. So this is called the bus topology. This bus is nothing but a line or a cable where the data can be transferred from one system to another system. Right? So here, if PC4 wants to communicate with PC2, the data will be moved in this way. Okay. So the data will be received here, the data will be received here, right? And also the data will be received here. But based upon the address, only the destination computer will be responding to that particular message. For example, if PC4 wants to communicate with PC2, so PC4 sends the data or a message through this cable. So the same message will be received for PC3. And also the same message will be received for this PC1 and the same message will be received for this PC2. But PC3 will reject this message, PC1 will reject this message, but PC2 will accept this message, will approve this message. Right? Because in that message there will be an address of PC2. Okay, so this PC2 will respond for that message. So similarly, if PC1 wants to send a message to PC4, the message will be sent through this single cable. So hope you understood. So through this single cable, the messages will be transferring. So here the main drawback is collisions. There might be a chance of having a data collisions. So if PC1 is sending a message here, similarly PC4 is sending a message here, there is a chance of getting collision and this network will be collapsed. And also if you add more number of computers, signal strength will be low. Automatically the signal strength will be decreased. Okay, so this is one more drawback. So these are all the drawbacks. And also no security, because every system is receiving the message. Every system is receiving the message, that there will be no security for the data transfer. Now the advantages, there are a few advantages over this bus topology. That is, we are using only one cable, so it's very less expensive to install. Less expensive, the cost will be less, and installation is easy. Right? So we can add more number of computers in a simple way. Okay, reconfigure, ease of reconfigure. So all these things can be done in this bus topology. So these are some advantages, but there are many drawbacks, because the collision, main drawback is a collision, and also if this cable, if cable fails, the complete network will be collapsed. So the complete network will fail, because all the computers are connected to only one cable. So if that cable fails, automatically the complete network will be failed. So this is the main drawback of this bus topology, right? So this cable we call it as a bus, right? Now we'll move on to the next one. Second topology, star topology. Star topology. So here there will be one centralized device, and all the computers will be connected to this centralized device. So see, right, so this is star topology. So all the computers will be connected in a single point to this centralized device, and this centralized device can be either hub or a switch. So I will tell you the difference between this hub and switch. Right. So if the centralized device is hub, then the message transmission will be in a broadcast. Broadcast means if PC1 sends the message to PC3, the same message will be transferred to all the computers that are connected in this network. So first that message will be routed to this hub, and through this hub it will transfer the same message to all the computers which are connected to this network. Right? So that is a broadcast. So complete transferring to all the computers which are connected in the network. Right? So this is one thing. And if the centralized device is a switch, then first the message will be routed to the centralized device, so that based upon the address available in that message, that message will be transferred to the destination address. Right? So see, if PC1 wants to send a message to PC3, right? So in hub, if hub is used, right? So message will be routed to hub, and through the hub, the message will be routed to every system which are connected to the computer. Right? So this is one thing. And if the centralized device is switch, then first PC1, the message will be transferred to switch, and from the switch, the message will be transferred to directly PC3. So a message will be sent from here to here and here to here. So no other system will be receiving this message. So this is the main advantage of using switch, right? So multi-way connection is also available. So so in between the PC4 can communicate with PC2 also. Multi-communication is also available. It is also possible in this star topology. So here the transmission we call it as unicast. Unicast means sending the message to only one computer based upon the destination address, right? So broadcast and unicast. Now advantages. So if we are using switch, there will be somewhat security. If it is a switch, okay, if the centralized device is a switch, and less expensive because we are connecting less number of cables. And drawbacks of this one is if the centralized device fails, automatically network fails, because any computer the computers cannot share the message from one to another, right? If this centralized device fails, either hub or switch, there's a main drawback. Okay, so this is all about our star topology. So based upon the address available in that message is routed from the centralized device to the destination computer, right? So we'll go with the next topology. See, the next topology is ring topology. Ring topology. So in this ring topology, the systems are connected with the adjacent computers. So see, so we can call it as a PC1, PC2, PC3 or nodes. Simply in a network, any computer will be considered as a node, right? So we can consider as node 1, node 2, node 3, node 4 or PC, personal computer 1, 2, 3, 4, right? So here, so this is a ring topology, so that every computer will be connected to its adjacent computers. That means it will be having a connection with two computers, one on the right side, another one on left side. See, if you consider PC1, it is connected with PC2 and PC4 because these two are the adjacent to PC1. If you consider this PC2, it is connected with PC1 and PC3, two adjacents. If you consider PC3, PC4 and PC2, so these two are the adjacents. If you consider PC4, PC1 and PC3, these two are the adjacent of this one. So every computer will be connected to its adjacent nodes or adjacent computers, right? So here the data will be transferred in only unidirectional in a circular fashion. So data is transferred in a unidirectional and in circular fashion. So if PC1 wants to send the message to PC4, it's a unidirectional. The message will be sent in this way, in this way, in this way, and finally it reaches to its destination. Right? So only unidirectional, in only one direction. Right? See, this is the direction of the transmission data. So if PC2 wants to send the message to PC3, again the same thing, in this directional, in this directional. And if PC4 wants to send a message to PC3, again, only in one direction, right? In this way, the data will be sent. So here, no collisions, because the data will be transmitted in only one direction, so there will be no collision, right? So if the data is transferred in unidirectional, then we call it as a collision, right? If one message is coming from left side and one message is coming from right side, so both will be collided. So this is called a collision, and here there is no chance of getting collision because the data will be transferred in only one direction, that is unidirectional. Right? No collisions will be occurred here. And also the main drawback for this one is expensive. So using of more cables, and also difficult to reconfigure. That means if you want to add a more number of systems, so we have to disconnect this one and we have to connect two adjacent nodes again. So that means somewhat difficult to reconfigure or expensive to reconfigure. And if any system fails, transmission fails. If any system fails, automatically the transmission will also get failed because data is transmitting only with only one direction. And again, easy to fault tolerance. Fault tolerance. Fault tolerance means identifying the fault. So if one system gets disconnected, so it is easy to identify where the fault occurs because compulsory the adjacent nodes will get disconnected because only two nodes will be connecting to each and every computer. So that's why it's very easy to find out the fault where actually the transmission has been discontinued, right? So, and also here less security because the data will be passed through all the systems, right? So that's why the less security here. Okay, so this is all about the ring topology because the data transmission is in the form of ring. Okay, unidirectional, right? So this is all about our ring topology. Next we'll move with another topology called mesh topology. Mesh topology. So here the mesh topology means every system is connected to all the other systems. See, for example, we'll consider 4 systems as we have considered in the ring topology. See, so there will be connection to all the 3 systems, and similarly, see, this is also bidirectional. This is a bidirectional. Bidirectional means data can be sent from one computer to, this computer to this computer, and as well as this computer to this computer. So, right. So you can observe here PC1, PC2, PC3, PC4. See, PC1 is connected with PC4, PC2, PC3. So 3 nodes, connection of 3 nodes. If you consider PC2, it is connected with PC1, PC4 and PC3. If you consider PC3, it is connected with PC4, PC2 and PC1. And if you consider PC4, it is connected to PC1, 2 and 3. So each and every node is connected with all the remaining nodes. That means if there are n nodes in a network, so links for each node will be n minus 1. And total links will be n into n minus 1. So you can observe here. So here there are 4 nodes. Sorry, okay. It's a bidirectional. Okay, if it's a bidirectional. N is equal to 4. That means 4 nodes. 1, 2, 3, 4. Next, links for each node. Links for each node will be n minus 1. That means 3. That means one node is connected to all the remaining. So see, if you consider this one, how many links are there? 1, 2, 3. So 3 nodes. Now total links. Total links. If it is a unidirectional, if it is a bidirectional, the links are n into n minus 1 by 2. That means 4 into 4 minus 1 divided by 2. That means 12 by 2, which is nothing but 6. You can count here 1, 2, 3, 4, 5 and 6. Total 6 links are available. And so this is a bidirectional. If it is a unidirectional, total links will be n into n minus 1. That means, see, sending, receiving, sending, receiving, sending, receiving, sending, receiving, sending and receiving. So you can observe, if it is a unidirectional, so these are the nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11 and 12. So total 12. So here you can observe 4 into 4 minus 1, which is nothing but 12. So if it is a unidirectional, the total links are 12. If it is a bidirectional, the links are n into n minus 1 divided by 2. That means 6 links. So here also it's expensive because lots of cable will be available, and difficult to reconfigure. So adding and deletion of systems is difficult, and if any system fails, transmission will not fail. If any one system fails, the transmission will not fail. It will move with the alternate path. Okay. So if PC1 wants to communicate with PC3, if the data is sending from in this way, if PC2 fails, automatically that will be moving in this way. So there are some alternates because every system is connected with all the remaining systems. So that's why if system fails, the transmission will not get affected in this mesh topology. Right? So hope you understood this topologies. And there is one more thing, that is a hybrid topology. Hybrid topology. So hybrid topology is nothing but a connection of two or more topologies. So connection of multiple topologies is called a hybrid topology. For example, if you consider the mesh, the bus topology, see, if you consider this one, so this is called a bus topology, this is a star topology, this is a ring topology. So this connection of multiple topologies, we call it as a hybrid topology. It's also very expensive because a lot of cable will be required, and also it is also difficult to configure because of adding more number of systems, right? So this is called a hybrid topologies, right? So hope you understood, guys. So mainly the topology means arranging the computers in a network. So how many ways we can arrange these computers in a network to connect a network to whatever the topology we are using, the main thing is the data can be shared from one system to another system, and also the resources can be shared among all the systems in a network. So these are the major network devices which are going to use in the networking. So we are frequently using these devices, right? So in that, the first one is repeater. So this repeater is used to regenerate the signal. So the signal will be sending from one system to another system in the network. So after some time, the signal will be becoming weak, or the signal may be corrupted. So in order to avoid those things, so every time the signal will be regenerated. A bit by bit regeneration will be done by using this repeater. Okay, so regenerating the signal to maintain signal strength in order to avoid the corruption of the signal, right? So before becoming the signal weak or corrupted, the signal will be regenerated. So that will be done with the help of this repeater. And the next one is hub. So hub will be used to send the data packets to all the connected devices. So different devices will be connected to a central unit that is called hub, and whatever the data received in this hub, that will transfer the packets to all the connected devices. Okay, so used to transmit data packets to all connected devices. So it doesn't have any filtering option. So it doesn't verify anything. Just it will send the data packets which have been received by this hub to all the connected devices. Right? There is no routing, there is no path, or there is no any other filtering options here. Right? So this is hub. And the next one is bridge. This bridge is mainly used to interconnect two different LANs in the same protocol, working on a same protocol. So interconnecting two LANs working on same protocol. Okay, same protocol, and this will be used in data link layer, and this is in physical layer. This repeater will be operated in physical layer, right? So a bridge, the name itself indicates, so that will be acting as an intermediate between two different networks which are operated in the same protocol, on same protocol, so working on same protocol. And the next one, switch. So switch is similar to our repeater with some additional functionality. So what is that additional functionality? So switch will send only the correct and good data packets to the ports, and whatever the error, if the packets contain some error, automatically those packets will be ignored by the switch. So error checking will be done here. Okay, switch, so error checking will be done. Error checking. So what kind of error checking? So good data packets can send to correct port, right? And data packets with errors will not be forwarded. So those packets will be ignored, will not be forwarded, right? So those packets will be ignored there itself. And the next one, router. So router will collect the data and it will send to the different ports based upon the IP address. So based upon the IP address, the data will be sent to the destination, right? So by using the different routing algorithms. So all the routing algorithms will be here and the routing will be done here, and the best routing path, it will select the best routing path, and through that routing path the data packets will be sent to the destination. So that will be done by the router. Okay, so packets will be routed to destinations in best routing path, and here dynamically routing will be decided. Okay, dynamically the routing will be changed from one packet to another packet. So it will select the best path, and through that best path the routing will be done in this router, and this will be operated in network layer. This will be operated in network layer, right? So this will be in the physical layer, this will be in the data link layer, and this will be in the network layer, right? So repeater, hub, bridge, switch, and router. Now the next one is gateway. So the name itself indicates gateway. It passes the data from one from one network to another network, which are handling in the different protocols, which are using the different protocols or a different network models, right? So here passing data to the networks of different networking models. So we are having different networking models, just like our OSI model and TCP model, right? So here the passing of data, that means the interconnection between the two different models, network models. So first it will get the data, and that will be interpreted, and that will be sent to the destination, right? So that is the usage of this gateway. So these are the basic network devices we will use in the networking. So repeaters, hub, bridge, switch, and router, right? So repeater is simply, it will regenerate the signal and hub will simply transmit the data packets to all the ports or all the connected devices. And coming to the bridge, based upon the MAC address, so it will connect, I mean the data will be processed, and it's nothing but an interconnection between two different LANs working in the same protocol, right? And coming to the switch, here the error checking will be done, and whatever the packets which are having the errors will be ignored here itself, and only the good data packet, that means without any error, the data packets will be transferred to the destination port to the correct way. And coming to the router, the packets will be routed to the destination, source to destination in the best routing path, and here there will be a dynamic routing based upon the different routing algorithms. So this is working on network layer, right, in the network layer. And finally the gateway, which is used to interconnect two different network models. Okay, so if you want to pass the data from one network model to another network model, then we'll go with the gateway. So this is also called as protocol converter. This is also called as protocol converter, because two different protocols will be used, and we are communicating the data between two different protocols, right? Protocol converter. Right? So hope you understood this one. So these are the basic network devices so used in the networking. So OSI layers means, OSI means Open System Interconnect, which was developed by ISO, that is International Standard Organization. So this was created a 7-layer architecture. 7-layer architecture which is used to transmit data from one system to another. Right? So all these layers collaboratively works for transmission of data from one system to another system. So this is the main advantage of connecting the systems in a network. So in the earlier sessions, we have seen that the main purpose of creating a network is resource sharing and the data sharing. So that means the data can be transferred from one system to another system, and that process will be done with the help of this 7-layer architecture. So in this session, we will see what are the these 7-layer architecture, and in the next session, we'll go with one by one. All right. Now we'll see the 7-layer architecture. So first one is the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and finally the application layer. See, these are the 7-layer architecture which was developed by ISO. Right. So here each and every layer is having its own functionality. So for transmitting a data from one system to another system, the data should be covered in all these 7 layers. See, first, so just I will give you a brief idea about all these layers, and from the next session we will go with one layer in each session. Right. Coming to the physical layer, it gives a physical medium to transfer bits. That means here the data will be in a form of bits. Right. So this is in the physical layer, the bits will be transferred, and in the data link layer, those bits will be changed to frames. So here, error-free frames will be transferred or transmitted. Right? So here the error-free check will be done in this data link layer. So some cyclic redundancy check and everything handling code. So those things will be done. Error-free techniques will be applied for the bits, and then those will be converted as a frames, and these frames will be transmitted from one system to another system. And coming to this network layer, these frames will be again converted into packets. So packets will be moved from source to destination. So in the network layer, the packets will be created and these packets will be moved from source to destination, right? So see, that means a routing will be done here. The packets will be routed from source to destination. So here the data will be in terms of packets. Now transport layer. So here, using protocols, reliable messages will be transferred. So with the help of protocols, these packets will be transferred, right? Reliable messages will be transferred. And in the session layer, the name itself indicates a session means some time period, we call it as a session. So here, establishing and terminating of sessions will be created in order to communicate from one system to another system. Some connection will be established. So establishing or termination of sessions will be created in this session layer. And here, see, before sending the data, the data will be encoded, either compressed, or we can use some security applications like encryptions and decryptions. So all these things will be applied in this presentation layer. So here the data compression, encoding or encryption. So the data compressions, so before sending the messages or before receiving the messages, the data can be compressed or can be encoded or can be encrypted for security purposes and for achieving the authentication and all these things. So the data will be, some techniques will be applied on the data, so that will be the compression, encoding or encryption. Similarly, while receiving the data, that will be decompressed or decoded or decrypted. So all these things will be done in this presentation layer. In the application layer, various services will be provided directly to the user. Various services will be provided directly to the users. So this is all about our 7-layer architecture, that is OSI Layers, which was developed by ISO in 1984. So while transmitting the data from one system to another system, that can be done with the help of all these 7 layers. So physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and application layer. So first the complete data will be in terms of bits, that means either zeros or ones. So that will be done in this physical layer. And coming to this data link layer, by adding some headers and tail, the bits will be converted as a frames, and some error-free techniques will be applied here, so that there is no error while transmitting the messages or receiving the messages. So that will be done in this data link layer, and those frames will be transmitted from source to destination. And coming to the network layer, again the frames will be converted into packets, and these packets will be routed from source to destination systems. And coming to the transport layer, so in the network, if the data want to be transmitted, that should be done through the protocol. So usage of all these protocols will be done here, and by using this protocol, the reliable messages will be transferred from one system to another system. And coming to the session layer, here, so before sending the messages, the connection should be established, and after sending the messages, the connection should be disconnected. So all these connection establishments and terminations, everything will be done in this session layer. Right? So presentation layer, so before sending or before receiving, some sort of things to be applied on the data. So that is the data compressions or encodings or encryptions will be done. So similarly, data decompressions and decoding and decryption. So if the data is compressed at the receiver side, the data should be decompressed before receiving the message. And similarly, if the data is encoded at the sender side, so the data should be decoded at the receiver side. Similarly, if data is encrypted at the sender side, the data should be decrypted before receiving the messages. So all these things will be done in the presentation layer. And coming to the application layer, so services will be directly provided to the user. Right? So this is all about the OSI layers, a 7-layer architecture. See among the 7 layers, this physical layer is a lower layer. Right? So that's why this is also called lower layer or hardware layer. Hardware layer. So what actually happens in this physical layer? So this physical layer is responsible for establishing, maintaining and deactivating the connection between two nodes. So this layer is responsible for physical connection. Physical connection between two devices. Right? That means this is responsible for establishment, the connection establishment, and maintenance, also deactivation. So establishing the connection, similarly the maintenance of this connection, and also the deactivation. Once the completion of this data transfer, how to deactivate this connection, everything is responsible by this physical layer. And here the information will be in the form of bits. So information will be in form of bits. So the data transmission will be in form of zeros and ones. So here the transmission of a signal converts to zeros and ones, which are nothing but our bits. Right? So this is about this physical layer, and this physical layer is also responsible for some functions. So we'll see those functions. Right? So it is mainly for connection between the two devices. That means establishment, similarly maintenance and deactivation. Right? So here the information will be in the form of bits. So a bits must be transferred from one device to another in this physical layer. Now we'll see the functionalities of this physical layer. So functions of this physical layer. The first one is bit synchronization. Bit synchronization. So this is completely responsible for this synchronization of bits. That means at a time only one bit should be transferred from one system to another system. So no overlapping of these bits should be done during the transmission. So that completely depends upon this physical layer. Right? So this is achieved by providing a clock. By providing a clock, the synchronization can be done will be achieved between bits. Right? So between bits means the sender and receiver bits. Okay, the sender can send the message and receiver will receive that message. So receiver also can send the message. So in that case, the synchronization should be there in this transmitted bits, and that synchronization is provided by using this clock. And the complete responsibility of this bit synchronization is on physical layer. Now, the second one is bit rate control. This is one more functionality provided by this physical layer. Bit rate control means it defines, so this physical layer defines how many bits to be transmitted per second. Right? So here bit rate, that means it defines number of bits transmitted per second. So this will be defined by this physical layer. So how many bits should be transferred per second. Next, the third functionality, it also gives the physical topology. Regarding the physical topology. So we have studied in the previous session that topology means arranging the networks, that means nodes in a network, right? So arranging the computers in a network. So we can arrange these computers in a network in different ways. So we have seen the bus topology, star, mesh, right? So ring topology, all these things. So this physical layer is responsible to know which type of arrangement is done between the devices. So it defines, or it is responsible to know the arrangement of devices in a network, either bus, ring, mesh, or star. Right? So this layer is responsible for getting the physical topology, to know about this physical topology. Right? So this is one more functionality. There's another functionality, that is transmission media or transmission mode. The fourth functionality, transmission mode. So in which mode the data can be transmitted from one device to another. In which mode data is transmitted. Right. So here in which mode? Mode here it deals with simplex, half duplex, full duplex. So the data can be transmitted in one among these three modes. One is simplex, half duplex, and a full duplex. We'll see one by one. Simplex. So in the simplex mode, the data can be transmitted only in a unidirectional. So there will be one system and there will be another system. So the direction will be only unidirectional. So if the system names are A, B, here A can send the message only to B. So B cannot send the message. B is only to receive the message from A, but B cannot send the message to A. So this is a simplex. This type of transmission is called a simplex. So this is a unidirectional. Sorry. Unidirectional. So example for this one is our monitors or keyboards. So example, monitors or keyboards. So the data can only receive to the monitors and send from the keyboard. So these are the example for simplex. So the data will be, the transmission mode is unidirectional. So one way the data can be sent, another way it cannot be sent. So one node is responsible for sending the data, another node is for receiving the data. So this is one type of mode, that is simplex. Now we'll go with the second one, that is half duplex. Half duplex. So here it is a bidirectional. So half duplex, A and a B. C. Sorry. It's a bidirectional. Bidirectional means A, the system A can send the message to B. Similarly, the system B can send the message to A, but at a time only one thing will happen. So if A sends the message or A sends the data to B, B should wait until it reaches the data from A. After receiving the data from A, then B can send the data from B to A. So the data can be transmitted in both ways, but not at a time, right? One after another. So data can't be transmitted at the same time. And here the data can be transmitted one after another. Right? So if A sends a message, B should wait until it receives the message. After receiving the message, B can send the data to A. So here the example for this one is walkie-talkie. Right? So security officers will use this walkie-talkie. So if one-way communication will be there. Once the person transferred his message, then only the other person will start communicating with this person. Right? So this walkie-talkie is the best example for this half duplex. So data can be transferred both ways, but not at the same time. So one after another. So this is called a half duplex. Now, the third one is full duplex. So you got an idea about this full duplex, I think. So this is also bidirectional data bidirectional data, but the data can be sent simultaneously. At the same time, the data can be sent. So this is also bidirectional, right? So here the data can be transmitted at the same time from both sender and receiver. Right. From the both sender and receiver, the data can be transmitted at the same time. This is called the full duplex. The best example for this is our telephone line. Right? So at a time, both the persons can communicate with each other. So A need not wait for the communication from B. A can speak. Similarly, B can speak at the same time. So that means the data can be transmitted from A to B and B to A at the same time. So this is called a full duplex. So this transmission mode, so which type of mode the data is transmitted is responsible for this physical layer, responsible by this physical layer to know about the transmission mode. So either the simplex, half duplex or a full duplex. Right? So hope you understood this physical layer. Let us stop here. So in the next session we'll go with the data link layer. So a physical layer is completely responsible to transmit the data in terms of bits. Right? So there are 4 functionalities of this physical layer. The first one is a bit synchronization, bitrate control, and topologies, identifying the topology, and finally is transmission mode. Okay, either simplex, half duplex, or the full duplex. And here the data will be in terms of bits. Right. So in the physical layer, we have seen that this physical layer is responsible to establish and deactivation of the physical connection between 2 devices, and also the data will be in form of bits, that means either zeros or ones. Now coming to this data link layer, here the data is represented in terms of frames. So the raw bits will be converted into frames. Data is represented in frames. Right? Next. And also this is responsible to transmit the error-free data from one device to another device. So it is responsible to transmit error-free data. Right? So it is also responsible for reliable and efficient communication between one device to another device. That means no corruption should be done on data. So also responsible reliable and efficient communication. So responsible to get this reliable and efficient communication, that means the data should not be corrupted, right? So in between the transmission. Now, so this is how the data link layer works and the responsibilities, and we will see the functions of this data link layer. The first function is framing. So the raw bits will be converted as a frames by adding a few more bits as a header and trailer. So these are the bits, and to these bits we'll add some header here and some trailer here. So this completely called as frame, and these frames will be transferred from one device to another device, right? So that means this is also responsible for data format in a network. Responsible to define a data format in a network. So that means this frame will be transmitted from one device to another device. So this is called a framing, and the bits, some header, that means this is also some sort of bits, right? So some bits will be added at the header side and also added at the trailer. So by adding this header and trailer to these bits, will give a frame, and these frames will be transferred from one system to another system. This is called a framing. So all this will be done in data link layer. Now, physical addressing. See, this is one more functionality of this data link layer. Physical addressing means, so here the destination address will be included in this frame as a header. So with the help of this header, the data will be transmitted to the destination address. So the destination hardware error, address, hardware address will be included as header. So in the previous function we have said that frame is defined by adding some bits at the front of the bits and at the end of the bits. So at the front of the bits we call it as a header, and in this header it consists of the destination hardware address. That means either source or destination, I mean sender or receiver. The destination address will be presented in a header. So based upon this address, the data will be transferred or transmitted to the destination. Right? So this is one more, and we'll see another. The third one, error control. So just now we have said that this data link layer is responsible to transmit the error-free data. So for this purpose, some sort of bits will be calculated, and those bits will be added to this frame before sending from the source. So that bits are called as cyclic redundancy code. Some techniques will be included in order to identify these errors. So those cyclic redundancy code will be added to the frame that is nothing but our trailer. So error control mechanism will be included. Will be calculated. Implemented and calculated bits, CRC, cyclic redundancy check. This will be added in trailer. Right? So header is having the destination address, trailer will be having the CRC, that means cyclic redundancy check, so that the receiver will once again check the data whether it is being corrupted or not. So if the data is corrupted after receiving, then immediately the receiver will send an acknowledgement to retransmit that corrupted data. So for that purpose, this CRC will be included. So if any error occurred, error or data corrupted, then the receiver sends acknowledgement to retransmit the corrupted data. So this retransmission of corrupted data will depends upon this calculated bits, that is a cyclic redundancy check. So by applying the cyclic redundancy check, some bits will be calculated and those bits will be included in the trailer. So immediately after receiving the data frame by the receiver, the receiver will check for the cyclic redundancy check, and if any error occur or any data corrupted, so immediately the receiver sends an acknowledgement to retransmit the corrupted data, so that again immediately the data will be retransmitted from sender to receiver. In such a way, this error control mechanism will be achieved. So all these things will be done in data link layer. So this is one more functionality of data link layer. Now one more thing, that is flow control. Flow control. So flow control means, the name itself indicates the control of data flow. That means either sender or a receiver sends the data, this bit rate should be in a constant. So constantly the data should be transmitted from sender to receiver as well as from receiver to sender. Right? So maintaining constant bit rate, so that if this bit rate is maintained constant, so that there is a less chance of getting the data corrupted. So it is, no chance of corrupting this data, right? So this is about the flow control. So this is also done in this data link layer. Now, see, data will not get corrupted if the bitrate is maintained constant, both the sender and receiver. And one more function is access control. Access control. So that means if more than one device is sharing the common channel, then these layer protocols are responsible to identify the correct device to get the connection. So if more than one device sharing same communication channel, then the DLL protocols, DLL means data link layer protocols, are responsible to identify device which have to get a control at the given time. So at a particular time, one device should be given control. So this data link layer protocols are responsible for getting the control over the device, right? So that is called access control. So no other device should get the control for the given time, right? So all these are the different functionalities of data link layer. So once again, I will write everything, the functionalities. So first one, it's a framing, so that the bits will be here, and after the header will be included and the trailer will be included. The header will be the hardware destination address, and the trailer will be the CRC, cyclic redundancy check. And next one is the physical addressing. The physical addressing means including this destination address as a header. Error control. Error control means some bits will be calculated and those bits will be added at the bits, and this will form a frame, data frame, and these frames will be transmitted from sender to receiver. Similarly, flow control. So to maintain the constant bit rate in order to avoid the corrupting, the data to get corrupted. And the last one is access control. So at a time only one should get the access, one device should get the access. So that control is also responsible by this data link layer. So all these are the functions of a data link layer. Right. So we have discussed in the previous session that in physical layer the data will be in form of bits, and in data link layer the bits will be again converted into, represented as a frame, and here the data is represented as a packets. Okay. The first point is the data is represented as a packets, right? So that's the main thing we have to remember. And one more thing is here the conversion of address will be done. The physical conversion of physical address to logical address will be done. So conversion of physical address to logical address, right? So here, so the address will be included in the packets, as well as some sort of bits will also be included as a header to these packets. So that particular bits will represent the route towards the destination. So we'll see that. Right. So two things. One is data is represented as a packets, and then it's a conversion of physical address to a logical address. Right. So the main functionality of this network layer is routing. So how the packets will be routed from source host to destination host. So routing the packets from source to destination. routing will be done by the network layer. So here two different networks, different networks will be connected with the help of routers. So with the help of routers, the packets will be transmitted from one network to another network. So that's why we call it as a routing. The main functionality of this network layer is a routing. So, and then one more thing is logical addressing. As I have said that the logical addressing. So see, frames will be having, and after that there will be some address of the source and destination. Address of source and destination will be added, and some sort of bits will be added here. Right? This is, we call it as a header. So here we have some bits, and this complete thing we call it as a packet. Right? So the destination address and the source address will be available in this packet. And apart from these source and destination address, there will be a header included to this, and it will form a packet. So what is the help of this header? So what is the use of this header? So by using this header, so as I have said that multiple networks will be connected with the help of a router. Right? So every router will maintain some forward table. So forward table is nothing but this forward table will be having some index as well as the output link from the router. So this table will be maintained by every router, So whenever the packet receives at the router, first it will check this header with this index values. So let it be some source 1, source 2, source 3. Let it be R1, R2. Right? So networks, different networks. So let us say it R2, R3. Okay. Now, first, whenever the packet reaches to the router, it will check this header, it will compare this header with these index values, and if this header contains the index value S1, so it will route the packet to the destination router, which is available in this output link, corresponding to the given input. So input link and output link. Simple to say, this is the input link and this is output link. So these index values will be added as a header to the packet. So based upon the index values, the packet will be routed to the corresponding output link. Right? So this will be happened in this network layer. So this is called a forwarding and routing. Then the next functionality is inter-networking. So just I have explained that a router will connect different networks and the packets will be routed through these routers to the destinations, right? So this layer will act as a logical connection. Between different routers or networks, different networks. So this network layer will act as the logical connection between the different networks, and through this logical connection, the packets will be transmitted to destination. Right? So this is one functionality, and one more functionality is fragmentation. Fragmentation means dividing. Right? Fragmentation means dividing. Now, what's the importance of this fragmentation? So we know that one network will be having different protocols, and the network will having a different bandwidths, right? So based upon the bandwidth, we can send the data, or we can send the packets to the destination. So that bandwidth and the protocols may change from one network to another network. So in such case, the avoidance of collisions and everything will be handled by this network layer, right? So in order to avoid the collision, see, if the packet size is more than the bandwidth, automatically some data will be lost, right? So in such case, we have to divide the packets into different parts based upon the bandwidth of the network. So that division we call it as a fragmentation. So during the routing, the packet from source to destination, based upon the bandwidth of the network, that packet will be divided into different packets, sub-packets. right? So that is the importance of this fragmentation. So in order to avoid the data loss, so if the bandwidth is less than the packet size, the data size, automatically the data will be lost. So in order to avoid such data loss, this fragmentation will be done. So based upon the bandwidth, the data will be, the packets will be divided, fragmented into different parts, and each part will be transmitted through this bandwidth. Right. So hope you understood this one. So these are the few services or the functionalities provided by the network layer. Now we'll see the functionalities or services. Services of this network layer. The main functionality is routing. It routes the packets from source to destination, and during the transmission, there might be a chance of getting the congestions, collisions, as well as the data loss. So all these things will be responsible by the network layer. Now we'll see the services. So earlier we have seen the functionalities, we'll see the services. The first one is guaranteed delivery. Guaranteed delivery. So this layer is responsible to deliver the packets perfectly without any loss. So guarantee, it gives the services that it guarantees the packets to be received at the destination site, right? So that is the responsible of this network layer. Next, in order packets. In order packets. So earlier I have said that the fragmentation, right? Fragmentation. See, let us think that this is a bandwidth and this is the size of a packet. This is the size of a packet. Okay, so we can't send the complete packet into this bandwidth, right? So some data will be lost. So such that it will be divided into small packets. See, now the packets can be moved through this bandwidth without any data loss. So that is fragmented. So this data is fragmented into different packets. Now here in order packets means, so whatever the order we are sending the packets at the sender side, the same order they will receive at the receiver side. For example, this is a packet number 1, 2, 3, 4, 5, 6, 7. Right? So every packet will be having some serial number. Okay, so at the receiver side again they have to combine all the packets to get the complete information, right? So in order to avoid the redundancy and all these things, some sort of serial number will be added to these fragmented packets, and these packets will be transmitted through this bandwidth. So in order packets means whatever the order we are sending at the sender side, the same order they will be received by the receiver side. So that is called the in order packets. Guaranteed maximum jitter. Maximum jitter. So guaranteed maximum jitter means, so the time between two successive transmissions, right? Time between two successive transmissions at the sender side will be equal to two receipts at the destination side. So this time difference and this time difference should be equal. Let it be, it takes some 5 seconds in between the transmission from one packet to another packet. The same time should be here also by receiving the packets from the bandwidth. Right? So the time difference should be seen at the receiver side and the sender side, source and destination. Right? Security service. And this security service is achieved by using the session key between the source and destination. So there will be some session key between source and destination. Right? That means whenever the data want to send by the source, that data will be get encrypted. The data will be encrypted and this will be sent to the destination. This encryption will be done with the help of session key. And at the receiver side, again, after receiving the same packet, the encrypted packet, so this is encrypted, and this will be decrypted to get the original data, right? So this will be done with the help of session key, and this is the responsible service of network layer. So security service, in order to provide the security for the package, so at the source it will be encrypted, at the source destination it will be decrypted with the help of session key. So by using this approach, it will achieve the integrity issues and authentication issues. Right? So for everything, the responsible is the network layer. Right? Hope understood the functionalities and services. So functionalities are the routing. The main functionality is routing the packets from source to destination, and logical addressing. So here everything will be in a logical address, and then the internetworking. So it is a logical connection between the source and destination, and the fragmentation. So based upon the bandwidth, the packets will be fragmented. Now, coming to the services, the guaranteed delivery. So it will provide a service that every packet is guaranteed delivered to the destination. And next, in order packets. So whatever the order we are sending at the sender side, same order it will be received by the receiver side. And the guaranteed maximum jitter, the time duration or the time amount between the two successive transmissions must be equal to time difference between two successive receiving the receiving the packets at the receiver side. And coming to the security services, so with the help of the session key, the encryption and decryption will be done at the both the sender and the receiver, from the source and destination. And with the help of this session key, it will achieve the integrities and authentication services. The transport layer. Okay, so in this transport layer, the data is represented in forms of a segment. So the first one is data is represented in segments, right? So, and the main function of this transport layer is to provide the communication between the applications on different hosts. So this layer provides the communication, the logical communication between the applications on different hosts. So that means applications on sender side and applications on receiver side. So there will be no physical connection between these applications, but there will be a logical communication. With this logical communication, the data, the message or the segments will be transmitted from source to destination. Right? That means this is responsible for delivering the end-to-end message. Responsible for end-to-end message delivery. So here message is nothing but our segments. Right? A number of segments will be there, and those segments will be transferred from source to destination. Right? And one more thing. After transmitting these segments from source to destination, this is responsible to provide the acknowledgement. It provides the acknowledgement for successful transmission of data. And if there is any error occurred during the transmission, this layer is responsible to retransmit the error data. That means, so if any error occurred, this layer is responsible to retransmit the data. That means the data here, the message, which is represented as segments in this layer. So these segments will be transmitted from source to destination, and if the delivery of the segments is successful, so this provides the acknowledgement. And if there is any error during the transmission, this layer is again responsible to retransmit the data. And one more thing here, the protocols, the transport layer protocols are implemented at end systems but not at routers. So that means here the protocols will not be implemented at the routers, but these protocols will be implemented at end systems, right? So here there are two major protocols for this transport layer facility. I mean layer TCP, the TCP and UDP. These are the two protocols which provides the services for this transport layer. So these two we call them as transport layer protocols, right? So we'll see the services provided by this transport layer. So first one is here the functionality, the responsibility of this one is delivery of messages from one system to another system, end systems, right? So there will be some logical connection will be there. So in between the applications of the different hosts. Here host is nothing but a system, right? Now services. So what are the different services provided by this transport layer security? The first one is, as we have discussed it just now, end-to-end delivery. So during the source, the system will be sending the segments, and at the receiver side, it will receive the segments from the source, right? So this will be done. This is one of the service provided by this transport layers. And the second one is reliable delivery. Reliable delivery. So reliable delivery means without any loss of information, without any error, without any interruptions, the data must be transmitted from source to destination. So that we call it as a reliable delivery. So if there is any error, some error control mechanism should be implemented, and we have to avoid that error, right? So it consists of error control. So whatever the errors we can't detect in the data link layer, those errors will be detected by this transport layer, right? So in between the transmission, the error control will be implemented. So the errors will be handled here by the transport layer, and will avoid the errors. Next, sequence control. Sequence control. So here the message is represented in terms of segments, right? So the message will be divided in number of segments, and each segment will be having one sequence number, because at the sender side we are sending number of segments, and at the receiver side they have to receive all the segments which are transmitted from the sender. So for that purpose, for reassembling the segments at the receiver side, one sequence number will be included for each and every segment, right? This sequence control mainly it provides the loss of data, the information about loss of data, right? And also reassembling, in order to reassembling, right? So for this purpose, we will use this sequence control. So if, for example, 5 segments are sending from sender to receiver, so 1, 2, 3, 4, and 5. This is the sender side, and in the receiver side, if we are receiving 1, 2, 3, 5, so we can observe based upon the sequence control, based upon the sequence numbers, we have received 1, 2, 4, and 5. So we are missing the sequence 3. That means there is a loss of data during the transmission, and so that's why this sequence control is used to detect the loss of data. And if the same data is received here in this way, 1, 2, 3, 4. So after receiving the data, here again they have to reassemble the data. So reassembling the data, the first packet must be here, second, third, fourth, and fifth. But actually, receiver have received the 5th packet first. That doesn't mean the segment 5 is a starting data, right? So for reassembling the data at the receiver side, we'll use these sequence numbers. So in this sequence control, the sequence numbers will be given. See, that is one thing. Next, similarly, loss control. Loss control. So just now I have said an example. If the segment 3 is not received at the receiver side, that implies some segment of data is missing. So automatically the receiver will request to the sender to retransmit the segment with the sequence number 3. That means it will avoid the loss control. It will avoid the data loss, right? So in order to avoid the data loss, it will request for retransmission of data, right? So that is one thing. Next, duplication control. Duplication control. So this duplication control means, again, so this sequence number is itself useful for controlling the duplicate packets, because we are arranging the sequence numbers for all the segments. So if any segment with the same sequence number is received more than once, automatically that implies the duplicate packets have been received. So automatically the duplicates will be discarded. So it also avoids the duplications of the segments, right? So this is by achieving all these things: error control, sequence control, loss control, and duplication control. So the reliable delivery will be achieved. So this is the one service provided by the transport layer. Next, so one thing is the flow control. See, all these things we have studied in data link layer: flow control and error control, right? So there we are that is depends upon the network, and this depends upon the end-to-end systems, related to the end-to-end systems, right? So flow control, if the receiver is having a overloaded, some packets will be discarded, right? So if there is no control on flow, the packets will be keep on sending by the sender, and the receiver is being overloaded of receiving the packets. Automatically some sort of packets will be discarded, right? So again, the receiver will request for retransmit those packets. So such a type of avoidance, this flow control will be. Flow control means a constant flow of data. So there must be no overloading on sender side, no overloading on the receiver side, right? The next last one, that is addressing. Addressing. So here addressing means for every segment there will be one header included, and that header will be having some port address. So segment will be having some header. So this header is nothing but port address. So each and every application will be having a unique port address. So if the sender sends the segment to the receiver, based upon this port address, the segment will be directly transmitted to that particular application, because here the communication between two end systems, right? So in the end system, the applications will be there. This transport layer is responsible for communicating between different application processes of different hosts, right? So this port address means that is related to the application, right? Process of application. So which process needs this segment, that depends upon this port address. So based upon the port address, this segment will be directly transmitted to the required application, right? This is the addressing. And two more services are provided by this transport layer, that is connection oriented, connectionless. Connection oriented and connectionless. So in the connection oriented service, the three things will be happen. One is connection establishment. So first the connection should be established, then data transfer. Once the connection is established, automatically the data will be transferred, and once the data transfer is completed, automatically connection termination. That means disconnection of this connection, disconnecting the connection, right? So in the connectionless, so one more advantage of this connection oriented is acknowledgement. So the acknowledgement will be given for every successful transmission of data. So that's why if there is any error, automatically the receiver can request to retransmit the data, right? So this is acknowledgement. This will be available only in connection oriented. So in the connectionless, there will be no connection establishments, so physical connections, and directly the data can be transferred. Right? And also no acknowledgement will be given. No acknowledgement. So when compared to these two things, connection oriented and connectionless, so connection oriented is more reliable to send the messages than the connectionless. So these are also the services of a transport layer. Right? So hope you understood this one, the services and some responsibilities. So main thing is transport layer is responsible to establish establish the logical connection between two application processes of different hosts, not the routers, not the network, two applications. Right? So here the data is represented in terms of segments, and for every segment there will be an header included for the transport layer header, and in that header we will include the port address. The port address represents the address of the application to which the data should be responsible. Right? So, and also apart from this header, there will be sequence number provided for every segment. This sequence number is used to achieve all these things for reliable delivery. That means error control, sequence control, loss control, and duplication control. For everything, the one answer is sequence number. The sequence number will be added to the segments. Right. So coming to the session layer, a session means some particular time period. So the main service of this session layer is to maintain a session, that means establishing a session, and the termination and maintenance of that session will cover in this session layer. So the first service or a function is session establishment, maintenance, and termination. So first one, establishment means connecting the two systems, and maintenance means during the transmission the session should not be expired or disconnected. So after completion of the data transfer, finally the termination of this session. So we have to disconnect the session. So that is the first service of this session layer. And the second one is synchronization. So in order to avoid the data loss, we will go with this synchronization. So synchronization means setting some checkpoints, and if any data is lost, we'll need not go with the first packet. So we can continue with the packets where we have get the error. So that means we have to create a checkpoints first. So for example, so this is for creating checkpoints, setting the checkpoints. So example, if the system wants to send some 100 pages of data from source to destination, and first we have to create a checkpoint. So here I am setting the checkpoint for every 20 pages. So that means, so after transmitting the 20 pages from the destination, we'll get the acknowledgement for those 20 pages. So that means if the source receives the acknowledgement, that implies the data is securely transmitted to the destination. So if there is an error in transmitting some 65th page, so we need not worry about 60 pages, because for every 20 pages we have created one checkpoint, and also we are receiving some acknowledgement from the destination. So first 20 pages, no error. Second 20 pages, no error. Third 20 pages, no error. That means up to 60 pages, there is no error. So there is an error in 65th page. So we have to check for, from 61st page, we can check for the data loss. So that means we need not go with the starting page itself. So for that purpose, we have to create a checkpoints, and we will achieve this synchronization. And the third one is dialog control. Dialog control. So dialog control means, so it serves, or it will provide two systems to be starting, either to start the communication either using half duplex or a full duplex. So it allows two systems to communicate or to start communicating either in half duplex or full duplex. So in the first session we have seen what is meant by this half duplex and full duplex. So half duplex means one-way communication. If source is communicating, the destination have to wait until the source completes its communication. And a full duplex means a two-way communication. So at a time, source can communicate with the destination, and destination can send the data to the source. So full duplex means a two-way communication. half duplex is a one-way communication, right? So this data control, this service also provided by this session layer. That means it allows two systems to start communicating either in half duplex or full duplex, right? And here the data is represented in data itself. So in the previous session, in the previous layer, that is a transport layer, the data is represented in terms of segments, but here the data is represented in a data format, right? So this is all about the session layer. So we'll go with this another layer, that is presentation layer. So the name itself indicates this implies how to present the data to the destination or the source. So that means it will change the format of the data in the presentation layer. So the first service or function of this presentation layer is translation. That means, so translation, the first service. So here the data format will be changed to another format. Example, ASCII data format can be changed to EBC DIC. So this is one more format, data format. So the one format will be changed to another format, and that will be transmitted to over the network. So that is all about the translation. And the second one is encryption and decryption. So this is also changing the format of data. So that means, so encryption, so sender will send the data. So the data will be encrypted so that the data will be changed into ciphertext. The data format will be changed. This is at sender side. Similarly, at the receiver side, the ciphertext will be decrypted and will get the plain text. So here the data is nothing but a plain text. Okay, so at the sender side, the plain text will be encrypted and the ciphertext will be output for this encryption, right? And in at the receiver side, receiver will receive this ciphertext, and this ciphertext will be again decrypted to get the plain text. So for all these encryption and decryption, one key will be used. A key will be used. So with the help of the key, this process will be working. So encryption and the decryption. So by doing this encryption and decryption, the data will be secure. Right? The data will be secure. And the third one is compression mechanism. So as we know that compression means reducing the data, complete data. So the size of the data will be reduced in this compression. So there are different compression algorithms will be there. So with the help of those compression algorithms, so we'll reduce the data, size of the data, and that will be transmitted over the network. Right? So it reduce the size of data. Right? So all these three are the main services of this presentation layer. So main service is to display in a required format. That means changing the data into the required format, and that will be transmitted over the network. Right? So this is all about the presentation layer. We'll go with the last layer, that is application layer. So application layer. So here the name itself indicates that is applications. There are different applications to be performed in the system. So here the example for these applications are the browsers, web browsers, messengers, and all these things will be coming into this application. So in the application layer, so this will serve as a, this application layer produces data, and that will be transmitted over a network. Right? So the data, whatever the data which is we want to send from the browser or the messenger, that will be transmitted over the network through all the 6 below layers. That means lower layers. This is the topmost layer. So lower layers, it will give services to the lower layers. So the main services of this one is file transfer, access and management, email services, right? So these are the services provided by this application layer. Similarly, file or directory services. That means the data actually transmitting from this layer. So this layer will provides the service to display the information in the required format. Right? So this is all about the application layer. So with the help of these applications, we'll send the data and we'll also receive the data. Right. So as we have discussed in the earlier sessions that OSI reference model will be having 7 layers. So we'll see 7 layers, and from the source and destination how the data will be transmitted from each and every layer. So the topmost layer in OSI reference model is the application layer. And then the next layer is the presentation layer. And the next one is the session layer. The transport layer. Network layer. Data link layer. Physical layer. So these are all the 7 layers in OSI reference model, and this is the source, and we have to draw for the destination also. We will draw the same layers in the destination also. So the topmost layer, application, presentation, session layer, transport layer, network layer, data link layer, physical layer. Right? So the actual data flow will start from the application layer and it ends with the application layer. So this is the source and this is the destination. So let us indicate it as a source, the source system and the destination system. Right. So here, as we have discussed in the earlier session, applications are directly communicated with the network. So that means the web browser or the messenger, with the help of those things, the data will be produced and the data will be transmitted through the network. So here the data will be represented in the form of the data itself. And here in the presentation layer, the translation will be done. That means the complete data format will be changed, as well as some security purpose, the data will be got encrypted and decrypted at the destination side. So here the data will be in form of encryption. So encrypted data. And in the session layer, the data will be transmitted using the synchronization points. So here we will create some checkpoints, and based upon the checkpoints, we'll reduce the error control. So in this session layer, the data will be synchronized data. That means data with checkpoints. Data with checkpoints. So some checkpoints will be created. Right. In the transport layer, the data will be in the form of segments. In the network layer, the data will be represented in packets. In data link layer, the data will be represented in frames. The physical layer, the data is represented in bits. Right? Similarly, here also, after receiving to the destination, the bits will be received here, and again in the data link layer it will be frames. In the network layer it will be the packets. In transport layer it will be the segments. In session layer, the data with the checkpoints, decrypted data, and the data, or a message. We can call it as a message. Okay. So here also we'll remove this one. We can call it as a message. Right. So the flow of control will be from the application layer to presentation layer, presentation layer to session layer to transport layer to network layer to data link layer to physical layer. So after getting from the physical layer, the bits will be transferred through the physical medium. So based upon the physical medium, the data will be converted, that means encoded in the physical layer, and this will be received to the destination section. So in the destination, the physical layer, it will be transferred to data link layer, to network layer, transport layer, session layer, presentation layer, and finally it will reach to the application. So simple example for this is, so if you send an email, that email will be sent from the system, so that email will be considered as a message. So that is nothing but application layer. So email services is in the application layer. So the data will be in form of message. So then the data again, it will send to the presentation layer where the message will be encrypted for getting the security. So no other, the data should not be modified during the transmission, and it should be received safely at the destination. For that purpose, we have to change the formats of the data. So that complete process will be done in presentation layer. So if this is a message, and this will be the encrypted format. The message will be encrypted in the presentation layer. So after this, in the session layer, some checkpoints will be created, and the same message will be given. And at the same time, see, so here again the message with the checkpoints. Okay, the message with the checkpoints. And after that, the segments. This message will be divided into different parts. So and for every segment there will be one sequence number, and along with this one, the port address will be added. Right, this port address will be added for each and every segment, and it will be transmitted to the destination. And here, coming to this network layer, so IP address will be added as a header to the given data. So here the IP address. So IP address is for both the sender and receiver. The sender IP address and receiver IP address will be attached here. So port address and data. Right? Then here in the data link layer, the MAC address will be added to the given data. So the MAC address will be created. Similarly, IP address will be there. Similarly, port address will be there, and finally the data will be added. And data will be in the encrypted format, right? And the complete information will be converted into bits, and these bits will be transmitted to the destination based upon the physical medium we are using, right? So the encoding will be done in this layer. So whatever the physical medium we are using, based upon that physical medium, the bits will be encoded, and that will be transmitted to the destination. At the destination, the same will be received, and it will based upon the bits. Okay, the same will be received here. The MAC, IP, port, as well as data. This will be received here, and based upon the MAC address, it will be sending here. So based upon the MAC address, the packet will be sent to the upper layer. So IP, port, and data. This is a MAC. Right? So in the network layer, based upon the IP address, it will be routed. Based upon the IP, the port, and data will be routed. So based upon the port, it will be sent to the, here, see, this is the port and this is the data, port address. So port address means application address. So each and every application will be having different processes. So the data will be sent to corresponding process. Okay. Then here, the data will be received here. So here it will check for the checkpoints. If there are any errors, automatically the error control will be done based upon the checkpoints. For every checkpoint, the acknowledgement will be sent to the source. And if there is any error, automatically that particular error, the packet where we got error, that will be transmitted, the segments, right? And here it is in an encrypted format. Data is in encrypted format. Here the decryption will be done. The data will be decrypted so that it can be understood by the destination. And finally, the message will be received by the application, the actual plain text. So this is how the data will be transmitted from the application layer to application layer in OSI reference model. So the data will be transmitted through all these 7 layers in both the source and destination hosts, right? So here the MAC address represents a network, the address given for a network, and the IP is given for a system, and port is given for a application, right? So hope you understood all these things. So 7 layers of OSI reference model. Right. So coming to this TCP IP model, so a small difference between this OSI and TCP IP. As I have said in the previous session, that OSI is a reference model and TCP is an implementation of OSI model. So first one, this is an implementation of OSI model. So some modifications will be done on the OSI model. So those here the TCP IP model will be having the 4 layers, where the OSI reference model is having around 7 layers. So these 4 layers are the application layer, transport layer, internet layer, host to network layer. So these are the 4 layers in TCP IP model. So let us see what is happening in each and every layer. The same thing, but in the application layer, we are combining the session and presentation. So combining these 2 layers in the OSI model in this application layer, and coming to this host one, we are combining a data link layer and the physical layer. We will combine both the data link layer and physical layer of OSI model into a single layer called host to network layer in TCP IP model. And this is as usual transport layer, and this is network layer. So this is the OSI layer and this is the TCP IP layer. Right? So this is the TCP IP and this is the OSI reference model. So implementation of this OSI model will get this TCP IP. Now we'll see one layer after another. So let us start with the lower layer, that is host to network layer. Host to network layer. So this is a combination of physical layer and the data link layer. So the first one is, this is used to a physical transmission of data. This layer is used or responsible for physical transmission of data, right? And it also defines a protocol to connect the host. This layer is responsible to define a protocol. Here the protocol means a set of rules. So there will be some set of rules to be followed while transmitting the data from source to destination. So that protocol definition should be done to connect the host. So it defines a protocol to connect host. And these protocols may be different from host to host or the network to network. Right? So these are the things happen in this host to network layer. And the next second layer, the above layer of this host to network layer is inter-network layer. or internet layer, right? So this is nothing but our network layer in OSI reference model, right? So here the functionalities are, the functions of this layer is packets delivery, so delivering the packets from source to destination, routing, so the packets will be routed from source to destination, so there we will use some more algorithms for routing, so that routing is one function of this layer, and similarly avoiding the congestion or congestion control. So congestion control. So in order to avoid these congestions, this layer is responsible. And also the main protocol. So in the TCP IP, the main thing is a protocol. So each and every layer will be having the protocols. So the main protocol of this layer, that means internet layer, is IP protocol. That means internet protocol, right? So this is used to transfer the packets from source to destination. So, and it is also responsible to transmit the packets independently. Responsible to transmit packets independently. So here this layer is responsible for transmitting the packets, right? So from source host to destination host. And again, here the packets may not be received in the same order that they have set. So the packets will be sent from the source to destination. So if the packets order from the source is 1, 2, 3 and 4, and in the destination it is not mandatory to receive the packets just as 1, 2, 3, 4. So the fourth packet may receive first, second packet may receive second, packet number 1 may receive third, packet number 3 may receive at the last. So packets may be received in the the packets may not be received in the order that they have sent. So whatever the order they are sending, the same order may not be received in the receiver side. So this is one more responsibility of this internet layer. So whatever the functionalities, whatever the responsibilities we have seen in OSI reference model of network layer, everything is applicable for this internet layer in TCP IP model. Right? Hope you understood. Next, we'll move on to the next protocol or next layer, that is transport layer. Transport layer. So here the transport layer, so same the functionalities and whatever the functionalities and responsibilities we have seen in the transport layer of OSI model, the same will be applicable here also. The main function of this transport layer is, this is responsible for segmenting, splitting of the data. So the data will be divided into different segments, right? So everything, splitting of data. So based upon the bandwidth, the data will be divided, right? So everything, that complete splitting of data is done in this transport layer. And it also decides to send the data either in single path or multiple path or a parallel path. That means source and destination. So it is an bidirectional. Source can send the data in this way, and using the same communication channel, the destination should send the data in this way. Or source and destination will be having two paths. So source can send the message in one direction from one communication channel, and destination can send the data through the another path. So it decides to send the data either in a single path or a multiple path. and this TCP IP model used to break the data into small units which are handled efficiently by this layer. So in order to handle efficiently, the data will be divided into small units, right? And also similarly, the header information will be added. The header information will also be added in this layer, and it is mainly responsible for transmitting error-free end-to-end delivery of segments, right? So transmitting the error-free messages, this transport layer will be implemented, right? So hope you understood about this transport layer. So one single thing, so whatever the responsibilities and functionalities which we have seen in the transport layer of OSI model, everything is applicable here, right? So next, the topmost layer in TCP IP is application layer. That means the combination of both the session and the presentation. So session and presentation will also be included, right? Here it will act as an interface between the host and the services provided by transport layer, right? And also it includes high level protocols. It also includes the high level protocols. So what are the high level protocols which are involved in the application layer? The first one is Telnet, which is a two-way communication. And similarly FTP, which is nothing but a file transfer protocol. Transmitting the data or file data from source to destination. Similarly SMTP, mail transfer protocol, which is used to transport electronic mail from source to destination. Similarly DNS is domain name service, which resolves IP address to textual information. So all these are the high level protocols which are included in this application layer, right? So hope you understood this protocols, these services of application layer. Now finally we will see the protocol stack of all these layers and we will wind up. See, let me give you the protocol stack for all the layers. So first, the topmost layer is the application layer, then transport layer, internet layer, host to network layer. So the protocols of applications are Telnet, FTP, SMTP, DNS, etc. In the transport layer, we'll use the two protocols, TCP, UDP. Internet, the main protocol which we are using is IP protocol. Host to host network, the data is Ethernet. Frame relay, token. So this is the protocol stack for all the layers. This is the protocol stack. The protocols involved in each and every layer of this TCP IP model. Okay, so hope you understood this TCP IP model. The only one difference over the OSI reference is that is a reference model, and this TCP IP is an implementation of that OSI model. So one more difference of this TCP and OSI are it will be having OSI is having 7 layers, whereas this TCP while implementing that OSI, this TCP IP reference model is having only 4 layers. So the session layer and presentation layer are combined into application layer. Similarly, the physical layer and data link layer are combined into the host to network layer. And one more difference is this TCP IP model supports only connectionless service, whereas OSI supports both the connectionless and connection oriented service. Right? So let us write the difference of this TCP IP and OSI reference model, and then we will stop this session. Right. So first one is it is a reference model, and here we have seen it is an implementation of OSI. So this will be having 7 layers, and this is having only 4 layers. And here the session, presentation layers are separately implemented. Here it combines both session and presentation layers. Here, so model is first and protocol is next. So model is designed before the protocol. So here protocol is implemented before the model. So protocol is first, model is next. So that's why this is protocol independent standard, and this is a protocol dependent standard. More importance to the protocols, right? So it supports connectionless and connection oriented architectures, but OSI, this TCP IP supports only connectionless, right? So these are the major differences over the OSI reference model and the TCP IP model. The main difference is it's a reference model, this is an implementation of OSI. See, the basic layer of OSI reference model is a physical layer. When we have seen that in physical layer, the bits will be transmitted from source to destination. That means the raw bits will be transmitted from source to destination through the transmission medium. So here, the transmission medium is used to transfer the bits from source to destination. So how many types of transmission mediums will be there? And we have to choose one among these transmission medium to transmit the bits from one system to another system. Right. So now we'll categorize this transmission medium. So this is categorized in 2 ways. One is guided, another one is unguided. Guided transmission medium and unguided transmission medium. Right? So the name itself indicates guide and unguided. So this is wired and that is wireless. This is wired medium. This is wireless medium. Okay, so coming to this guided, again it is classified into different categories. So one is twisted pair cable, coaxial cable, fiber optics. Right? So these are all the wide transmission medium, and this is a wireless. So this is again divided into three categories. One is radio waves, microwaves, infrared. Okay, so these are all the wireless medium. So there will be no wire. And coming to this twisted pair, the name itself indicates here we will be having two copper wires, so separately insulated, and these are in a twisted format. So what's the purpose of two wires? So one wire is for transmitting the data, and the second wire is for ground. So these wires will be twisted manner, in a twisted manner. So because with the help of this twisted manner, it will reduce the noise and the crosstalk over the data in the wire, in the cable. So that's why these two copper wires will be in a twisted manner in order to reduce the noise and crosstalk. Right. So this twisted pair is again classified into shielded, unshielded, shielded twisted pair and unshielded twisted pair. So this is called STP, shielded twisted pair. This is called UTP, unshielded twisted pair. See here, this is coming to this unshielded twisted pair. So there will be two wires. So as we have discussed, just two wires. One is for data, another one is for ground, and both will be in a twisted manner. So the expensive is also very less, and it is also very easy to install. Right. So and the data is low. The data rate is low. So the transmission of data from one system to another system, the data rate will be low for this unshielded twisted pair. And coming to this shielded twisted pair, it is also a pair of copper wires in a twisted manner. And again, these cables will be shielded with, enclosed with one mesh or some foil. Right? So that is nothing but another ground. Okay. So here, the cable, the twisted pair will again enclose it with a mesh. Here there will be no mesh. Okay, so the data rate will be high as well as the expensive when compared to this unshielded twisted pair, and also it is somewhat difficult to install by using these shielded twisted pair cables when compared to the unshielded twisted pair cables. Right. So see, I will show you a simple thing. So unshielded twisted pair, let us take this as a cable. See, this is a twisted pair cable, unshielded twisted pair. So there is no shield. Okay, so this is nothing but one cable. And coming to this one, see, so this is a foil. So twisted pair, again it is enclosed with this foil or a mesh. Here there is no foil or mesh, directly the cables will be there. Right? So this is all about this shielded twisted pair and unshielded twisted pair. So the mainly these twisted pair cables are used earlier in a telephone lines. Right? So in a telephone lines or a LAN cables and all these things in earlier days, right? So coming to this coaxial coaxial cables. So here, again, this is a copper cable shielded with metal shielding, enclosed with a metal shielding, designed to provide the immunity against noise and this data, crosstalk. So here we are using the twisted pair. So we are twisting the cables in order to reduce the noise and crosstalk. But here we are not twisting the cable, but we are enclosing these copper wires with a metal shield which acts as a ground. Okay. See. So this is a coaxial cable. This is a coaxial cable, right? So this is a metal shielding. Outer insulation. This is a insulation, and this is a copper wire. This is a copper wire. Okay, so this is a coaxial cable. So here also we are reducing the noise and crosstalk, but with the help of metal shielding. But here we are reducing the noise and crosstalk with the help of twisting the cables, right? So here also it can transmit the data in a long distance, right? With a high data rates. Here also the data rate is high, and the data can be sent. The data can be sent through a long distance. Okay. So coming to this fiber optics, so it is completely use of glass, and here we can use this in a cable TV cables. Okay, cable TV. Okay, cable TV network, using a cable TV network or a telephone network. Now, then coming to this fiber optics, the fiber optics is completely of a glass, which is used as a waveguide to transmit the light signal from one system to another system. Right? So this is completely, the medium is a glass. It's not a cable, it's a glass. So through the glass, the data will be sent. So here also there are two layers. For this fiber optics also, there are two layers of a glass. The first one is called a core, which is used to transmit the data. The second one is cladding, just like our shield, metal shield. It's a cladding. The upper layer of this core is a cladding. Okay. So with the help of this one, the data will be transferred through this glass. Okay, so it can be done in two ways. One is a single mode and multi-mode. The fiber optics can be implemented in single mode. Right here. Okay. So single mode and multi-mode. So here the name itself indicates single mode means only single data mode can be sent, and multi-mode means at a time the multiple modes of light can be propagated. Right? So this is the different modes of fiber optics. So this is also used in LANs, okay, cables, etc. Right? Then coming to this wireless unguided, that means unguided transmission media, that is a wireless media. First one is the radio waves. So these radio waves, this is mainly used in multicasting. Multicasting means only one sender will be there and multiple receivers will be there, right? So the data will be propagated in all the directions without any security. So any receiver can receive the signal from the radio waves. So the best example for this radio waves is FM radio. So through the signal, any receiver can catch the signal and they can use the data. So this is called, this is mainly used in multicasting. One sender and multiple receivers. Right. So coming to these microwaves, this is again differentiated into two categories. So one is terrestrial microwaves and satellite microwaves, terrestrial and satellite. So the difference between these two is completely depends upon the range. So within the limited range, we will use this terrestrial microwaves, and within the large range, so wide range, we can go with the satellite. So best example for the satellite microwaves is our mobile network, right? So the data can be sent. So weather report, weather forecasting also comes under this satellite microwaves. Okay, so these are all comes under this microwaves. And coming to this infrared. So this is for communicating over a short ranges. So if we want to communicate over limited range or short range, we'll go with the infrared rates. That means example, so sharing the files from one mobile to another mobile. So that must be kept in a limited range so that the data can be transferred from one mobile to another mobile. So that is one example for this infrared. And also TV remote operation. So the TV, if you want to, operating the TV remote, so the channels will be changing, the volume will be changing, and all this will be done with the help of this infrared waves. So that is nothing but here we are not using any type of wires. So that's why it is called as a wireless transmission media. That is also called as unguided. So we are not guiding. Okay. So directly the receiver will receive this infrared signals or microwaves or radio waves. So one among these transmission medium, the raw bits will be transferred from one system to another system in physical area. Right? So hope you understood. The transmission medium is of two ways. One is guided and unguided, wired and unwired. So coming to this guided, there are three categories. One is a twisted pair, coaxial, and a fiber optics. Right? So twisted pair. So one final aim of all these things is to reduce the noise and the crosstalk. So for that purpose, here we are using the cables will be twisted, and here we are using the metal shielding, and here we are using the glass with the two layers. One is for the core and another one is cladding. And coming to this unguided, we'll go with the radio waves, microwaves, and infrared rays. The design issues of data link layer. So DLL means the data link layer. So the major design issues here is the flow control. So how the data frames will be controlled in between the sender and receiver host, right? So that we call it as a flow control. And the second important design issue is error control. So error control will be having both detection and correction, error correction and error detection, right? So we'll go with this flow control in this session, and the next session we'll go with this error control, right? So coming to this flow control, so first the data will be in form of frames in data link layer. So how these frames will be recognized, represented. So the payload will be done. So in this payload, header will be included. Similarly, trailer will be included. And this combinedly forms a frame. Right. So this combinedly forms a frame. We call it as a data frame. Right. This is completely it's a frame. So the data will be recognized in terms of frames. Here the payload is actual data which is going to be sent from the sender host to the receiver host. Right. So what is meant by this? So how this data controlled, these data frames will be controlled between the sender and receiver. So we know that the sender will be there and the receiver will be there. Right. So particularly in this flow control, so the speed is a most important issue. So whatever the speed the sender is sending the messages, the receiver must be able to receive those data frames at the particular speed itself, at the same speed itself, right? So both have to work, sender and receiver both have to work at the same speed, okay, at the same speed. So at what speed the sender sends the messages, with the same speed the receiver have to process the data frames, right? So what happens if it violates? That means if sender is sending with a more speed and receiver receives with a less speed, automatically at the receiver side there might be a chance of overloading. So before processing the data frames, so new data frames will be arriving at the receiver side. So that's why we call it as a overloading. So this overloading will be done here so that the result will be the data loss. So due to this overloading, some data will be lost. So this happens if the speed is difference between the sender and receiver. So that means if sender and receiver following the different speeds, so automatically the overloading will be done, which results the data loss. So both have to work in a same speed, consistent speed. Right. So in order to control these data frames, it can be done by using two types of mechanisms. So this control flow depends upon two mechanisms. This can be done in two mechanisms. So first one is stop and wait mechanism. And the second one is sliding window mechanism. So if you follow these two techniques, automatically the control, that there will be a control on data frames. So there will be no data loss, right? So in the stop and wait, here the name itself indicates stop, wait. So here there will be a sender and a receiver So whenever the data is sent from sender to receiver, so let it be, it's a frame 1. So senders should stop and wait until the sender receives an acknowledgement from the receiver. So unless it receives an acknowledgement for frame 1 from the receiver, this sender will stop and it wait for the acknowledgements. It doesn't send the next data frame. Right? So whenever this receiver sends an acknowledgement of 1, that means for frame 1, immediately now the sender will again sends the data frame, the next data frame. And again the sender stop sending the data frames and it waits for the acknowledgement from the receiver. So again it have to receive the acknowledgement from the receiver. So this can control the flow of data frames, but here the resource will be wasted, the time is wasted, and also the utilization of resources is also wasted because the sender have to wait until it gets the acknowledgement from the receiver. That means it should be in idle position, right? So for the in the sliding window technique, there will be a sender and receiver. So here, so instead of sending the acknowledgement after each and every frame, the acknowledgement will be sent after the some set of frames. After sending the some set of frames. So some set of frames will be depends upon the window size. So after sending a few frames, then the acknowledgement will be coming from the receiver. Right? So the sender will be keep on sending the frames. After some set of frames, then the receiver will start sending the acknowledgement for sender for the received data frames. So this by this we can, so there will be one window. So a set of frames will be sent. Right? So this is how we can the flow of data from frames can be controlled by using the stop and wait and the sliding window. Right. So let us stop here and hope you understood this flow control in the data link layer. So we'll go with the next session, that is error control. Error control. So the only one answer for this error control is retransmission. So as we know that in data link layer the data will be processed in terms of frames. So the sender keeps on sending the frames, data frames along with the sequence number to the receiver, and if the receiver doesn't receive the data frame or it receives the frame after some time out, then the only solution for this error control is this retransmission. Right? So till now the phases of error control are the first one, error detection. So error detection means, so first we have to find whether the error occurred or not. So for this the acknowledgement will be done, the acknowledgement will be sent from the receiver to the sender. If the acknowledgement is not received by the receiver, then automatically we can detect that there might be an error occurred. So first phase of this error control is error detection. So we have to detect the error first. The second one is acknowledgement. Acknowledgement, we can call it as ACK, acknowledgement. So after receiving the data frame from the sender, the receiver have to send an acknowledgement to the sender by saying that to represent the successful delivery of that particular data frame. So this acknowledgement can be classified into two ways. One is a positive acknowledgement, another one is a negative acknowledgement. So positive ACK and negative ACK. Okay, so positive ACK, so both will be sent by the receiver itself. So when will be the positive acknowledgement and when will be the negative acknowledgement. So if the data frame is successfully received by the receiver, then the receiver will send this positive ACK. And if the data frame is corrupted or if the data frame is not received by the receiver, then in such cases the receiver will send this negative acknowledgement. Okay, so if the sender gets this negative acknowledgement, that means the data frame is not received by the receiver or the data frame is corrupted during the transmission. So any one reason may happen, right? So this is all about this acknowledgement. Next, the third phase, nothing but retransmission. retransmission. So by checking the acknowledgement whether it is a positive or a negative, if it is a positive, the sender will keep on sending the next set of some data frames. So if the sender receives this negative acknowledgement, that implies so the sender have to retransmit the data frame. Once again, resends the data frame to the receiver. So these are the phases involved in this error control, and this error control can be implemented by using the 3 protocols. Okay? So we'll see those protocols. So error control protocols. The first one is, as we have seen in the flow control, that is a stop and wait. Stop and wait protocol. Second one, go back and protocol. The third one, selective repeat. Selective repeat protocol. Right? So stop and wait, go back and selective repeat. Right. See, in these 2 cases, we'll use the sliding window. Where in the stop and wait, we are not using any sliding window. So actually, these 2 terms we have already seen in the flow control. So what is meant by a stop and wait and what is meant by a sliding window? Right? So in the stop and wait, the sender keep on sending the data frames. So after receiving the data frame, immediately it will send the receiver will send the acknowledgement. So unless it receives the acknowledgement from the receiver for the data frame which has been sent, the sender have to wait and it have to stop sending the data frames. See, I will explain you an example. So actually we have already covered the stop and wait protocol in flow control, right? So there will be a sender, just a recall, a receiver. So the sender will send the data frame 1, and after sending one data frame, the sender have to stop sending the remaining data frames and have to wait for the acknowledgement from the receiver. So once the receiver receives the data frame, the receiver will send the acknowledgement for the frame 1, so acknowledgement 1. So after receiving the acknowledgement from the receiver, the sender will send the next data frame, so frame 2. Right? So here the sender will use a time counter. So this time counter will be started immediately after the data frame is sent from the sender. So this is because, so after some time period, even though the sender doesn't receive any acknowledgement from the receiver within the timeout, so automatically the sender will retransmit the data. See, frame 2. So frame 2, here the time slot some 5 seconds. There is a 5 seconds. So time counter will start. The time counter will be starting immediately after sending the data frame. So after 5 seconds, if this receiver doesn't send the acknowledgement, after completion of this time period, again it will send the frame 2. Hope you understood. So the time counter, the timer will be there, and this time counter will be enabled immediately after sending one data frame. So within the timer, that if the sender doesn't receive any acknowledgement from the receiver, it will again resends the data frame. And this is common for all the 3 protocols. Right? So this we call it as automatic repeat request. We will call as ARQ. So automatic repeat request. So this will be based upon this counter timer. Right? So this happens in the stop and wait. So there are some drawbacks here. So as we have discussed in the earlier session. So sender have to wait a more time until it gets the acknowledgement from the receiver. So the resource utilization will be very less. Okay, the resource will not be utilized perfectly. So for that purpose, we are moving on to the next protocol, that is go back N protocol. So we will see that one. Go back N protocol. So here also there will be a sender and receiver. Right? But here we'll use a sliding window. Right? So there will be a sliding window at the sender side. Okay, in this go back N. So this will be having a size. Right? So the sender will keep on sending the frames without waiting for acknowledgement. So it will send the frames based upon the window size. If the window size is 4, the 4 frames will be sent to the receiver, and it doesn't wait for the acknowledgement. Right? So see, frame. Right. So it doesn't wait for the acknowledgement. So after the receiver will receive the data frames coming from the sender, and based upon the sequence numbers, it will send the acknowledgement to the sender. Okay. So see. So here it has sent the acknowledgement 1 and acknowledgement 2 and the timer. Okay. Here also the time counter will be there. So within the time counter, the sender have to receive the acknowledgements. So after acknowledgement 2, that means here it sends only the acknowledgement 2 and it doesn't send the acknowledgement for frame 3. Okay, it doesn't send the acknowledgement for frame 3. So immediately the sender will start resending the frames from which it doesn't receive the acknowledgement. For example, right, let me explain once again. So here the sender sends 4 frames. So because let us take the size of the window is a 4. Okay, the sliding window size is 4. So until it sends the 4 frames, it doesn't wait for the acknowledgement, right? It keep on sending the 4 frames. So the receiver will receive all the 4 frames and it will be sending the acknowledgement to the sender. So later, after completion of all these 4 frames, the sender will check for the acknowledgements. So in that acknowledgements, if the sender receives only 2 acknowledgements, that means acknowledgement for frame 1, acknowledgement for frame 2, that implies it doesn't receive the acknowledgement for frame 3. Right? So immediately the sender will start resending the frames from the frame which it is not receiving the acknowledgement. So in this example, the sender received only 2 acknowledgements, acknowledgement 1, acknowledgement 2. Right? So it doesn't receive any acknowledgement for frame 3. So immediately the sender will send frame 3 and 4. It will again resend frame 3 and frame 4. So because frame 3 we are not receiving the sender not receiving the acknowledgement. So frame 3 and frame 4 will be retransmitted to the receiver. Right? So receiver will not have any buffers. Here the sender will be having the buffers which maintains the data of acknowledgements and the data frames. Right? So in this case the receiver doesn't have any buffers. So that here the drawback is, so wherever from where the acknowledgement has not been received, all the remaining frames will be retransmitted. So if it gets all the acknowledgements for all the 4 frames, then the next set of frames will be transmitted. So here we'll use the positive acknowledgement and negative acknowledgement. So if the sender receives all the 4 positive acknowledgements from the receiver, it again sends the next set of 4 frames. Right? So if it receives only the acknowledgement for 2 frames, the remaining frames from which the acknowledgement was not received, that will be retransmitted. So that is the drawback here. And that will be avoided in the next protocol, that is selective repeat. See, selective repeat protocol. Here, the receiver will also maintain the buffer in order to maintain the received frames. Right? So here also the same thing. The sender will send the frames to the receiver. The receiver will maintain the buffer to maintain the received frames with the sequence numbers. Right? So here, see, if the sender doesn't receive the acknowledgement for frame 3, it will resend only the frame for which it was not receiving the acknowledgement. Right? Okay, so here, so previously the sender doesn't receive any acknowledgement after frame 2, so it resends the remaining all the frames. But here the receiver also having the buffer, it is also maintaining the frames which are received by the sender with the sequence number. So based upon this buffer, it will send acknowledgements, and here in this case the sender will resend the only frames which are not acknowledged by the sender. Right? So if the sender sends the 4 frames, because here we are considering the size as 4 frames has been sent to the receiver, right? And the sender doesn't receive the acknowledgement for frame 3 and it receives the acknowledgement for frame 4. So the sender will send only the frame 3 because the sender doesn't receive any acknowledgement for frame 3. But in the case of go back N, the sender will send the frames after the frame 2. That means frame 3 and 4 will be resent to the receiver. Right? So hope you understood this selective repeat protocol. So this is all the 3 protocols are used for error control. So the only answer for this one is retransmission. So in which cases we have to retransmit it, what type of retransmission will be done, based upon which criteria the retransmission will be done. So in the stop and wait, the sender will stop until it gets the acknowledgement. In the go back N, the sender only will be having the buffers, so from where the acknowledgements was not received, it will resend all the frames. So in the selective repeat, the only one frame, sorry, not only the only one frame, only the frames which are not received by the acknowledgement was not received by the sender, those frames will be retransmitted. Right. So error detection. So in this error detection, let us know about what is meant by an error and how many ways the error can be obtained. So an error in this communication means interchanging of bits. So the complete data will be transmitted from source to destination in terms of bits. That means either 0 or 1. So here the error is the 1 becomes 0 and 0 becomes 1. Right? So if in the transmitted data, if this type of exchange or interchange is done, that means that implies the data is corrupted or an error is occurred. So how many types of errors? So there may be a single bit error, and burst error. See, so coming to the single bit error, the name itself indicates only one bit will be corrupted in the transmitted data. So as it is an error detection, in this we can know that the data is corrupted, but we can't predict which data or which bit is corrupted. Right? So for example, let us take, so this is the data to be transmitted from sender to receiver. So this is the sender and this is the receiver. But at the receiver have received, see, second bit as 1 instead of 0. So this is the original data transmitted from source to destination, but due to the voltage problem or any other frequency problem, the 1 bit is exchanged or interchanged. That means the 0 becomes 1. So that means there is a corruption on the second bit, right? So in this error detection, the name itself indicates a detection. That means we can detect that there is an error, but we can't predict where the error is. Okay, so only 1 bit has been corrupted. So such a type of error we call it as a single bit error. Okay, single bit error. And in the burst error, coming to the burst error, multiple bits, not the 1 bit, multiple bits will be corrupted. For example, the same data is transmitted if it receives, see, if you observe, the first bit, the original data is 1, but the received data is 0. Second bit is 0, second bit is 1, third bit is 1, third bit is 0. So that means there is a corruption on multiple bits, right? So in that multiple bits, we call it as a burst error. If it is a single bit error, it is called a single bit error. Hope you understood. Here we can only detect the error. That means we know that there is a corruption on the bits, but we can't predict where the corruption is exactly, right? So for this, there are 2 methods to identify. See, detection. So one is the parity. In order to detect the single bit error, we'll go with this parity. Okay, and there is one more method called CRC, Cyclic Redundancy Check. So by using this one, we can detect the burst errors. Okay, 2 techniques. Majorly 2 techniques are used to identify whether it is a single bit error or the burst error. For single bit error, to identify, we'll use this parity, and here to identify the burst error, we'll follow this Cyclic Redundancy Check. Right. So coming to this parity. So coming to this parity, for this, one additional bit will be added to the original data and it will be sent to the receiver. So what is that additional bit? What represents that additional bit? So that additional bit represents the parity check. right? So here the main functionality of this parity is count of ones. So the data will be in terms of zeros and ones. The count of ones should be even. Should be even. That's the main aim. Okay. So it may be odd also, right? Let us consider if it is even, right? So the count of ones should be even. So for that purpose, we'll take the data. So here, what is this data? So this is the data, right? This is the data. This should be transmitted from source to destination. Here count the ones 1 and 2. That means even. The count of ones is even. So we will add 0 as an additional bit. 0 as an additional bit because already the count of ones is even. So here this is the data and this is the even parity bit. Even parity bit. Right? So this will be transmitted from source to destination. So receiver and sender. So receiver will receive the data so that again the receiver will count the number of ones so the last bit is a parity bit, even parity. So that implies the number of ones should be even. Right? So if there is any change, for example 1 1 1 0 0 0. Okay, sorry. At the receiver side, if it receives this one, as the receiver knows this is an even parity because the last bit is 0, it's an even parity. So the receiver will count the number of ones it will getting the odd such that the receiver will know that there is some corruption in the data which is sent by the sender. Okay, so for that identification we'll add one parity bit. So this is called even parity. This is called even parity. Coming to the second one, see. If you consider the data as this one, so this is the data, okay, and we have to add one bit at the end, okay, so this is the bit we have added. This is called an even parity bit which is added to the data. Here also we have to add the parity bit, okay, so here count the number of ones 1 2 3. The count of ones is odd. So we have to make it even. So the odd parity bit must be 1. So the 1 will be added to the data. So this is the data and this is the odd parity bit. And this will be transmitted to the receiver. So if the receiver receives the same, so that it will count the number of ones, it becomes even, right? So because the last one is appended with 1, so that the total count of ones will be odd. So that the even parity bit, the odd parity bit will be appended with 1. So it becomes even. So that implies it is an original data. The data is not corrupted during the transmission. If this data is received in such a way, 1 0 0 0 1 1. This implies, so see, count the number of ones. So last one we are appending with 1 such that the number of ones should be odd. Okay, right? So this is called odd parity. That means if the data contains the number of ones odd, we are appending 1 as a parity bit. Okay, 1 as a parity bit to make the number of ones as even. So here, if the data received in such a way, here last bit is the parity bit appended 1. That implies, so this one means odd parity. Odd parity means the number of ones should be odd. So here if you count other than this parity bit, the number of ones are even. So that the receiver will decide that this is the data is corrupted. 1 bit is corrupted. Right? So this will not work for 2-bit change. See, if you observe here, if the data is this one, okay, so 1 0 0, if it becomes 1, see, if it becomes 1, it is the parity bit is 1. That means the number of ones other than the parity bit should be odd. So it is true. So the receiver doesn't know that the receiver will treat it as a perfect data which is received by the sender, right? There is no corruption. The receiver will decide that there is no corruption on data, but there is a corruption because here the first bit is 1, second bit is 0, third bit is 1, but here it received 0, fourth bit is 0, but here it received 1. But according to this parity check, the last bit, the parity bit is 1, so that other than this parity bit, all the number of ones should be odd. So that satisfies here. That satisfies here. So that implies, so even though there is a corruption on bits, the receiver doesn't know that the corruption occurs in the data, right? So there's a main drawback of this parity check. So this parity check is used for only single bit errors. So multiple bit errors can't be identified by this parity check, right? So hope you understood this parity check. So even parity, odd parity. So even parity means if the data contains even number of ones, automatically the last parity bit will be added as 0. Odd parity means if the data contains the number of ones in odd number, so in order to make it even, we'll add 1 as a parity bit. So this all happens in this parity, even parity and odd parity. Mainly it is used for identifying the single bit errors. What about the burst errors? Burst error means multiple errors. So this the main drawback of this one is you can't identify the multiple errors. Right? So for this purpose, we'll move on to the next error detection method, that is CRC, that is cyclic redundancy check. Okay, so only one solution for this type of methods in the error detection is retransmission of packet. So if receiver identifies there is a corruption in the data, automatically the receiver will request the sender to the retransmission, because here these are the only meant for error detection. There will be no correction. So the receiver will only detect the error, he can't able to correct the errors, right? So error correction will not be there. So whatever the technique you take, whether it is in parity or a CRC, the only solution for this one is retransmission, and this retransmission request depends upon the error detection. If there is any error, automatically the receiver will request the sender to retransmit the data. See, for this we have to consider the data, and the second one is CRC generator. So with the help of this generator, we will find the redundancy bits, and here we have to identify the redundancy bits, or we can call it as a CRC bits. Okay, CRC bits, right? So here we have to know about one thing, that is if the CRC generator is of n bits, the length of the CRC generator is n bits, so this CRC bits will be n minus 1. The CRC bits will be n minus 1. And initially we have to find the CRC bits. For that purpose, we have to add this data plus this CRC bits, that means n minus 1 zeros, and we have to divide that with the CRC generator. Right? So which gives the CRC bits. Okay, so hope you understood this one. So first we have to consider the data and the CRC generator. The CRC generator. So if the CRC generator length is of n bits, the CRC bits will be n minus 1. So if it is a 4, the CRC bits will be 3 bits. So the data, whatever the data we are considering, plus n minus 1 zeros. So initially we don't know this CRC. So this is for calculating the CRC bits, right? So what is the CRC bits? That means data plus n minus 1 zeros must be divided with CRC generator. So whatever the remainder we are getting, not the quotient, okay? The remainder is an important. The remainder will be the CRC bits. So remainder is a CRC bits, okay? Not the quotient. So data plus, if the CRC generator is of 4 bits, the CRC bits will be 3 bits. So here the data plus n minus 1 means 0, 0, 0, 3 bits and 3 zeros. That means the 3 zeros must be appended to the data, which is divided by this CRC generator. So whatever the remainder we are getting, that remainder will be the CRC bits. So this will be calculated at the sender side. This will be calculated at the sender side. And after getting the CRC, finally the data plus CRC will be combined and it will be transferred to the receiver. From the sender, this calculation will be done for identifying the CRC bits. So the data plus CRC will be sent to the receiver. So at the receiver side, so this is all will be done at sender. Okay, this is all will be done at sender. At the receiver side, so this will be considered data plus CRC, again the data plus CRC will be divided with this CRC generator, the same CRC generator, which will give zeros as a reminder. If we get the zeros as a reminder, that implies the data is not being corrupted during the transmission. So that means there is no change in the data bits from the sender to receiver. And if we not get a zero, that means if you get the non-zero value as a reminder, that implies there might be some modification or some data has been corrupted during the transmission. So if it identifies the data is corrupted, automatically the receiver will request the sender to retransmit the data. So in this process, the receiver will only detect the error, but receiver doesn't know where actually or what are the bits actually being corrupted. Right? So the only single solution for this error detection methods is retransmission of data. So only the receiver will identify whether the data has been corrupted or not. Right? So let us take an example so that your doubts will be clarified. So see, and here the division means here we'll do the XOR operations. Okay, here the division means, so that is also important. So here the division means XOR operation. XOR operation means we know that if one is true and another one is false, we'll get the true. Okay, if both are true or both are false, we'll get the false result. So that will be done in the division process. Right. So let us consider an example. Let us take the data as random data. Let's take it random data. So 101 and 101. Okay, 101 and 101. And the CRC generator is 1101. Okay, CRC generator is 1101. So that there are 4 bits. So the CRC bits must be 3. So the CRC bits must be 3. Okay, so division XOR. Let us take the data. So we have to find the CRC bits. CRC bits is equal to, so append this data plus 3 zeros because the CRC bits are 3. So 1, 0, 1, 1, 0, 1 and append 3 bits and divide it with the CRC generator. So 1101 and we have to apply the XOR as a division. Okay, so no need of having the quotient. Okay, don't follow the quotient, just we need the remainder. So we can directly apply this one. So here we have to apply the XOR operation, right? So XOR operation. So 1 1 it's a 0, 0 1 it's a 1, 1 0 1, 1 1 0. Right? So start from the leading one. So omit all the zeros on the left side, start with the leading one. So omit this part. So consider this one. So here there are 3 digits, 3 bits. Here we are having the 4 bits. So you can take this one 0. Okay. So again follow the same procedure 1 1 0 1. Apply here, it's a 0, 0, 0 and 1. So omit all the leftmost zeros, right? So omit all the leftmost zeros. Consider from here. So 1, 0, 0. Okay, again follow the same procedure 1, 1, 0, 1 and here it is 0, 0, 0, 1. Again omit all the left hand side zeros. So you can have it here 1. Okay, so after getting the 0, we are having only 2 bits. Here we are having the 4 bits as a CRC generator. The divisor is having 4 bits and here we are getting the remainder as 1 0. So in such case, stop the process and consider the 3 bits. Consider the 3 bits. So not the 3 bits, consider the CRC, the number of CRC bits. So here it is 3. So we have to consider these 3 bits as a CRC bits. So here the CRC is 0 1 0. CRC bits are 0 1 0. So hope you understood, right? So first consider the data and append the number of CRC bits zeros. Okay, so here the CRC bits is 0. So the number of CRC bits depends upon the number of bits of CRC generator. So here the number of bits of CRC generator is 4. Here the CRC bits will be n minus 1, that is 3. So division operation here we are performing is XOR, right? So apply this divisor, that is CRC generator 1101 and we have to append 3 zeros for the data and we have to done the process. While doing this division operation, omit all the leftmost zeros and start from the leading one. So I am applying here. So stop the process if you get the remainder less than the divisor. Remainder less than the divisor. So I got the remainder 1 0 and here 2 bits and divisor is 4 bits. I have stopped the process and consider the CRC bits, the length of CRC bits, that means 3 bits. So consider 3 bits. So 0 1 0 will be the result. That means CRC bits. Redundancy bits are 0, 1, 0. So now the sender will send the data. The sender will send the data 101, 101, and it will append these CRC bits to the here. Okay, so these are the data which is sent by the sender. So 101, 101, which is nothing but our data plus CRC. So data plus CRC. So this should be sent to the receiver side, right? So this will be sent to the receiver side. Again, here the receiver receives the data. See, receiver receives the data as 101, 101, and 010. This is the data received by the receiver from the sender. So this is the actual data, and these three are the CRC bits. These three are the CRC bits. Now again, consider the CRC generator, which is nothing but 1101, which we have calculated from the sender. So both the sender and receiver should use the only one CRC generator, the same CRC generator. Now again, calculate the division operation. Apply the division operation. So 101, 101, 010. So it is divided with 1101. So here the result we should get it as 0. If we get 0, that implies the data has not been corrupted during the transmission. Right. So let us check. So 1101, apply the XOR operation. So 0, 1, 1, 0. So omit the left hand most zeros and consider from the leading one. So again 0, 11, 0, 1, again 0, 0, 0, 1. Again omit all the left hand side. So consider this one. Again 1, 0, 0. Right? So 11, sorry, here it is 1. Okay. Right. 11, 0, 1, which is again 0, 0, 0, 0. So if you apply here, it is 0. So finally we got the result as a 0. Okay. If we got the result as 0, that implies the data has not been corrupted. The sender, the receiver will know that data is not being corrupted. So this is how we will calculate this CRC. We can we can detect the error. So this is only for detection, not for the correction. So the receiver knows that there is no corrupted data, right? So if you change one bit, for example, if you consider this is the received data, okay, actual data we got is this one 1011011010, but here the second bit has been changed 0 and here it is 1. Now check out the result. What we'll get? Actually the data is corrupted during the transmission, so we'll check it out. So let us take a 2-bit corruption. Okay, 2-bit corruption. Let us take the 2-bit corruption. Okay, so first bit 1 same, second bit 0 becomes 1, third bit 1 becomes 0, and all the remaining is same. So 2 bits have been corrupted, the second bit and third bit. Now we'll check. So 1101, 01, 010. Okay, so apply the same thing. 1101. So all are zeros because we are applying the XOR operation. So consider, so omit everything. So consider the same 0, 1, 0, 1, and apply the same 1101. So that 1, 0, 0, 0, and apply the same here. Sorry, here we can't omit anything. 100. Again the same apply here. 1101. We'll get 0, 1, 0, 1. Omit this one and bring this one here. So 4 bits. Again 1101. So we'll get 0, 1, 1, 1, which is not a 0. It's not a 0. So this implies that receiver will know that some data has been corrupted during the transmission, but the receiver doesn't know that second bit and the third bit has been corrupted. The receiver only detects the error. So then immediately the receiver will request for the retransmission of data from the sender. Right? So this is how we can detect the error by using the cyclic redundancy check. So we have to remember this thing. First data, consider the data. So next CRC generator of any number of bits, but depends upon the n number of bits, CRC bits must be n minus 1. And division is XOR. The first thing we have to add the zeros, the CRC bits, the length of the CRC bits, zeros with the data, because initially we doesn't know the CRC. That means the redundancy bits we don't know. So in order to calculate those redundancy bits, we will append the zeros to the data and it will be divided with the CRC generator. Right? So then finally we'll get the n number of CRC bits here at the end. So that CRC bits will be appended to the original data and that will be sent to the receiver. And at the receiver again, that complete data plus CRC will be divided with the CRC generator, so that the result must be 0. We have to get the remainder 0. If the remainder is 0, that implies the data has not been corrupted during the transmission. If the if the remainder is a non-zero, that implies some of the data has been corrupted during the transmission. So the receiver can only detect the error but cannot identify what actually bits has been corrupted. So the solution for this error detection methods is only the retransmission. So whenever the receiver detects the error, whenever the receiver identifies that there is some data has been corrupted, so immediately the receiver will request to the sender for the retransmission of data. Right? So hope you understood the cyclic redundancy check. So let us stop here. So in the next session we'll go with the error correction. So the receiver can able to identify the error and also it can be able to correct the errors, which is not done in this error detection. Error detection and also the correction. So that means in this the sender can able to identify the error and also the sender can able to identify at which place the error exists. So for this there is a method called Hamming code. Hamming code, right? So with the help of this Hamming code we can identify and correct the single bit errors. 1 bit errors can be identified, right? So for this the requirements are the data, which can be represented as M. It can be of any length. Okay, it can be of any length. Then we need redundant bits. Redundant bits, which is represented as R, and that depends on this M. So that means we can select the R such that 2 power R should be greater than or equal to the data plus R plus 1. So with the help of this equation we have to find out the length of R. The length of R depends upon this equation. So with the help of this equation we have to find that, right? Then after that the sender will send the message, the plain text or the data plus the redundant bits. And one more thing, here the redundant bits must be placed at the powers of 2. Powers of 2. For example, R1 should be placed at 2 power 0. R2 should be placed at 2 power 1. R3 should be placed at 2 power 2. R4 should be placed at 2 power 4 and so on. Right? So it depends upon the length of the R. We have to place those bits in these positions. So this is nothing but a position where these redundant bits should be placed. So for example, so if the R is some 4, then we can say the parity bits. So these are nothing but a parity bits. Okay, so parity bits. So parity bits will be P4, P8, P4, P2 and P1, because this is at the position 2 power 0, this is at the position 2 power 1, this is at the position 2 power 2 and this is the position 2 power 3. That means this 1, 2, 4, 8 are nothing but the positions. Okay, so all these are the positions where we have to include this parity bits. So that is common for everyone, right? So that is common for everyone. So all the parity bits should be placed at the powers of 2. And then we have to follow either even parity or odd parity. The data should be in even parity or odd parity. So we have discussed about this even parity and odd parity in the earlier session. So if the total number of ones are even, then the parity bit should be 0. If the total number of bits are odd, the parity bit should be 1. Okay, so here we have to achieve this even parity. So for identifying the P1, right? So we have to verify the position of 1, the first position in all the binary numbers, right? So let us take the example so that you will be understand. So let us take an example. So hope you understood up to this one. So first we have to consider the data of any length, it can be of any length, and then we have to find out the redundant bits, that means the parity bits. So how many parity bits should be added here? So the length of the parity bits must be depends upon this equation, 2 power r greater than or equal to m plus r plus 1. So based upon this equation, we have to find out the length of r so that the position of parity bits will be considered. So the positions where we have to include these parity bits is at powers of 2. So after placing this one, we have to find all these parity bits, the value of these parity bits either 0 or 1, and that should be sent to the receiver. And the receiver again follow the same process and find out the error, and they will correct the error. The receiver will correct the error. Right? So I will give you an example so that your doubts will be clear. Okay. Now let us take an example for this. So in this session, I will take an example in a simple way. In the next session, I will give you one more example with a complicated. So I will increase the data and I will show you in the next session. In this session, let us take the data m with the 4 bits. Okay, 4 bits. So m is 4 bits. So the r parity bits r must be 2 power r greater than or equal to m plus r plus 1. That should be depend on this equation. So let us take from starting onwards. So 2 power 1 greater than or equal to 4 plus 1 plus 1. So 2 greater than or equal to 6. Failed. Next, 2 power 2 greater than or equal to 4 plus 2 plus 1. So 4 greater than or equal to 7. This also fails. 2 cube greater than or equal to 4 plus 3 plus 1. So 8 greater than or equal to 8. So this is correct. So we can consider R as 3. Okay. So R as 3 bits. So what are the 3 bits? Where we have to include this one. So these should be included at P4, P2, P1. Right? So first position, second position, fourth position. Right? So the total length of data will be m plus r, which is nothing but 7 bits. See, I will give you the 1, 2, 3, 4, 5, 6 and 7. Total 7 positions. So in that 7 positions, we have to include these parity bits at these positions. That means powers of 2. Right? So see, powers of 2 means first position there must be a parity bit. Second position there must be a parity bit. Third position no. So fourth position again we have to include the parity bit. And from the 3, 5, 6, 7 we will be having the actual data. That means this one. So 1, 0, 0, 1. So this is the order. And here the sender have to identify the bits of P1, P2, P4. Right? So after identifying the P1, P2, P4, this data will be sent to the receiver. So what is the procedure to find out these P1, P2, P4, bits of P1, P2, P4? So as this is the position 1 and we are having the length of 7, so write down all the possible binary representations of all these numbers. So that means 1, 2, 3, 4, 5, 6 and 7. So for 7, the binary representation, so 3 bits. Okay, the 3 bits representation. R is a 3, so 3 bit representation 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? So this is the positions. Right. So for identifying the first parity bit at position 1, so P1 must be identified with the help of positions where the first position is having 1s. So in all these numbers where we are having the first position as 1, 1 is having the first position. Second we are having 0, so we should not consider 2. And the 3 is having the first position as 1, so 3 should be considered. And again 4 is having 0, we should not consider. 5, again it is having 1, so we have to consider 5. And again 6 is having 0, we should not consider. 7 is having 1, so 7 should be considered. Right? So hope you understood. So P1 position is 1, so we have to find out the first positions. Right? So where we have the first positions. So the representation of parity bits is this one, P4, P2, P1. So this is nothing but P4, P2, P1. Right? So all P1s in this position, all ones should be considered. Similarly P2. So P2, the second bit should be 1. That means 2, 3, 6, 7. So 2, 3, 6 and 7. Similarly P4, the third bit. Third bit is, so 4, 5, 6, 7. 4, 5, 6 and 7. So hope you understood this one. So for identifying, so the 3 bits are the redundancy bits. So that will be represented as P4, P2, P1. That is nothing but our binary representation 0, 0, 1. So this is 2 power 0, 2 power 1, 2 power 2. Right? So in order to get the first parity bit, we have to identify, we have to consider the numbers which are having the first bit, the P1 bit with 1. That is 1, 3, 5, 7. Similarly P2, second bit, consider the second bit. So whatever the numbers we are having the second bit as 1, those numbers should be considered. So 2, 3, 6, 7. Similarly fourth bit, third bit, P4. So P4 is representation third bit. Okay, third bit, so it is 4, 5, 6, 7. Now, see, write down the bits. From this one, write down the bits here. So what is the value of P first position? P1. What is the value of third position? It's 1. What's the value of fifth position? It's 0. What's the value of seventh position? It's 1. Similarly here also. What's the value of second position? P2. Third position 1. Sixth position 0. Seventh position 1. Similarly fourth position P4. Fifth position 0. Sixth position 0. Seventh position 1. See, here we are having the 3 positions along with the parity bit, and we have to consider either even parity or odd parity. The data should be maintained in an even parity or odd parity. So even parity means the number of ones should be even. Odd parity means the number of ones should be odd. So let us consider for an even parity. Okay, let us consider for an even parity. So for even parity, the number of ones should be even. See, here we are having 2 ones, that means even number of ones. So P1 value can be 0. So if you include P1 value 0, the P1 101 will become 0101, which is nothing but even parity. Hope you understood, right? So we are considering this even parity. So for this even parity, already there are even number of ones, so we can place P1 as a 0. If you place P1 as 1, automatically this will be coming as a odd parity, but we are considering the even parity. So that here also you can consider P2 101, that means 2 ones are there already even, so P2 value can also be 0. And here coming to this one, see P4 001, so only 1 is there, right? Only 1 is there, that means the number of ones are odd. So to make it even, the P4 should be included as 1. So if, see, P2 101, so 0101, that is even parity. Similarly, P4 001, we have to include this P1 as 1001. So again, it will be considered as an even parity. So from here, P1 is equal to 0, P2 is equal to 0, P4 is equal to 1. So this is the value of the redundant bits. Now replace these values in our data. So P1 value is 0, P2 value is 0, and P4 value is 1. Okay, so P1 value is 0, P2 value is 0, and P4 value is 1. So we got this. So all these calculations will be done at sender. All these calculations will be done at sender. So sender will find the parity bits. So what is the value we have to include in the parity bits, and that will be included with the data, and this will be sent to the receiver. This will be sent to the receiver. So hope you understood. So first consider the data with an n number of length. So I am taking 4 for a simple understanding. So in the next session we'll increase the length, right? So from this we have to identify the length of parity bits. That is compulsory. We have to add some parity bits to the data, and we have to send for purpose of error detection and correction. So these parity bits must be like P4, P2, P1, right? That means these parity bits will be placed at the powers of 2. 2 power 0, 2 power 1, 2 power 2, 2 power 3, and etc. So here we are having only 3 bits. So this finding of R should be depends on 2 power R greater than or equal to m plus R plus 1. So based upon this equation, we have to find out the length of R. So here we are getting R is equal to 3 bits. So that's why. So we are writing all the combination of 3 bits. That is 0, 0, 1, 2, 1, 1, 1. So that means 1 to 7. And next we are placing the data and the parity bits. So in the position of first position, second position, fourth position, we are placing the parity bits and finding the parity bits. So for getting the P1, we are finding the numbers for which the first position is having 1. And coming to the P2, we are considering the numbers which is having the second position as 1. Coming to the third P4, we are considering the third bit with the numbers which are having the third bit as a 1. So in these bit positions, we are considering the actual bits, right? So first position, second position, third position, fifth and seventh. So here we are deciding that we have to send the data with an even parity. So that's why the total number of ones should be even. So we have to find out this, whether the data is without the parity bit, whether the data is even or odd. That means the number of ones are even or odd. So if the number of ones are even, the parity bit can be replaced as 0. If the number of ones are odd, we have to place the parity bit as 1 to make this sequence as even parity. So after getting all these things, we can place those values in the data. So I have placed the values here. So first position, second position, and fourth position. Now this is the actual data which is sent by the sender to the receiver. Now so this is about sender, right? So see, so this is the actual data sent by the sender. Now the receiver, so this is original data. Okay. Now the receiver receives the data with a single bit error. Received data. So 1. So I will change the position of 6 as 1. Okay. 0, 1, 1, 0, 0. Hope you understood. So actually the sender have to send the data this one, and the receiver received the data with 1 bit error. That means the bit the position 6, the bit of position 6 has been changed to 1. That means 1 error is there. So this is data with error. So at the receiver side, again follows the same procedure to find out whether we are getting the whether the receiver received the correct data or not. Same procedure. So find out the P1. For P1 consideration, we have to find out all the ones for first bit with the ones position. So 1, 3, 5, and 7. Similarly, P2 is also having 2, 3, 6, 7. So 2, 3, 6, and 7. Next, similarly, the third bit, that is a P4, fourth position, that is 4, 5, 6, 7. 4, 5, 6, 7. Right? So here also we have to consider whether the number of ones are even or odd, because we are considering the even parity. If it is an odd, then we have to consider the parity bit as 1. If all the ones are even, the parity bit will be 0. Right? So 1, first position is 0. See, this one we have to consider. This one we have to consider because this is received data at the receiver, right? So this is only the original data. So first position 0, third position 1, fifth position 0, seventh position 1. So the total number of ones are even. So that means P1 should be 0. P1 should be 0. Okay, consider P1, P2, P4. So P1 should be 0. P2. So second position 0, third position 1, sixth position 1, seventh position 1. So here we can observe there are odd number of ones. So in order to make it even, the P2 must be considered as 1. Okay, so hope you understood. The same procedure we are applying, but without the parity bits in this one, right? So we are just considering the positions 1, 3, 5, 7. The position number, the bits at this particular position are considered, and we are counting the number of ones, and we are considering whether it is an even or odd ones. So if the number of ones are even, then the P1 should be 0, and the number of ones are odd, the P2 the parity bit must be 1. And consider this one also 4, 5, 6, 7. 4, 5, 6, 7. So 1, 0, 1, 1. Again the parity bit. See, again the number of ones are odd. So to make it this one, the parity bit should be 1. So if we get all these three as zeros, that implies the data is original data. I mean, the data is not corrupted during the transmission. There is no bit error, right? So here, but we are not getting a 0. We are getting a non-zero. So representation for this one is P4, P2, P1. That is nothing but 1, 1, 0, right? So if we get this non-zero value for all the parity bits, that implies the receiver will know that the data has been corrupted. So now we have to correct the data. So at what position the data is corrupted? So convert these parity bits, the binary representation of these parity bits, to the decimal value. Decimal. So what's the value of decimal? This is a 6. So that implies there is a corruption of data on bit position 6. See. So now that the receiver can correct the data because there are only 2 bits, 0 or 1. So if the sixth position is having 1, it will be replaced to 0, and if the sixth position is having 0, it will be replaced to 1, because there is a 1 bit error, and we are finding the error and we are detecting the error. So by getting the decimal representation of all these parity bits, we'll get the position of a bit which has been corrected. So here we are getting 6. So 6 is having 1. So it should be replaced with 0, which is nothing but the original data. Hope you understood. Right? So by this one, we can the receiver can identify the error. They can detect the error, and also the receiver can know the position where the bit has been corrupted. So, for example, take the same thing and now find the send. So 1357. If the data is received perfectly without any error, then we will check. So 1357. 1 is 0, 3 is 1, 5 is 0, 7 is 1. So P1 should be 0. Right. Now consider the P2 and P4. 2, 0, 3, 1, 6, 0, 7, 1. So the number of ones are even. So P2 is 0. Next 4, 1, 5th position 0, 6th position 0, 7th position 1. Again the number of ones in this one is even. So this one is also 0. So that means if we get all these parity bits as a 0 at the receiver side, that implies there is no error in the received data. The data has been received perfectly during the transmission. So the data is not corrupted during the transmission. Right? So this is all about the Hamming code. This will identify and correct the 1-bit errors. So that can be done by the receiver. So first consider the data bits, and then we have to find out the parity bits, the number of parity bits based upon the equation, and we have to combine those data and parity bits, and we have to find out the values of parity bits, and then it will be sent to the receiver, so that the receiver will again follow the same procedure to find the parity bits, and he will identify, the receiver will identify and correct the errors. So we can consider even parity or odd parity, but here we are considering the even parity. So even parity means all the number of ones should be in even. If it's an odd parity, all the ones should be in odd. In today, we'll see one more example for this Hamming code. So in the previous example, we have taken the 4 bits of data, small length of bits. So this Hamming code can identify 1 bit error in n number of length. Okay, so we can consider the data with n number of length, but it can identify the 1 bit error. So previously we have seen with the simple problem, that is a data taken with the 4 bits and even parity. Now in this session, we'll go with one more example, that is the data we will consider with the 7 bits, and then we'll find the redundant bits, that is the parity bits, and then we will find the parity bits, the value of those parity bits, and the data sent to the receiver, and the receiver receives with the 1-bit error, and we can identify the error where the position where the error has been occurred. Right, we'll move on to the problem. So today also we are discussing about the Hamming code, example for Hamming code. So let us consider the data M as 7 bits. Let us take anything 101, 1011. So this is the data, which is a length of 7 bits, and we have to find out the R such that 2 power R should be greater than or equal to M plus R plus 1. So based upon this condition, we have to find out the R. So if you take 3, R is equal to 3, 2 power 3 is greater than or equal to 7. So 1, 2, 3, 4, 5, 6, 7. 7 plus 3 plus 1. So 8 greater than or equal to 11. So fails. Now R is equal to 4. So 2 power 4 greater than or equal to 7 plus 4 plus 1. So 16 greater than or equal to 12. So this satisfies. So this satisfies means we can consider these redundant bits as a 4. So R can be considered as 4. Right? So see, R can be considered as a 4 based upon the expression. 2 power R greater than or equal to M plus R plus 1. Right. So now the 4 redundant bits, where we have to place these 4 redundant bits. So we have discussed in the earlier session that these redundant bits should be placed at the powers of 2. So 2 power 0, 2 power 1, 2 power 2, 2 power 4. Right. So the position of this one is 1. So 2 is a 4, and it is 8. So this can be considered as a P1, P2, P4, P8 parity bits. These are the parity bits. So we will consider here. So the total length, we have to add these parity bits to the plain text, that is a data, and this should be sent to the receiver. So the total length of the message will be 7 plus 4 parity bits, that is 11. So we will consider 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Right? So first position, this is the position, right? So this is the position of parity bits. This is the position of parity bits. Now see, first position P1. fill these positions. Second position P2, fill this one. Fourth position P4, eighth position P8, and fill all the remaining with the data. So here 1, 0, 1, 1, 0, 1 and 1. Right? So this is the data which we have to send from the sender to receiver. Now we have to find out the values of all these parity bits. So here the complete data length is 11. So write down the binary equivalent of all these numbers. So 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. 8, so 1, 0, 0, 0, 9, 1, 0, 0, 1, so 10, 1, 0, 1, 0, so 11, 1, 0, 1, 1. So these are the binary equivalent for all the numbers. So we can consider the data of the length of the data. Here we are having 11 bits, 11 positions. So we will consider the binary equivalent for 1 to 11. Now, in order to identify the P1, as we have discussed it, so the redundant bits are P8, P4, P2, P1. So P8, P4, P2, P1. Similarly, P8, P4, P2, P1. Right. So in order to find the P1, we have to find all the numbers which are having the P1 value as 1. So here we can observe 1, 3. So this one 1, 3, 5, 7, 9, 11. So 1, 3, 5, 7, 9 and 11. So in order to identify this P1, we are supposed to find out the positions of all these things. Now, similarly, P2 means the second position. So second position, come to the second position P2. So 2, 3. So these are the second positions. 2, 3, 6, 7, 10, 11. So 2, 3, 6, 7, 10 and 11. Similarly, P4. That means fourth position. Here the P4 is the third one, right? So let us consider 1, 2, 3, 4. Right. So 4, 5, 6, 7 positions. 4, 5, 6, 7 positions. Similarly, P8. Let us consider the P8, 8th position. So here you consider the last P8, the fourth bit. So here you can observe 1, 2, 3, 4. That means 8, 9, 10, 11. 8, 9, 10, 11. So here we will consider the even parity. So even parity means, so the total number of ones should be even. Now we'll consider these bits. So bit in first position is P1, third position is 1, fifth position is 1, seventh position is 1, ninth position is 1, and 11th position is 1. So here you can count the total number of ones. 1, 2, 3, 4, 5. So total number of ones are 5, and here we are considering the even parity. So the total number of ones should be even. But here it is odd. So P1, if P1's value is 1, that implies the total data will be in an even parity, right? So the total number of ones will become 6, which is nothing but even. So that's why the P1 can be considered as 1 in order to maintain the even parity. So hope you understood. So number of ones are 5, but here we are following the even parity. In order to make this even, we can consider P1 as 1. So the value of P1 should be 1. Similarly, P2. So position at second position. So P2, third position 1, sixth position 0, seventh position is 1, 10th position is 0, 11th position is 1. See, here also you can consider the number of ones, you can count the number of ones which are nothing but odd. So in order to make this even, P2 should be 1. The value of P2 should be 1. So we can consider the P2 as 1. Right. Coming to this one, P4. Take the fourth position, that is a P4. Fifth position is a 1. Sixth position is 0. Seventh position is 1. So here you can observe the number of ones. The number of ones for finding P4 is even. So if P4 is 1, automatically the number of ones become odd number. So but here we are maintaining the even parity. So here we can consider P4 as 0 because it is already even. Similarly, consider P8. So 8th value. So 8th position is a P8. 9th position is 1. 10th position is 0. 11th position is 1. So again, here if you count the number of ones, we will get the number of ones as even. So P8 can be 0. Now the redundant bits P8, P4, P2, P1 can be 0, 0, 1 and 1. So these are the values of parity bits. So here we can replace this one P1 with a 1, P2 with 1, P4 with a 0, P8 with a 0. So this is the data we can send. This is the data we can send, right? So see. So sender finds the parity bits, the value of parity bits, and this data will be sent to the receiver, right? Now, if the receiver receives a wrong information, so this is the correct one, and if the sender sends the data as 1 0 1 0 1 1 1 0 1 1 1, so this is a 1 bit error. 1 bit error. So here instead of 0, 1 is placed. So this is the data received by the receiver. Now receiver have to identify the error and have to correct the error. Now coming to this P1, follow the same procedure. So we have to follow the even parity. That means the number of ones should be even. So follow the same procedure. The receiver also follows the same procedure in order to find out the parity bits. First bit. So the receiver also know about these parity bits, that the position of parity bits are P8, P4, P2 and P1. Right? So that means in the first position, in the second position, in the fourth position and in the 8th position are the parity bits. Now we'll check whether all the data is in even or odd. So again P1, the first position is 1, third position is 1, fifth position is 1, 7th position is 1, 9th position is 1, and finally the 11th position is 1. So total count, what is the total count of ones is 6. So this is already even parity, right? Now here P1 is equal to 0. Okay, that means there is no error. There is no error. Now coming to this P2, second bit, that is 1, third bit, it's again 1, sixth bit, it's again 1. So consider only this one, right? We have to consider only this one because this process is done at the receiver side. So receiver receives the data in this way. Okay, this is the data received by the receiver. So all these process will be done on this data, right? So the sixth position is 1, not 0. Okay, 7th position it's 1, 10th position is a 0, and 11th position it's again 1. So count the number of ones so that see here if you count the number of ones it is an odd, but we have to achieve this even parity. So there is some error. So that's why to make this even, the second one must be 1. Let us consider the second parity bit should be 1. Okay, so this is an error. In order to make this even, we have to add some 1. So P2 is equal to 1. Consider P4. So fourth position is 0, fifth position is 1, sixth position is 1, seventh position also is 1. So again the number of ones are odd. So that means the parity bit should be made 1 to make this bits as even parity. So consider P4 as 1 and consider this 8, 9, 10, 11. So 8th position it's a 0, 9th position it's 1, 10th position it's 0, 11th position it's 1. So this is already the number of ones are even, so it achieves the even parity. The P8 will be 0. Now you can consider P8, P4, P2, P1. So we have, if the data is received perfectly without any error, all these parity bits should get 0. Okay, if all the parity bits got 0, that implies the receiver receives the data without any error. Okay, there is no modification during the transmission. But here we got 2 errors. So consider this P8, P4, P2, P1. That means 0, 1, 1 and 0. So this is the Hamming code we got, right? So convert this into decimal. And we have to get the 0 if the data is received perfectly without any error. But we received the data and after calculating this one, we got the parity bits as 0, 1, 1, 0. Convert it into decimal. So the decimal number is 6. So first of all, if the parity bits got non-zero while calculating, so the receiver will identify that there is an error, right? So the next step is the receiver should correct the error, 1-bit error. So in order to do the correction, first the receiver should find the position of the error. So where, in which position the data has been interchanged. So for that we have to convert these parity bits into decimal. So we got 6. So that implies the receiver knows that the 6th bit is having some error. So we can observe that every bit is same except the sixth one, except the sixth bit. So automatically the receiver will interchange the value of the sixth bit position. Okay, the bit of the sixth position. So previous bit is 1, so the receiver will connect it with 0, such that the receiver receives the data perfectly. Right? So hope you understood this. Another example. So you can consider n number of length, but based upon that length, based upon this condition, we have to find out the position. I mean the number of bits of redundant bits. That means the parity bits. So these R value should be placed in powers of 2. So if it is having 5 bits, the power of 2 power 5 is the next one. Next 2 power 6, 2 power 7. The positions. So this will be the positions of redundant bits. Right? This you have to remember. So R will be in the powers of n. Okay, n. Powers of n. Right? So hope you understood this one. So let us stop here. So this is the error correction mechanism. So the receiver will identify the error and also correct the error. So identify, and the receiver knows about the position where the data has been interchanged, and the receiver will find out that position, and the receiver will interchange the bits. So either if it is 0, it will be changed to 1. If it is 1, it will be changed to 0. So this is how the Hamming code works. So this is, once again I am telling, so this is the mechanism for finding the 1-bit error. So identify and correction of 1-bit errors. CRC and Hamming code and some example of Hamming codes. So in this session, we'll discuss about one more important concept in computer networks, that is IP address. IP address. So what is this IP address and why we require this IP address? Right? See, why? What is this IP address means? This is the address of identity for the device. So why I am calling this device means, so it may be a computer, desktop or laptop or a tab or mobile phone, whatever it may be. So address of identity for the device. Why we require this IP address? Simple, a single word answer is communicate with other devices over network. So we have discussed about the network. Network means a collection of all the computers, right? So in order to communicate one computer with another computer, this IP address should be required. So if you consider two persons, some A and some B, so if A wants to communicate with B, A should know the address of B, right? So unless A knows the address of B, A cannot communicate with B. So if A knows the address of B, then A will start communicating with the B by sending the messages. So for example, this address is some email, right? So A wants to communicate with B through an email. So A should have an email address as well as B should have an email address. So A will send the message through email to the B. So A requires the address of B, that is email address, right? If B wants to communicate with A, B should also know the address of A, right? Address of A, that is nothing but email. Okay, so unless B knows the email of A, B cannot send the message. So in order to communicate between two persons, there must be some address, right? So in the earlier days, the communication will be through postal, right? So there will be some postal address, and if A wants to communicate with B, they will write some letters and they will use the post office, so that the message will be sent via post office through letters, right? So nowadays it's an electronic mail. So every person will be having an electronic mail, so that one person will communicate with another person by knowing the address of that particular person. That means email address of that particular person, right? Similarly, if one device wants to communicate with another device over the network, that device should have an IP, right? See, example. So we all know that if we need to know any information, the first thing we will go for with google.com, right? Google.com. So this is my system, right? This is my system, and this is the server of the Google. Right. So this is system A. Similarly, is one more system in another location which is connected. So that is system B. So if A wants to search for Python, okay, for Python material, simply A will search this Python in a Google server, right? So Google search. And if B wants to search for machine learning, if B wants to search for machine learning, again B also responds to this machine learning, right? So now the Google server will respond to the client. So it will give some Python related websites. So this should send some ML related websites. So we all know that. So if A wants to search for Python, so automatically if you write this keyword Python in the Google search, automatically we'll get some related websites. Similarly here also, if B wants to learn about machine learning and if B use this keyword machine learning in the Google search, automatically we'll get some machine learning websites. Now the question is how the Google server is sending the exact response to the particular systems. So it's a single server maintaining all the systems. So it's giving response to all the systems, right? So A is sending some Python keyword and the server should respond to that system itself. So Google should not send the machine learning websites to A and Google should not send the Python related websites to B, right? So this proper communication will be done only through the address, the unique address. So A will maintain some unique address. Similarly, B will maintain some unique address. So based upon this unique address, if A sends the Python keyword to the Google search, automatically that Google server will send the response as a Python related website to the address, unique address from where it received the request. Similarly, if B sends a request of machine learning keyword, so Google server will send these ML websites as a response to the unique address of B. So this unique address we call as IP address. This unique address is called IP address. Right? So that's why I am saying why we need this IP address means communicate with other devices over network. So it's an internet. In the internet, there will be a large number of computers, so interacting one another, right? So it will interact with the server. It will request send the request to the server, and it will get the response from the server. So every communication in the internet will be done with the help of this IP address. So I hope you understood this basic thing. Now, IP address means Internet Protocol address. Internet Protocol. So here the protocol means some set of rules to be followed. Right? So this IP address will be having in the form of four formats, four parts separated with colon. Sorry. So separated with a dot. Four parts separated with a dot, and each part will be having the numbers from 0 to 255, and this part will also be having 0 to 255. This will be also having 0 to 255. Right? 0 to 255. So what's the maximum number to represent this 255 is 8 bits. 8 bits, right? So 1 1 1 1 1 1 1 1. So this represents the decimal value 255, right? And 0 0 0 0 0 0 0 0. This represents the decimal value 0. So for every section, so there will be 4 sections. So for every section, it will be filled with one number among 0 to 255, ranging from 0 to 255. And so So we know that the system doesn't know these decimals and all these things, only it can understand the binary numbers, right? So that's why this will be again converted into 8-bit binary. 8-bit binary format. 8-bit binary format, right? And similarly, here also we will get 8-bit. Here also we will get 8-bit. Here also we will get 8-bit. So the IP address, IP address, and all these is in version 4. So there are different versions, right? So this is called IP version 4. Okay, IP version 4. So IP address in IP version 4 is the length. Okay, the length of IP address is 32 bits. Right? The length of IP address in IP version 4 is 4 sections divided with a dot, and each section is represented as a 0 to 255. So it will be represented in 8-bit format, binary format. So 8 bits, 8 bits, 8 bits, 8 bits, 4 8s, so 32 bits. Right? So it represents 32 bits. And see, from these 32 bits, how many IP addresses can be generated? So 2 power 32 IP addresses will be generated. So why I am saying this is, this IP address should be unique, right? So no two systems must have the same IP address. So if two systems are having the same IP address, automatically that data will be sending to both the systems, right? So the IP address should be unique. Okay, this IP address should be unique. It should not be shared with any other system, right? So one IP address to the one device itself. Either it may be mobile, or it may be tab, or it may be computer, or it may be laptop, right? So in the IP version 4, the IP addresses can be generated to 2 power 32 devices. 2 power 32 devices, only 2 power 32 devices. So, but nowadays we know that everyone is having a mobile phone and also the computer or a laptop or a tab. So automatically this will be a shortage of IP addresses, right? This number is obviously a shortage of IP addresses. So that's why we are moving on to the IP version 6, right? So this is all about version 4. So 8 bits will be there. Now see, so only IP version 4 can have 2 power 32 IP addresses. Okay, IP addresses. Now IP version 4, IP version 6. IP version 6. So there are 8 parts separated with dot. 1, 2, 3, 4, 5, 6, 7, 8. 8 parts separated with the dot, and every part will be fixed with hexadecimal format. Hexadecimal. So every part will be filled with hexadecimal. We know that hexadecimal are nothing but 0 to 9 and A to F. Combination of 0 to 9 and A to F, right? So hexadecimal, every column, every section will be filled with hexadecimal format. Okay, so if you convert this hexadecimal format into binary equivalent, because the system only knows about the binary formats, right? Either zeros or ones. So if this hexadecimal format is converted into binary, it must be represented using 16 bits. 16 bits. Okay, so if you observe any IP version 6 IP address, you can know the combination of numbers and alphabets with the 8 sections divided with dot, separated with a dot. So that is nothing but hexadecimal separated with a dot, and this hexadecimal is represented in 16 bits. 16 bits. So this 16 bits, total 8 into 16 bits. So this will be again 16. This is 16. This is 16. Again 16 bits. 16 bits. Right? So 8 into 16. So total length of IP in IP version 6 is 128. 128. So that from the IP version 6 we can generate 2 power 128 IP addresses. So that means we can accommodate around 2 power 128 devices. So that devices may be the mobile, laptop or desktop, as I said earlier, right? So this is the reason why we are moving from IP version 4 to IP version 6. So just one thing. So if just find out the IP address, so you can go to Google search and you can type what is my IP address, so that it will give your particular phone or a mobile, system's IP address. It will give result as your IP address, right? Which IP address you are having. So if you can observe that if it is a version 4, the 4 sections will be there, the numbers will be in between 0 to 255. And if it is IP version 6, 8 sections will be there, and each section you can find the hexadecimal formats, hexadecimal numbers. Right? So hope you understood this simple introduction to this IP address. So what is that IP address and why we are using this IP address? So every device should have an unique IP address. So in order to communicate one device to another device, that will be done only by the means of this IP address. So everything there will be having an IP address, but so whatever we are typing in this URL, see, for example, we are going with a google.com, right? www.google.com. So actually this google.com will be converted into IP address because the system does not know this Google and all these things, right? So system only knows the IP addresses. So IP addresses means IP version 4 or version 6. So every device will be having the IP address. So here a Google server will be maintained, and this Google server will be also having some IP address. So similarly, if you go with the e-commerce websites, some Flipkart.com or Amazon.com, right? So similarly, eBay.com. So for every website, there will be some IP, unique IP, right? So for an user, it is somewhat difficult to remember all these websites with the help of this IP, right? Because IP will be having 4 sections with different numerical terms, right? So it is somewhat difficult to remember this numerical IP address for the user. So we are converting this IP into some domain name. So this Flipkart is a domain name, Amazon is a domain name, eBay is a domain name, Google is a domain name. So the IP address will be converted into domain name so that we can remember the domain names. And if you enter this www.google.com, immediately that domain will be converted into IP address, and then the request will be sent to this IP address. So you can find this IP address at the bottom left of your web page. So at bottom web page of your, bottom left of your web page, here you can find the IP if you type this google.com. So whatever it may be, not only the google.com, whatever the website you are entering, so whatever the website you are typing, that particular IP address will be converted. This domain will be converted to the particular IP address, and the request will be sent to that particular IP address. Similarly, that particular IP address, that response will again send to the same IP address from which it accepts the request. Right? So here you can find this IP address. It will be a fraction of seconds. So once you find out, so you can know about these IP addresses. Right? So hope you understood this. So what is the IP address and why we are using this IP address? The only one answer for why you are using is communicating with other devices over network. Right? So in this session we have seen IP address, the length of the IP address in version 4 and version 6. So in the version 4 there is a drawback that only limited number of devices can be, IP address can be generated for the limited number of devices. So as now the number of devices are increasing a lot, so this is not sufficient to accommodate all devices. For that purpose, we are moving to the IP version 6, which is represented as a hexadecimal format in 8 sections separated with a dot. Right? So the length of the IP address in version 6 is 128. So 2 power 128 devices can be accommodated by giving the unique IP addresses. So for every device there must be one unique IP address. Either it may be a laptop or a mobile or a system, okay, desktop or a tablet. Right? So whatever it may be, there will be some unique IP address. So you can find by typing what is my IP address in Google search. So whatever device you are using, either mobile or desktop or laptop, just type what is my IP address, so it will give the IP address of your particular device. Right. So these IP addresses are divided into different classes. So categorized into different classes like class A, class B, class C, class D, and class E. So some sort of IP addresses will be come under class A, and some sort of IP addresses will be under class B, and some sort of, that means a range of a few IP addresses will be coming on class C and so on, class D and class E. Right? So now we will see which range belongs to which class. Right? So as I am saying that some range of IP addresses will be assigned to some classes. So giving the name as class A, B, and so on. Right? So there are 4 classes like class A, class B, class C, class D, and class E. So complete IP addresses will be divided into 5 classes, 5 different classes. As we know that IP address is representing the numerical format or a binary format of 4 sections. Like, so one section, colon, another section, column. There is a sequence of numbers, right? So another column and another. So 4 sections will be there. Oh, sorry, not a column, it's a dot. Right. Sorry. So section dot dot dot. So each section is ranging from 0 to 255. So everything we have discussed in the previous session, right? So this representation of this number into binary equivalent will require 8 bits, right? Similarly, here also 8 bits. Here also 8 bits, right? So all these things we have discussed in the previous section, right? So total in the IPv4 we require 32 bits. 32 bits. Now this IP address is used to identify 2 different parts. So this IP address will identify 2 different parts. One is the network ID. Another one is host ID. That means, so if there are 3 networks, okay, network 1, network 2, network 3. If there are 3 networks and each network will be having different hosts, right? These are all hosts, H1, H2, H3, H4, H1, H2, H3, H1, H2, H3, right? Now, if one packet wants to, one system wants to communicate with another system of different network, so based upon this IP address, we can know which network ID and which host ID should receive the data or receiving the data, right? So, hope you understood. IP address identifies the network ID and host ID. So the systems may be in different networks and each network will be having a several hosts, right? So in order to route this, each IP address, for every IP address there will be 2 parts. One is a network ID, another one is a host ID. So depends upon the class, the number of bits represented for network ID will be varied. So in class A, some sort of bits will be representing network ID and some sort of bits will be representing the host ID. Coming to the class B, so the number of bits to represent the network ID may be different from the class A. So that's the main difference between these different classes, all these classes. But for every class, for every IP, there will be 32 bits. So by using these 32 bits, we will represent the IP address. So this is common, right? 32 bits. In these 32 bits, a few bits will be representing network ID and a few bits representing host ID. Right. Now, hope you understood this one. Now, see. Here, see, I will give you. So this is the 4 bits. Oh, sorry, 8. Okay. As we know, this is the 8 bits, 8 bits, 8 bits, and 8 bits. Right. So in the class A, the first 8 bits represents network ID. First 8 bits. Okay. I will draw once again. So see, the first 8 bits, these are the 8 bits, right? And all the remaining bits, so out of 32, just 8 bits represent the network ID and remaining 24 bits represents host ID. Okay, so this represents the network ID. And here, in class B, bits represents network ID and 16 bits represents host ID. And in the class C, so here 24 bits represents the network ID and only 8 bits represents the host ID. Right? So class A represents, 8 bits in the class A, 8 bits of the IP address will be representing the network ID and 24 bits of the IP address will be representing the host ID. Similarly, in the class B, 16 bits of IP address will be the representing the network ID and the remaining 16 bits will representing the host ID. Similarly, here 24 bits. Class C, 24 bits will be representing the network ID and 8 bits representing the host ID. And class D is completely meant for multicasting. Right? So in further sessions, you will know about this multicasting and all these things. Don't worry. So class D is completely for multicasting and class E is completely for research. Research and experiments. So class E, completely for research and experiments. So reserved. So these IP addresses are reserved. Okay. So this is how we can classify the IP version 4 IP addresses into different classes. Now we'll see. So how many? So we know that the IP addresses will be starting from 0.0.0.0 to 255.255.255.255. So this is the complete IP version 4 IP addresses. Right? The IP version 4 IP addresses are starting from 0.0.0.0 to 255.255.255.255. So among all these IP addresses, a few IP addresses, a range of few IP addresses will be belong to class A, and some range of IP addresses will be belongs to class B, and some range of IP addresses will be belong to class C as well as the class D and class E. Right. See how we can identify these classes. So which IP addresses belongs to this class A or class B, class D. Just one thing you have to remember. So class A, for the class A, the leading bits will be 0. So that means the leftmost bit, right, most significant bit should be 0. And all the remaining bits should be occupied by further IP addresses. So we'll see class by class. Okay, first we'll go with the class A. We'll go with the class A. Right. So in the 8 bits, the leading bit will be 0. The leading bit must be 0. That means, so we can say that 0, 0, 0, 0, 0, 0, 0, 0 dot 0, 0, 0, 0, 0, 0, 0, 0 dot, again 0, 0, 0, 0, 0, 0, 0, 0 dot 0, 0, 0, 0, 0, 0, 0, 0 dot. 8 bits, 8 bits, 8 bits and 8 bits. Right? So 2, this is the starting address. Okay, this is the starting address. Now the last one, right? The last ending address is, so the leading bit should be 0, so that's why 0, 1, 1, 1, 1, 1, 1, 1 dot, okay, 0, 0, 0, 0 dot, sorry, right, the range, this is the range of IP addresses. Okay, so what's the value of this one? So 1, 2, 4, 8, 16, 32 and 64. Right? You can add all these things. So 1 plus 2, 3, 7, 15, 31, 63, 63 and 127. So the value of this one is 127. Right? So the range of class A are 0.0.0.0 to 127.0.0.0. Right? So that means 0 to 127 is the range of IP addresses belongs to this class A. Okay, hope you understood this one. So the leading bit should be 0 in class A. The leading should be 0 in class A, so the leading bit is this one, all the remaining 7 bits. So whatever the 7 bits are there, that 7 bits represents the network ID. Okay, so we are seeing that first 8 bits belongs to network ID and the next 24 bits belongs to host ID. So in that network ID, the first bit should be 0. The leading bit will be 0 in class A. So that's why, so all the remaining 8 bits, all the remaining 7 bits of the first octant. So we'll call this as octant, right? Octant. The first octant, second octant, third and fourth. So here in the first octant, the leading bit, except the leading bit, all the remaining 7 bits represent the network ID. right? So hope you understood this one. So how many number of hosts, I mean sub networks can be created? Number of subnets or subnetworks. So there are 7 bits, so 2 power 7, and number of hosts. So number of hosts. So what are the bits remaining? 24. So 2 power 24. So from class A, the number of subnets can be created as a 2 power 7, and number of hosts can be 2 power 24. Subnets means nothing but networks, different networks. So there can be 2 power 7 different networks, and among those 2 power 7 networks, so we can accommodate 2 power 24 hosts. The IP addresses can be accommodated for 2 power 24 hosts. And this is the range. This is the range. So this is all about a class A. So this is very important, 0. So 1 bit for leading bit, class A representation, and all the remaining 7 bits for host representation. So 7 bits for host. 7 bits for host. Right? So hope you understood this one. Next. So class A 0 to 127. Next, similarly, class B. Again, class B consists of, so here the leading bits are 1 0, 2 bits. That means 2 bits. So as we have discussed just now, 16 bits are for network ID and 16 bits for host ID. So 2 bits, 1 0, host ID, sorry, so network ID, okay. Network ID, host ID. Right? So this is 14 bits and this is 16 bits. 14 bits and 16 bits. So the number of subnets or subnetworks will be 2 power 14 and the number of hosts will be 2 power 16. Right? And here the range is from, so we know that we have stopped at 127, so here it must be 128. Okay, so here it will be 128. The range is from 128 to 128 to, so how many bits we have to represent here? See, that means 10000 dot. So we have to fill all the 4 octants with 8 bits, right? So this is nothing but 128. Okay, 128. So it's 1, 2, 4, 8, 16, 32, 64, 128. So 128. So first 2 bits should be 10. 2. Here you can observe 10, 1, 1, 1, 1, 1, 1 dot. See this one. So you can observe, you can add all these things. So see here, so 1 plus 2, so total 1 plus 2 3, 3 plus 4 7, 7 plus 8 15, 31, 60, 31 63, 63 plus 28. So 191. Okay, so total 191. Right? So the range of these IP addresses are from 128 to 191. The IP addresses ranging from 128 to 121, 191 will be belongs to host this class B. For example, like see 129 dot some 199.0.10.5. So this is the IP address. If you consider this IP address, so this belongs to automatically class B because 129 is in between the range 128 to 191. So this belongs to class B. Right? So hope you understood this one. Next. Similarly, class C, and in class C, the leading bits will be 3, so 1, 1 and 0. The leading bits will be 3. Right? So here we know that in the class C, so there are 3 octants are for network ID. That means 24 bits will be for network ID and host will be for only 8 bits. Similarly, this is for 8 bits and this is 11124. So total 21 bits will be used for network ID. 21 bits. So subnets will be 2 power 21 different networks and different hosts for each network can be 2 power 8. Right? And here it will be 128 to 191. So this is A, this is B. Now coming to the C, class C again. So 191. That means 1. So it should start with 191, right? So 192. So 1, 1, 0, 1. Dot. See, this is the starting edit. So this is nothing but 191. So it's 1, 2, 4, 8, 16, 32, 64 and 128. So you can observe this is 192. Okay. 192 2. So first 3 bits should be 110. So 110 and all the remaining bits can be 1. So for getting the maximum, right? See. Okay. See. So if you count this one, right. So if you count this one, 128 plus 64, it's 192. 192 plus 16. Okay, 192 plus. So you can add all these things. 1 plus 2, 3 plus 4, 7, 15. 15 plus 16, so 31. So 192 plus 31, which is nothing but 223. It's nothing but 223. So just don't mug up the ranges, right? So you can find these ranges in the system. So don't mug up. So this is the logic why we are writing these ranges, right? So the leading bits will be 110. So maximum it should be 110 and all should be 1 in the first octant. So that's why it's 223. It becomes 223. That's the end of the IP address in this class C. So it is 1223. Okay. So hope you understood this one. So the range of IP addresses are 192 to, so this is 192, 223. So this is the range of class C. Right? So hope you understood this one. Next. Next one, class D. So next one is a class D. So there should be the leading bits 1110. 1110. Okay, 1110 and everything will be some network ID. Network ID. So here you can observe in this class C the leading bits. In order to find the range of IP addresses, the leading bits will be 1110. So 1110 means where we have to stop? It's 223, right? So 224. We have to start from 224. So 224 means 1110 0000 dot and all the remaining zeros. Okay. Right. So this is nothing but 224. So you can observe 128, 64, and 32. So 64 plus 32 is 96. So 128 plus 96. So it's nothing but 4. So 2 and 1, 224. So this is nothing but a 224. So the starting address of class D. This is not a C, it's a D. Okay. 2. So the leading should be this one. So 1110, 1111 dot all the remaining zeros. So you can observe here. So this is nothing but 224 and this is 8421. That means 12, 14, 15. So 15. So 239. So the value of this one is 239. 239. So the range of D, IP address range of D is 224 to 239. Right? 224 to 239. And obviously the remaining, the next one will be E, which starts from 240 to end 255. That means, see, if you consider E, the leading bits will be 4 bits and it's all ones. So you can observe here. So 224 plus 16, so 240, right? So here the leading bits will be all ones. The leading bits will be all ones for the starting address. So the total count of all this, that means 128 plus 64 plus 32 plus 16, which is nothing but 240. And the final address is this one. That's completely 255. So the range of E, the class E, will be 240 to 255. Right? So this is a procedure. So why we are getting these ranges? The complete depends upon the leading bits. Right? So every IP address is divided into two parts. Some sort of bits will be identifying the network ID, and some sort of bits will be representing the host ID. Right? Coming to the class A, class B, class C, there are some sort of bits for identifying the both the network ID and the host ID. Coming to the class D, that is completely depends on multicasting. That's completely useful for multicasting purpose. And the class E, whatever the range of IP addresses comes under this class E, all these will be under reserved purpose. Those are used only for research oriented and experimental oriented. Right? So hope you understood this one. See, class A, B, C, D, E. Leading bits 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. Range of IP address. That is 0 to 127, 128 to 191. 192 to 223, 224 to 239, and remaining 240 to 255. And here 7 bits for network ID and remaining 24 bits for host ID. Here, so 10, that means 14, so 14 will be for network ID and 16 for host ID. And here, see, 3. So total 24 for network ID, 3 here, so 21 for network ID and 8 for host ID. And this is completely for multicasting, right? And this is completely for research and experimental purpose. Right? So this is how we can differentiate the IP addresses, or we can classify the IP addresses to different classes. So class A, class B, class C, class D, and class E. Right? Right. So the name itself indicates a subnet, means subnetworks. So it's a worldwide net, so there will be a lot of subnetworks, and each and every network will be having different hosts. Okay, so in the internet, so we can have a lot of networks. Okay, some LAN. Right. So in each network there are different hosts. So these are hosts. So again, LAN 2. Again, it will be having different hosts. Okay. And LAN 3, different hosts. LAN 4, different. Right? So this network is called subnet. Okay? So our IP address, as in the previous session, I have discussed that in the IP address, it covers the two concepts. One is network address and host address. Right? So, as we have discussed in the previous session, that IP address is an unique identifier for any computer or any device. Okay? So, that device, that address consists of both the network address, that means which network, okay, the packet or the data should be transferred to which network, and in that network we can have a lot of hosts, right? So, the data should be sent to particular host. So that's why IP address, in the IP address, it covers both the network address as well as the host address. So based upon the class of IP address, there are different network addresses and host addresses, right? So See, so as we have discussed, so class A, if the IP address of a class A will be having the first 8 bits as a network address, network ID, okay, simply we can say network ID, and the remaining 24 bits. So total length of any IP address will be 32 bits, right? So 4 sections, the 32 bit will be divided into 4 sections, so each one is having 8 bits. So 4 octants, we can call them as an octants. So here 8 bits represents the first octant, and the second 8 bits represents the second octant, and the next 8 bits represent the third octant, and the last 8 bits represents the fourth octant. So class A IP addresses, so whatever the IP addresses comes under this class A, those class A IP addresses will be having 8 bits as a network ID and 24 bits as the host ID. Right? Similarly, class B. So in the class B, 2 octants, the first 2 octants will be considered as a network ID, and the last 2 octants will be considered as a, it will be used for host ID. So 16 bits represents the network ID, and 16 bits represents the host ID. Right? So 8 bits represents the network ID and 24 bits for host ID. So that's a class A, and the class B, 16 bits for network ID and 16 bits for host ID. And coming to the class C, so whatever the IP addresses comes under this class C, so first 3 octants, that means the 24 bits are used to represent the network ID, and the remaining 8 bits represents the host ID. Okay, so we know that the complete 4 sections, so the minimum value for each octant is 0. Okay, so right here, so each octant minimum value is 0, maximum value is 255. So that means it will be represented in 8 bits, so 0, 0, 0 and 0, 0, 0, 0. So this is nothing but 0 decimal value, and all ones which represents the 255. So total 266 numbers, right? So coming to this one, so class A, okay, consists of 8 bits for network ID, 24 bits for host ID. Now, what is meant by subnet mask means, so making network bits as 1 and host bits, the bits represented for host, as zeros. Simple. So coming to this one, what is the thing? Class A consists of 8 bits for network ID, the first octant. So the first octant will be having 8 ones. Okay, and all the remaining 24 bits will be zeros. Right. So this implies what's the maximum value here? 255. So 255.0.0.0. So this is the subnet mask for the IP address comes under class A. And coming to the class B, the 16 bits for network ID. So in order to find the subnet mask for this class B IP addresses, so make all the network bits ones and host bits as zeros. So first 16 bits will be 1. Okay, so dot. So last 2 octants will be zeros. So here you can observe the maximum value for this one is 255, right? So 255.255.0.0. So this is the subnet mask for the IP addresses comes under class B. Coming to the class C. So here the class C, 24 bits are network ID and 8 bits for host ID. Again, if you want to calculate the subnet mask for this class C IP address, so just make all the network bits as 1s and host bits as 0. So network bits, so here 24 bits, that means 3 octants will be having maximum. So the first octant will fill with all 1s, dot second octant will fill with all 1s, dot third octant will also be filled with all 1s because 3 octants represents the network ID. And the fourth octant, zeros. 4 octants, it will be zeros, right? So the maximum value will be, so 255.255.255.0. So this is the subnet mask for the IP addresses comes under class C. Okay, so this is completely for each class there will be, total, see, the first and last IP addresses will be kept on hold, and all the remaining IP addresses can be allocated to the host. That means the 0th IP address represents network, and the last one, that is 255. 255 is represent for, it will be kept on hold for broadcasting. So these two should not be used for allocating the IP address per host. So total 266. So we are taking two IP addresses. So those are the first address and the last address. The first address represents the network, and the last address represents the broadcast. So that last address will be used for broadcast. So we should not allocate these IP addresses for any other host, right? So we can allocate only 256. Okay. So 254. Allocate the 254 hosts. This you have to remember. In every class, the first ID represents the network, and the last ID represents, the last ID will be kept on hold for the host, broadcast. Right? So hope you understood this one. How to get this subnet mask. Right? So in order to get the network ID, okay, in order to get the network ID or host ID, so in order to get the network ID, consider the IP address and make sure that of which class it depends, and apply the subnet mask and apply the end operation between the IP address, given IP address, and the subnet mask. It gives the network ID. So let us explain with an example. Right, now let us take one example IP address and we'll find the network ID for that particular IP address. Right. So first let us write here the range of classes of IP address. So 1 to 127 comes under class A. So class B it will be 128 to 191, and coming to the class C it will be 192 to 223, and the remaining class D and E. So class D is used for multicasting, and class E is for completely research and experimental purpose. So don't go over all those things, just we'll write the differences of class only A, B and C. Now let us take an IP address. We'll take an IP address example. So that is some 192.10.5.5. Okay. Let us say 192.10.15.5. So this is an IP address. Now, first of all, we have to convert this into binary. Okay. So before that, we'll write the subnet mask. So here we can see that 192. So 192 comes under class C. So if it is a class C, we know that the first three octants will be used for finding the network address. So the subnet mask for class 3 is 255.255.255.0. Right? Now we have to find the network ID for the given IP address. So here you can first binary format, in the binary format, convert it to binary format. So let us write here. So 128, 64, 32, 16, 8, 4, 2, 1. So in order to convert this 192, this bit should be 1, and 180 and 192. This should be 1. Okay, 128, 64. 128 plus 64. That's nothing but 192. Okay, so all the remaining bits will be 0. This is 192. Okay, so 110000 dot 10. 10 means, see, this all should be zeros and except 8 and 2. So 10. So you can write here 00001010 dot 15. So again 15 means, see, 8 plus 4, 12, 4 plus 2, 14 plus 1, 15. Right? So hope you understood. Okay, except this one. So 00001111 is nothing but 15. Right? And next 5. 5 means again 4 and 1 should be 1. See, 0101. So this is the binary equivalent for the given IP address. Now take the subnet mask. The binary of subnet mask. So it is all ones for all the 3 octants. Dot. See. And the last one will be zeros. So in order to get the network ID, we have to perform the AND operation between the IP and subnet mask. Right? So we have to perform the AND operation between the IP address and the subnet mask. It will give the network address or network ID. See, we know that AND operation means if both the bits are true, then only it will come true. So here we will get 1, 1, and all the zeros. Okay, here also the same thing, except the last octant, the complete first 3 octants will be same for the IP address. So here also we'll get all zeros and all ones, but here we'll get all zeros. Right? So this is the network ID. Network ID to which the host belongs. Okay, to which the host belongs. So here you can observe the binary the decimal equivalent of this one is 192 dot. This is 10.15.0. So this is the network ID of given IP address. So this is how we can find out the network ID. So even some bits, I mean, as we have discussed in the previous sessions, that first octant will be, I mean, coming to this class C. Let us take the class C. So in that we have discussed that first 3 octants will be representing the network ID, and the last octant represents the host ID, right? So even though the 8 bits represents the host ID, in that if the IP address or if the network divided into subnets, different subnets, that means large organization will be having a different subnets, right? So in order to divide the complete network into different subnets, some portion of the host IDs will be acting as a network ID. Okay, in such cases. So in order to get the subnetting, some part of the host ID bits will also get represented to the network ID bits, right? So finally, whatever the thing, we have to do the AND operation between the IP address and the subnet mask, right? So here you will get the address of network ID. So this IP address belongs to this network. This IP address belongs to this network. And in this network, so 0 represents the network address, and the last IP address, that means 192.10.15.255. So this is the network address. And this one, the last one, will be for broadcasting. If you want to broadcast any messages, so broadcasting, the last address will be given. So only we can accommodate 254 hosts. 254 hosts. The protocols. So we'll be using these protocols in the networking, but in this session we'll see what exactly these protocols, what is the importance of these protocols, and what will we do with these protocols, right? And these protocols are defined as a set of rules established for formatting or processing the data. So coming to the network, if a group of computers are connected to a network, so some sort of data will be transferred, right? And some sort of resources will be shared among the different systems. And all these networking functions will be processed smoothly with the help of these protocols. Right? So protocols are a set of rules that are established to process data. For example, so data sharing, that means one computer can share the data with another computer. So both the networks may be different or same. That means 2 computers, that means 2 devices which share the data may be of a same network or different networks. So each computer will be using their own softwares and their own hardwares. Even though the data will be processed efficiently, that is done with the help of these protocols. So different protocols will be used for different processes. There are a lot of protocols. For each process, the different protocol will be used. Now we'll see what are the different types of protocols and where exactly these protocols will be used. How the data, which kind of data will be exchanged, which kind of data will be communicated or processed, right? So coming to the first one. The first one, ARP, so which stands for Address Resolution Protocol, and this, the name itself indicates, it gives the address mapping, okay, in the network. So how can one system shares the information with the another, how one system communicates with the another, So with the help of some IP address and the MAC address. So the IP address and MAC address, right? So this identifies the network and this identifies the system. So this sort of mapping of IP address with the MAC address will be done with the help of this address resolution protocol, and this ARP will maintain a table with all the MAC addresses, right? So it maps the IP address and the corresponding MAC address so that the packets will be transferred to that particular network, right? And this mapping is the responsible of this particular address resolution protocol, right? Second one, SLIP stands for Serial Line Internet Protocol. So this serial line internet protocol, so we have discussed in the computer networks that the data will be transferred with the help of a packets in the form of packets, right? So the grouping of characters to form a packet will be done by this serial line protocol. So the group of characters, a sequence of characters will be forming a packet. To form a packet will be done with the help of this serial line protocol. Okay, serial line internet protocol. Next, IP version 4. It's nothing but internet protocol. Internet protocol. So this we will use this one. I think many of you were aware about this internet protocol. So how the packets means the data which we are communicating, right? So the packets or the data should be communicated from one system to another system. So that should be routed. Okay, so that should be routed. So the complete routing of a packet to the destination from source will be done by this internet protocol, right? So here it will be done a routing. A routing will be done. So here packet forming, and here mapping IP to MAC, right? So routing will be done with the help of this internet protocol. And this is version 4, okay? And the next one is IP version 6. This is the latest version. So updated of version 4. So what is this updation? What is this updation? The IP length will be increased from 32 bit to 128 bit, so that more number of addressing will be done, and the data will be routed efficiently than IP version 4. That was the updation, right? So more number of addressing will be done because the IP length will be increased from 32 bit to 128 bit, right? And in order to routing the packets, this IP protocol, I mean internet protocol, will be done, and with the help of another protocol called TCP, the data packets will be delivered to the destination address. So that's why we call them as a TCP IP. So the combination of both these protocols, transmission control and the internet protocol, the data or the packets will be routed to the destination, right? Next, ICMP, Internet Control Message Protocol. See, this will be used by the network devices which will give the error messages. So during the transmission, if there is any errors or any congestion, that sort of information will be communicated with the help of this ICMP. So network devices will send error messages or any conditions, right? So whatever the thing, so that will be communicated with the help of this Internet Control Message Protocol. Internet Control Message Protocol. Next, TCP, Transmission Control Protocol. So here the name itself indicates transmission, the packets. So this is responsible for transmitting the packets from source to destination, and with the combination of internet protocol, the packets will be routed to the destination, right? So with the help of acknowledgement, so the error checking will be done here. The error checking will be done, and if there are any errors and if the packets are not delivered at the destination, So this TCP will retransmit the data, retransmit the packet to the destination. So also the TCP retransmits the lost packets. So in our previous session we have discussed about these packets, right? So in that we have seen there will be some sort of disturbance, and due to that disturbance some sort of packets will be lost. So lost means the packets were not delivered at the destination. So in such case this TCP is responsible to find the acknowledgement and to find the error, and it is feasible to retransmit the lost packets. So whatever the packets lost, that will be retransmitted with the TCP protocol, and with the combination of TCP IP the packets will be delivered to the destination. And this is also called as a connection oriented protocol. Connection oriented. So before before transmitting the packets, there should be a connection between the client, the two devices. Okay, so which we want to communicate. So the data should first, the connection should be established, and once the connection is established, then the packets will be transferred from source to destination. So that's why we call it as a connection oriented protocol. TCP is also called as a connection oriented protocol, transmission control protocol. And the next one, UDP, is called a user datagram protocol. And similar to this TCP, so this is a connectionless protocol. And this is also used to transmit the packets from source to destination, but no reliability. There is no reliability. Okay, and no error checking. Obviously, no retransmission of data. So data or packets, right? So this is just to send the packets from source to destination. So it doesn't observe or doesn't have any error checking that whether the packets have been received at the destination or not. So that's why there is no concept of retransmission of lost packets, right? So this is no reliability. There is no reliability when compared to the TCP. And the next one, RPC, remote procedure call, and this is used to communicate between the remote device. Okay, one system can communicate with another device. Okay, so connect with another remote device. Okay, this is used to connect with another device. And the next one, so DHCP, dynamic host configuration protocol. And here the name itself indicates this is used to distribute the IP addresses among the systems over a network. So if any one of the system is included in the network, then assignment or assigning a new IP address to the newly added system will be done with the help of this protocol called dynamic host configuration protocol. So this is responsible for distributing IP addresses to newly added system in network. So many systems will be added, keep on adding the systems to a network, right? So if one system is added to a network, then some new IP address should be assigned, and that will be done with the help of this DHCP, dynamic host control configuration protocol. Next, DNS, domain name system protocol. So we know that, so if you are observing some client server, so the client will send the request and the server will give the response. One example is just accessing a website. So for example, if you want to communicate or if you want to search anything in the Google, so the first step we are doing is opening the browser and in the address bar we are typing just www.google.com. So immediately the request will be sent to the server, and the server will give the response by loading the home page in our client, that means in our system. But here a system, the server will also be identified with the help of IP address only, but we are just communicating with the help of URL, right? So in order to remember all the IP address, that is difficult, so we are just making it easier by remembering the URLs, that means the host names. So whenever you just type the URL like google.com, the first step happens is that google.com will be converted to the numerical IP address, corresponding numerical IP address, and automatically the packets will be sent to that particular IP address. Okay, so in our networking, two systems will be communicated only through the IP address, the numerical IP address. So but here we are just giving the host name, that means URL. So that will be first converted into IP address, and to that particular IP address the data packets will be transferred. So that will be done with the help of this DNS, domain name system. So conversion of URL to IP address, that's it, domain name system protocol, domain name system protocol, right? The next, FTP, which is a file transfer protocol, and this, the name itself indicates, in order to transfer the files, that means a file sharing, will use this file transfer protocol. So this will be for file sharing between the host, or device or computer, whatever it may be. So in order to share the files, okay, this FTP protocol, that means a file transfer protocol, will be used. And next, HTTP stands for Hypertext Transfer Protocol. So Hypertext Transfer Protocol is used to communicate between the client and server. So just we have seen, right? So just we have explained about this one DNS, right? So if you want to access any group, any web server, so we need to access with the help of URL, so that the URL will be converted into IP address, and this communication will be done with the help of this HTTP. So you can observe, if you just give google.com in the address bar, automatically it will start with this HTTP or HTTPS. So this hypertext transfer protocol, this is used to connect client with server. So you can imagine the client as a browser, server as a web server, right? And this is also known as request and response protocol, because the client sends the request and server gives the response. So that's why we call it as request response protocol. So this is used to connect or sending data in World Wide Web. www is the World Wide Web, right? So for that we are using this hypertext transfer protocol. And there's one more variation in this HTTP, that is a HTTPS. That's nothing but secure. So the data which we are sending in the World Wide Web, that means the communication what is going to be done between client and server, that will be in the encryption format. So that means the data will be giving security. So that we call it as a HTTPS. So this also we will observe in the web browser. If you are communicating with any other website, any website, not only the Google, if you go with any website, you can observe this one, right? For example, going to the Google, it will come like this, HTTPS : / so like this we will get, right? So that means some sort of data we are communicating to the World Wide Web. Okay, so that is a HTTP and HTTPS. Next, IMAP, which is an Internet Message Access Protocol. Internet Message Access Protocol, and this is an email protocol. So all of us are using the email service, right? So this is a one email protocol, one of the email protocol, and this is used to access or manipulate emails, the emails, right? So this is used to retrieve emails from mail server, right? So the Google will be having some mail server. Similarly, Yahoo will be having some mail server, right? So like that, there will be different mail servers. From that mail servers, in order to retrieve these emails, we'll use this Internet Message Access Protocol. So this is one type of email protocol. And the next one, see, these are all different types of protocols which are being used for different kinds of processes, right? POP. This is called as a post office protocol. This is also an email protocol, another email protocol. So this will also be used in a mailing purpose, and here it will enable user to download the emails from mail server to client, so that next time if the client wants to read the emails, it need not be in the internet connection, right? So offline mode, we can read the emails in the offline mode. So it enables the user to download the emails from the mail server to the client, email client, right? So for that we are going to use this. This protocol will be used, post office protocol. This is also another email protocol, two email protocols, IMAP and POP. Next, SMTP, simple mail transfer protocol, and this is also one more email protocol. This is also another email protocol, and this protocol is used to transfer the emails from one user to another. So this is used to transfer emails from one user to another. So here the previous two protocols, that means IMAP and POP, are used to retrieve the protocols, but this SMTP is used to send the protocols. Okay, so here you can see IMAP and POP, they are used to retrieve emails from the email server, and whereas SMTP is used to transfer email, retrieving and transfer. Right? So these are the three different email protocols. And the next one, telnet, and this telnet is used to communicate or connect the remote devices. So with one device with another device with the help of some IP address or host name. So this telnet enables the admin to connect with any remote device with IP or host name. So mainly this will be used to share the data from one system to another system, right? So with the help of IP address or the host name, the two systems can be connected, two different remote devices can be connected, and once there is a connection, automatically the data can be transferred, right? Next, the next one, SNMP, stands for Simple Network Managing Protocol, and this will also be used by the admins. So it enables the admin to monitor the network performance. So in order to monitor the network performance or managing the nodes, so whatever the nodes that are available, nodes is nothing but a device, right? So managing the nodes also, this protocol will be used. SNMP, Simple Network Managing Protocol, Simple Network Managing Protocol, right? So these are the different protocols that are used in networking to process the data. So in all these protocols you can observe some sort of data is processing, right? So without the protocols, the networking functions will not be possible, right? So any function, anything, if you want to work with the network, then obviously there should be a protocol, discuss about one more topic, that is understanding about the packets in networking. So coming to the networking, so the data will be transferred between two different devices. So that means the data will be transferred in terms of packets. So in this session, we'll see what exactly these packets and what will be available in the packets, right? So packets. So very important concept in networking, right? And this will be also be used in ethical hacking also, right? So if you consider two systems which are connected in a network, so this is system and this is another system. So it will be system A and system B. So there are two different systems and we are supposed to exchange the data between A and B. So let it be, this is the bandwidth. So the data will be transferred from A to B through the bandwidth. And for example, if A wants to send the data which is more than the available bandwidth, then what happens? So here the data will be divided into a small parts called packets, right? So for example, some So for example, some 100 bytes of data is to be transferred from A to B and the bandwidth is only 50 bytes. Okay, the bandwidth is only 50 bytes. So it's somewhat difficult to send 100 bytes at a time. So what happens here? So this will be divided into different smaller parts. So let it be, I'm giving a small example. So let it be 4 parts. Okay, 25 bytes, 25 bytes, 25 bytes and 25 bytes. So these small parts, these small units of data is known as packet, so that the transfer will be fast and it will be reliable, right? Instead of sending the complete information at a time, so it will be very easy and efficient if you divide the complete data into smaller units. So that means in terms of packets, right? So packet means a small unit of data, Now let it be, so this is one packet, this is one, this is one and this is one. So total 4 packets are available now. So each packet size is 25. So what exactly will be in the packet? So this packet represents the two things. One is header and the second one payload. So payload is actual data. Okay, whatever the bytes we are using, that will be the payload. Okay, the actual data which we want to transfer from A to B is called a payload. Coming to the header, so the packet should be transferred from A to B, right? So that means this packet should have the destination address. So unless you have the destination address, the packet can't be transmitted, right? So if you want to send an email, so what we need, the recipient email ID should be there. So without the recipient email ID, you can't send a message. So if you want to send a post, so there should be some postal address, the recipient postal address. Similarly, there should be the destination address, so that the packet will be transmitted from source to destination. So both the things will be included in this header, right? So one thing is source address from where the packet has been transmitted and the destination address. So here the address means identification of that particular device. So we can call it as an IP address, source IP and the destination IP. So in between there will be different routers which will route the packet to the destination, towards the destination. Right, so that in order to route the packet, we'll apply some routing algorithms. So already we have discussed about some of the routing algorithms in our computer networks playlist. So I'll post that one in the description section. You can go through that one. So the packet will be having the header and payload. In the header, we'll be having the source address, destination address. And one more important thing is the length of the data. So whether the data has been modified in the transmission or not. So we have to check. So that will be added here. Length. The length of data will also be included in the header, right? So I'll write this payload once again. The 3 things. And the 4th one, the timestamp, the time when the payload has been created, when the packet has been created, right? So timestamp. So the packet will be valid only up to that particular time, right? So up to that particular time, the packet will be valid. So if the time exceeds, automatically the packet will be destroyed. It will not be used. Okay, so within that particular time, the destination should receive this particular packet. So if it receives the packet where the time has been exceeded, automatically that implies that packet has been destroyed, right? So timestamp is important. So within that particular time period, the packet should be received. And next very important thing is sequence number, identity, or we can call it as a sequence number. So what is the use of this sequence number? So here we have divided the complete data into 4 packets, right? So these 4 packets will be sent here. These 4 packets will be sent to here, right? So imagine these 4 packets as a 4 different vehicles, okay, 4 different cars or 4 different bikes. So this is a bandwidth, it's nothing but a road, okay, it's nothing but a road. So at a time 2 packets can be traveled here, or 3 packets can be traveled based upon the bandwidth. So here we have given some 50, so at a time 2 packets can be traveled at a time, right? So we don't know which packet receives, which packet will reach the destination first. Okay, for example, this is 2, this is 1, this is 4, and this is the 3. Maybe the 3rd packet has been received first, next 4th packet has been received second, and 1st packet has been received third, and 2nd packet has been received last. Okay, so we don't know the order. So what happens? The destination, yes, the destination have received all the 4 packets, but the destination should reassemble the data. Okay, reassemble the packets. So which comes first, which comes next, and which comes the 3rd, and which comes the 4th, like that. So in order to reassemble the data at the destination, for every packet there will be a sequence number. So according to that sequence number, the destination will rearrange the packets. Okay, so even though the packets received in this order, so for example 3rd, 4th, 1 and 2, so this will be reassembled as 1, 2, 3 and 4. So for the reassembling of data, the sequence number will be used. So that is most important. And also, so sometimes due to some congestion, network congestion, or some failures, the packets may be lost. Okay, the packets may be lost. So if the packet is lost, for example, if the packet 1 is lost, okay, the 1 has not reached the destination. The 1 has not reached the destination. So we are having only 3 packets at the destination. So what happens here? So there should be one acknowledgement from B to A, such that we have received so and so packets. So based upon that acknowledgement, if A doesn't receive any acknowledgement from B, that implies that the corresponding packet has not been reached to the destination. So in such cases, the B expects the retransmission of the packet, and that retransmission of the packet will be taken care by the protocols. So the protocol will make sure that all the packets has been received by the destination. If any one of the packet has been lost, automatically the retransmission will be initiated. So the packets will be retransmitted to the destination, right? So this is how packets can be transmitted from source to destination. So apart from this, there are 7 more fields. Okay, there are 7 more fields. Okay, also there will be checksum, header checksum. This is called a header checksum. If any one of the data has been lost, automatically based upon this checksum, the correction will be done. Okay, checksum, okay, length, and a lot of information will be there. So these are the major things. I have covered only the major things that are included in the packet header. Okay, and the second part is payload. Payload means actual data, and there is also a third part which is a trailer. Okay, header and a trailer. Trailer consists of a checksum, so which corrects the data if any modification is there. Okay, so that will not be available for the TCP/IP protocols. So the majorly packet will be having only 2 parts, that is a header, packet header, and the payload, right? So this is how the packets will be transferred from A to B. So every packet will be having the sequence numbers, so in order to reassemble or reassign at the destination, right? If any one of the packet has been lost during the transmission, the protocol will initiate the retransmission of that particular packet, and if any packet is received by the destination beyond the timestamp, okay, so automatically then also it will expect the retransmission of the same packet. Okay, so the packet loss will be due to some network damage or any network congestions, okay, network traffic, etc., etc. There will be many reasons why the packet has been lost, right? So this is the overview of the packet. So this is most important. So if your system is connected to a network, so here the data transmission will be done with the help of a packet itself. So what is the data transmission? For example, this is a client. Just for an example, I am saying this is a server. Let it be, this is a Google server. So if a client gives some www.google.com, automatically some sort of data, so data means this URL or anything else, right? So whatever the request we are sending from the client, that we call as a data, that will be sent to Google server, okay, as a request, and server will give a response to the client by loading this Google home page to the client. Okay, so immediately if you are giving www.google.com, we are getting the home page. So that actually that home page will be available in the Google server. So once you send the request, the Google server will load the home page into the client system based upon the IP address, right? So some sort of data will be communicated from the client to a server. So that data will be transmitted with the help of this packet in the form of packets, right? So hope you understood this packets information. So what is a packet and how these packets will be transmitted from A to B, that means two different devices, right? So this will also be useful in our ethical hacking, right? So there is a tool called Wireshark, so which will be acting as a packet sniffer, packet analyzer, how the packets or what are the packets transmitted from source to destination. So I'll explain that tool in our further sessions. So there you can see all these things. So what is a packet? What is the sequence number of the packet? What is the timestamp? What is the length of the packet? What is the source address? What is the destination address? Everything you can find in that particular tool, Wireshark. Okay, and this is a one popular tool that will be used by the ethical hackers. Routing. So routing means we know that in a network the packet should be sent to destination, right? From source to destination. So this is a packet, right? This packet should be transmitted to the destination from the source, right? So in which path the packet should be transmitted? In which path the packet should be transmitted to reach the destination? Right? This is called a routing. Okay, routing. So there may be a number of possible paths available here, but which path we are going to select for to send this packet to the destination? That is the main goal of this routing. So there are a number of routing algorithms are there. Before going to the routing algorithms, we'll see how many ways these routing algorithms have been classified. So these routing algorithms are classified in different ways. The first one is non-adaptive routing algorithms. See, here non-adaptive routing algorithms means this is also called as a static routing algorithms. So also called as static routing. So now we'll see what is meant by this static routing. Static routing means, so the routing process will be designed in advance. So before starting the routing algorithm, the routing process, so the way it reaches to the destination will be set in advance, and all the routing process will be stored in routers when the boot completes. So immediately whenever the booting completes, then only the routing process will be stored in the routers. So blindly the routers will follow this routing process. So in between the transmission, the routers will not change their routing process. So from one computer to another computer, so all the complete routing process will be designed in advance, and blindly we have to follow that routing process. So this is all about this non-adaptive routing. So it doesn't affect with change in network topology and traffic. So whenever the network topology is changed or any traffic changes, that that impact will not be done on this routing process, particularly non-adaptive routing algorithm. Right? So this is all about this non-adaptive routing algorithm. Now the second one is, see here again this non-adaptive routing algorithm is classified in two ways. So classified in two ways. So first one is flooding. Right. So flooding means all the incoming packets will be transmitted to all the outgoing links. Right. So incoming packets. So whatever the packets are coming to this router, all incoming packets will be transmitted or sent to all outgoing links. All outgoing links except the link or except the router which it is receiving, right? So just flooding means all the incoming packets will be transmitted to all the outgoing links. So for example, this is the router, one router, it is having around 5 outgoing links. These are the links, okay? 5 outgoing links. So if one packet is coming towards the router, automatically that packet will be sent to all the outgoing links. So blindly it will be sending to all the outgoing links. So that is called a flooding, and here there is a disadvantage because so every router will be having multiple copies of packets. Okay, that's the main disadvantage. So multiple copies will be multiple copies of packets. Multiple copies of packets will be received here. So that's the main disadvantage. And the second one is random walk. Random walk. So here in this way, so incoming packets, so whatever the incoming packet is there, that incoming packet will be transmitted to the neighbor packets, neighbor links randomly. So it will not send every packet to the outgoing link, but it will send randomly to the neighbor links. Neighboring links means the connected links. So whatever the systems or routers connected to the particular router, so it will be sending this incoming packet to the neighbor links randomly. So this is best for, this process is best for alternative path. Alternative path. So selecting the alternative path, for selecting this alternative path, so this random walk will be efficient working, right? So these two are the classification of non-adaptive routing algorithms. Okay, now we'll go with the second thing, that is C. Adaptive routing algorithms. So here this adaptive routing algorithm is the dynamic routing algorithm. Dynamic routing algorithm. So during the transmission, the destination, that means the routing process will be designed. Okay, so here routing will change dynamically. Routing will change dynamically based on change in topology and traffic. The network topology and the network traffic. So whenever there is a change in network topology or network traffic, so automatically the routing process will be changing, right? So that is one thing. And the main parameters are hop count, as well as the distance, as well as the transmit time. So based upon these three parameters, the routing will be decided. So from the current place to the next place is decided based upon these parameters: hop count, distance, and transmit time. Right? So this is the main thing, and this is also again classified into 3 ways. These type of algorithms are classified into 3 types. The first one is centralized, isolation, and distributed. centralized routing algorithm, isolation algorithms, and distributed routing algorithms. Now we'll see one by one in a brief way. Okay, so first one, centralized. Here, so finally it will compute the, this is also called as global routing algorithm. So global routing algorithm, and here see, it computes least cost path. Least cost path. Okay, least cost path. So what is meant by least cost path means, let us take 3 nodes A, B, C. See, so if A and C is having a link with a cost of 10, and A and B is having a cost of 4, and B and C is having a cost of 4. So in order to reach C, A can directly reach C. Okay, if you want to send a packet from A to C, so the cost is 10. And if you want to send through B, through B, that means sending the packet from A to B, B to C. What is the total cost? 8. So this is the least cost path. Least cost path. Okay, so this least cost path will be computed here based on global information. Global information. And so the same thing, coming to the isolation, and here also the routing will be done, will be decided based on local information rather than global. So whereas centralized means it will collect the global information, that means it will collect the cost of each and every link. Okay, it will collect the cost of each and every link. So based upon the global information, so this routing process will be decided. And also it computes the least cost path. And coming to the isolation, the routing will be decided based upon the local information, that means the neighboring links. Okay, and not rather than the global. Okay, instead of taking the global information, we collect the local information. So, and the third category, distributed. So coming to this distributed, see here also it computes least cost path based on iterative and distributed manner. See, I will tell you. Distributed manner. So here also it will compute the least cost path, but that will be done based upon the iterative and distributed manner. So initially the current node will know the cost of all its neighbors, and immediately after starting the transmission, it doesn't know the cost of every link, right? So it will be decided randomly or it will be decided dynamically, right? So that will be done. This least cost path will be calculated based upon the iterative calculations, iterative manner, right? So this is the only difference between the centralized and distributed. And one more thing, this is also called as decentralized algorithm. Decentralized algorithm. So don't worry if you are having somewhat doubts in these classifications. So whenever we go with the example algorithm, so that you will be understanding all these points, right? So what is meant by this global information and what is meant by this iterative and distributed manner, how it will be achieved, everything will be known once you go with the example problems, right? Example algorithms. So this is another type of routing algorithm, that is an adaptive routing algorithm. Adaptive routing. Now, we'll see what are the algorithms and in which category those algorithms will be classified. See, so the first one, we'll go with the non-adaptive routing algorithm. Non-adaptive routing algorithm. So coming to this non-adaptive, so it is having the 3 examples. We'll go to see 3 example routing algorithms. That is the shortest path, flooding, and flow-based routing algorithm. So 3 categories, 3 algorithms. We are going to see 3 algorithms under this non-adaptive routing algorithms. Next, second category we have seen adaptive routing. Adaptive routing. So this we are calling as a static, and here we can call it as a dynamic. So dynamically the routing will be changed. So here we will see the link state routing, and distance vector routing. Distance vector routing algorithms. Right? So these two will comes under this adaptive. And see, we will go to the third category. Coming to the third category, hierarchical routing. That we'll see what is the hierarchical routing algorithm, and then we'll go with routing in mobile host. And then broadcast routing, then multicast routing. So in the coming sessions we are going to discuss about all these algorithms. So shortest path, loading, flow based, link state. So again this link state comes under centralized routing, and this will comes under distributed routing. Right? Distributed routing. So we are going to see this link state routing algorithm, distance vector routing algorithms, and then we'll go with the hierarchical routing, and then routing in mobile host, broadcast routing, and then multicast routing. So these are all the different routing algorithms we are going to discuss. Right? See, shortest path routing algorithm. So here in this, the name itself indicates, so the packet should travel from source to destination in the shortest path. So first, route means traveling the packet from source host to destination. And here the route must be shortest route. So the connection of two different networks or two different hosts will be having some sort of function. So this will be with the help of a function between nodes. So we call these systems as nodes. So some sort of function will be available. So with the help of this function, we have to find the shortest route. So this function can be the cost, the distance, the traffic, similarly the bandwidth, right? So anything it may be. The time, also a time. So whatever the function we are using, based upon this function, we have to find the shortest route between the source and destination. So that means the packet should travel from source to destination with the shortest path. Right. So that is based upon this function. This function may be one among these things. So any criteria can be considered as a function. So with the help of that criteria, we have to find the shortest route. Right. Let us move on to the algorithm. See, let us take an example and then we'll find the shortest path. So I will consider a small network. So I will consider a small network. See, so A, B, C, D, E, and F. So let it be. This is the network. Okay, this is the network. Now we have to consider some function between two nodes. So these are the nodes A, B, C, D, E, F are the nodes, and this is a link between each and every node. So there is a link between nodes. Okay, so this link will be having some sort of function. So let us take some cost, or let us take some time. Okay, time as a constraint. Okay, so now we have to give the time to travel from one node to another node. That means we have to give the time for each and every link. Okay, so let it be 2, 6, 4, and this is also 4, this is a 5, and a 7, some 2, and again some 3. Okay. Okay, so let us take this one. So sorry, so 3 and 4. Let us take this one. So we'll consider this network, and we have to find. So this is the source, and this is the destination. This is the destination. Now we have to find the shortest path. This can be done in two ways. One is finding the tree. Okay, so with the help of tree structure, so construct the tree for this graph. Okay, so this is a graph. Okay, we have to construct the tree. Now starting from A, so A is having two routes, that is B, another one is F. Very good, right? Next, so only move forward, not backward. Okay, so now B is having two output lines, one is from to C, one is from to E. So B is having again C and E. Now let us take F. F is also having C and E. The links to C and E. So again you can go with the C and E. Okay. Now C is having to F and D. So here you can see. Okay. Here C, F is already covered. Move only forward. Okay. C to D. So C to D. This is the destination. Right? So let us make this destination. So we have to get all the leaf nodes as a destinations, right? D. Now E, for E also it is D. And similarly here also D and D. So this gives the path from source to destination. See, A, B, C, D. So A, B, C, D. This is one path. Okay. So I will write here A, B, C, D. This is one path. Next, A, B, E, D. So A, B, E, D. So this is one more part, A, B, E, D, right? Next, A, F, C, D. So A, F, C, D, right? A, F, C, and D. Next, A, F, E, D. A, F, E, D. See, A, F, E, and D, right? So these are the possible paths. Okay. So if you go, if you use the the backtracking also. See. So A, F, C, D. A, F, C, D already there. You can go like this. A, F, E, B, C, D. Okay. So I am considering only in the forward direction. I am not considering the backward direction. Okay. So let us consider only the forward direction. So what is this cost? So how to find the shortest path? Now A to B. What is the time to travel from traveling from A to B? It's a 2. So here it reaches at 2. Now F, it reaches at 7. Now from B to C, it is 6. So to travel, the packet should travel from A. So A, B, C. That means B to C it is 6 and up to B it is 2. So total 8. So the total time is 8 here. Now B to E. So one more path is there. A, B, E. So B to E is a 4. Okay, B to E is a 4. Right? So 4 plus 2, it's a 6. Right? Next, F to C. F to C is 5. Already A to F is 7. F to C is 5. So it is 12. Now, F to E. So A to F is 7. F to E is 9. So it is 9. Now to the destination. C to D. Here C to D. C to D is 3. Already we spent 8. So 8 plus 3, 11. Next, E to D. So E to D is 4. So it is 10. Already we have given 6. So 10. Next, C to D. 3. Already 12 is there. So it is 15. Next, E to D. 4. 4 plus 9, 13. So you can observe here, all the leaf nodes are destination and we got the time for all the leaf nodes. So here, A, B, C, D, the total time is 11. A, B, E, D, the total time is 10. A, F, C, D, the total time is 15. Next, A, F, E, D, the total time is 13. So here, you can find the shortest path. So this is the shortest path to travel from the packet from source to destination. So if the packet starts from A, it follows this path to get the shortest distance or to reach the destination with a short time. So it depends upon the function. Okay, right? So this is a one way how we can find this shortest path. So we can construct a tree and with the help of the tree, we can find out the shortest path. Right. Now the second method is Dijkstra algorithm. Dijkstra algorithm. Let us see this one. So I will draw a small latch. Okay. See, the same example I am taking. Okay, now we'll solve it by using one more method, that is this case star. We'll also take the same distance or a cost or a time, whatever it may be. See. So the source is A and the destination is D, so the packet should travel from A and D, and the procedure how to find the shortest path using this ditch case star algorithm. See, so let us find out the nodes coming to B, the incoming nodes to the B. So there is only one incoming node, that is A from A with a cost of 2. So here you can write A2. And here coming to the F, there is only one incoming node, one incoming link to the F, that is from A with a cost of 7. So we can consider it as 7. Right? So here we are having only one possibility, so we have to consider either A2 or A7. Right? Now coming to this C. See, C is having two incoming links. One is from B, another one is from F. Okay, so now if the packet comes from B, the total cost will be 2 plus 6, 8. So B8. And if the packet comes from F, the total cost will be 7 plus 4, that is 11. So that means F11. Okay, now there are two possible ways. So the packet can be reached to C through B or F. So among these two, we have to find the shortest distance or the shortest path. So B8 is the shortest. So we can consider only B8. Okay, we can consider only B8. Now, coming to the E is also having two possible incoming links. One is from B, another one is from F. If the packet comes from B, so already the weight of B is 2 plus 4, it will be 6. So B6. And if the packet comes from F, so 7 plus 2, it will be 9. So F9. So among these two, which one is the shortest one? So this one is the shortest path. Now coming to the D, there are again two incoming links. One is from C, another one is from F. Okay, one is from C, another one is from, C and E. So if you consider here, if you consider C, so already the shortest path we got is 8. So let us consider it. So C11. C11. Okay. So coming to here, already the packet is at A with the cost of 6, which is coming from B, and to reach D, the cost is 4. So totally E10. So you can consider the least cost. You can consider the least cost among this one. Okay. See. So you can also calculate these things. So F11 is one way. Okay. F11 plus 3. So that means in order to reach this, we'll get F14. And here, in order to get this, we'll get F13. Okay. Among all these things, this one is the shortest distance or the shortest cost. Okay. Shortest path. So just backtrack. So first one, so D, in order to reach D, we are considering E. So E. So go to the E. So in order to reach E, we are considering B. So B. In order to reach B, we are considering A. So as this is only one node, we have considered it as a shortest, right? So A. So A. So this is the shortest path in order to reach from source to destination. So the total cost or the total distance will be 10, or total time is some time. Okay, the function, whatever the function it may be, so it may be a time or a distance or a cost or a bandwidth, whatever it may be. So based upon this functionality, we are supposed to find the shortest path from source to destination, so that the packet will travel from source to destination with the shortest distance or a shortest path. Right? So this is the simple algorithm, that is the shortest path routing algorithm, which is a static routing algorithm. So it's a non-adaptive routing algorithm. So very simple routing algorithms, these two, flooding and shortest path. So first, this flooding is nothing but the broadcasting the message. It's a broadcast the packet. So what is meant by this broadcast? So what this broadcast means, sending the link to all the neighbors, sending the link or sending the packet to all its neighboring routers. So that means sends the packet to all outgoing links except to the link from which it was received. So we have to send the data packet to all the outgoing links except only one link. That means from which we have received the packet, right? So this is the only concept in this flooding, just like flooding of water, right? So flowing of water. So this is nothing but a broadcast. So without considering any constraints, just sending the message or just sending the data packets to all the possible ways. See, let us take an example. See, I am taking the same example which we have solved in the shortest path routing algorithm. So now A is a source. See, A is a source and D is a destination. A is a source and D is a destination. Now A wants to send the data from, the data should be sent from A to D. Now blindly, without knowing anything, just sending the data to its outgoing links. So here A is having two outgoing links. So A is having two outgoing links to B and F. Sorry, B and F. So A sends the packet to B. Similarly, A sends the packet to F. Right? Now, B is having one packet, B is having one packet, F is also having one packet received. Okay. Now, B is having how many outgoing links? So consider one node at a time, one router at a time. Okay. Now consider B. So B is having how many outgoing lines? So A, C, E. Three outgoing lines. Okay. A is having three outgoing lines. Now B received the packet from the A. Okay. B received the packet from the A. That's what we are saying. It sends the packet to all outgoing links except, so this is very important, except to the link from which it was received. So B receives the packet from A. So you need not go with the A. Just remove A. So B have to send the data to C and E. So B is sending the packet to C and E. Now receives packet, C receives the packet. C receives the packet. Okay. This is the received packet. Okay. So square box means received. Received. Okay. Now coming to C. So C is having how many outgoing links? So C is having B, comma, F, comma, D. Three outgoing links. And we have to consider this except. So from where we got the packet to the C? From B. So just remove this B. We need not send the packet back to B. So C have to send the packet to F and D. So C sends the packet to F and C sends the packet to D. So here, so D receives the packet here and again F receives the packet here. Okay. So C receives the packet here, F receives the packet here. Now D. So we need not bother about D because D is the destination. So that means D will not be having any outgoing links. So don't consider the destination. Consider E. So E is having how many outgoing links? F, B, D. Okay, E is having the outgoing links F, B, D. But E is having the packet, right? E is having the packet. So consider this condition. From where we got this packet? From B. So you need not bother about B. So send the packet here and send the packet to here. Right? So hope you understood this one. Next, F. Consider F. F is also having the three links, that is A, C and E. So F receives the packet from A. So remove A. F also receives the packet from C. Remove C. F also receives the packet from E. Remove E. So F is not having any outgoing link. So F need not send the data. Right? So this is how we can apply this flooding. The only one concept, that is just blindly sending the data to all the outgoing links. The main drawback here is you can observe clearly at the router F, the same packet has been received 3 times, and at the same packet of data is received 2 times at the router D. So that means the main drawback is getting duplicate packets. So a router can have the duplicate packets. Okay, so you can observe clearly that F receives 3 packets of same data, that means 3 duplicates, and again D is receiving 2 packets of same data, that means again duplicates. So this is the main drawback of this flooding algorithm. So in order to avoid this drawback, so avoid duplicates, use sequence number. See, in order to avoid the duplicates, just give the sequence number for every packet and just flood it. Okay, now we'll see. So we are using sequence number. See, I will erase everything and we will again send the data with the sequence number so that we will see whether these routers will receive the duplicates or not. So we'll apply the same concept. So sending the packet to all the possible outputs except the one which it has been received, right? So now A is having two things, two routers, neighboring routers. So A is sending the packets with serial number S1. So B receives the S1 and here F receives the S1. Okay, so before receiving, the B will check whether the data has been received with the same serial number or not. So if not, then it will accept the packet from the A. So now B is not having any packet, so B accepted the packet which is coming from A, and also F is also accepting the same packet from A. Now B is having one packet and F is having one packet. Now same, B has to send to C and E. So B will send this packet with the serial number to C. Okay, so now C again checks whether it is having the data with the same sequence number. No, it doesn't have any sequence number S1, so it accepts the packet from B. Again E. So E first it will check whether it is having the sequence number, packet with the sequence number S1. It doesn't have, so it will accept the sequence number S1, right? Now C. So C have to send to F and D. C is supposed to send the data to F and D because 2 outgoing links. There are 3 outgoing links. B we have to exclude the B because from the B itself we received the packet. So exclude the B. We are having 2 links, that is F and D. Now C sends the packet to F. Now F, before accepting the packet from the C, F checks whether it consists of the packet with the same sequence number. So it will check and it will having the same packet with the S1 which is received from the A. So F will reject this packet which is coming from the C because this is also having the same sequence number and it is already received by the A. So it doesn't accept the packet from the C. And now C sends the packet to D. So D receives the packet S1 with the sequence number S1. So this is completed. Now E to F and D. E must send to F and E must send to D. So E will send the packet to F. So once again F checks whether it is having the packet with the same sequence number. Yes, it is having the packet with the same sequence number which is received by the received from A. So F will reject the packet which is coming from E. Similarly, E will send the packet to D. So again, D will check whether it is having the packet with the same sequence number. Yes, D is already having the packet with the same sequence number which is received from C. Right? So D again rejects the packet coming from E. And F, coming to the F, see, F have to send the data to A, C and E. Okay, so F receives the packet, so it need not go for A or C or D. Right? Just ignore this. So here, if you observe here, every node is having the packet only once. There is no duplicates. So before accepting the packet, the router will check whether the previously received packets are of same sequence number or of same data. If the previously received packets are of same sequence number and same data, the packets will be rejected by the router. It will not accept the packets. Right? In such a way, we can draw back these duplicate packets by adding the sequence number to each and every packet. So you can observe there is no sequence, there is no duplication of packets in any one of the routers. Right? So this is how we will apply the flooding. The only one thing is just blindly passing the packets to all its outgoing links except to the receiving link. Right? So this is all about flooding, and we'll move on to the next one. That is a very simple routine, that is flow based routine. flow based routing. Flow based routing. So this flow based routing is also one of the non-adaptive algorithm. That is a static algorithm. So it must be, and here the routing will be done. The routing is done based on two conditions. So one is topology which the network is using, and the second one is the load or traffic. So based upon the topology and the traffic, the packet will be routed to the destination. So we'll see the same thing. So whatever we have seen in the shortest path routing algorithm, so you can observe here. See, so very simple concept. There is nothing complex here. See, so if you consider this one, so I think in the shortest path routing we have seen. So there are many possible ways. So let us consider this is a source and this is the destination. Okay, so source and destination. So packets have to be sent from source to destination. There are many paths: A, B, C, D, A, F, E, D, A, B, E, D, A, F, C, D. Okay, so likewise different solutions are there, different paths are there. Now we'll go with the shortest path. First we'll go with the shortest path. So we have seen the shortest path. So that is A to B to E and to D. So in the shortest path routing algorithm we have seen that. So this is the shortest path with a given distance, right? So if the path is having a heavy traffic, if the same path is having a heavy traffic, so we can change the path to the next shortest path. So if this is having a heavy load or heavy traffic in this path, that means A to B, B to E, E to D. If this is having a heavy load or a traffic, we have to select for alternate path, that means the next shortest path. So moving to next shortest path. So we have to move only when it is having a load or a traffic. It may be A to F, F to C and C to D. Okay, A to F, F to C, C to D. So this is the next shortest path. Okay, so that based upon these two things, that means the topology which it was using as well as the traffic in the current path, so it will change its route to different way. I mean the next shortest path. It will select the next shortest path to reach it to its destination. So these two are the remaining non-adaptive routing algorithms, right? So flooding and flow based. So as these are all the static routing algorithms. These three are the static routing algorithms. So priorly, before starting the routing itself, every node should have an idea about all its neighbor nodes. So whatever the algorithm you are considering, it may be a shortest path or it may be a flooding or it may be a flow based. So as it is a static routing algorithm, whenever the network is booting up, the routing table or the routing path should be embedded in the router. So that's why every router, whatever it may be, the three algorithms, whatever it may be, every node, every router should have an idea about all the links of its neighbors, along with this cost or a distance or something. We generally call it as a function, right? So both the link description as well as the function. So every node should have a clear-cut idea about these, the neighboring links and the functions, particularly in these non-adaptive routing algorithms. So routing means transmitting the packets from source to destination and which path we have to follow. So that is least cost distance path should be followed. So we know that, so there will be a number of routers, okay, and the packets will be transmitted from one router to another router. And here this is a dynamic state routing algorithm. And here every router will maintain routing table. routing table. So which fields or which content will be available in this particular routing table, and this routing table consists of the destination hop, so we can call it as a hop or network or router or a system, whatever it may be, and how much distance it requires to reach the destination, and what is the next hop, or what is the next system, or what is the next router. And this information will be maintained in each and every router. Okay, and this routing information will be shared with all neighboring routers. So this is most important. So whatever the routing information maintained by each and every router, so will be accessed or will be shared among all the neighboring routers, only the neighboring routers. Now neighboring routers means, so the routers which are having a direct links. Okay, the router which is having the direct link are called as a neighboring routers. And by sharing the routing information with the neighboring routers, the routing table will be periodically changing. So the routing information will be updated periodically. After sharing the routing information with the neighboring routers, the routing table will be keep on updating. So finally this will be repeated until there is no new information is to be exchanged between the routers. Okay, so that's why we call this distance vector routing algorithm as an iterative routing algorithm, and this mainly follows Bellman-Ford equation. In order to calculate the least cost. Path, we'll follow the Bellman-Ford equation. So I'll tell you the equation, and moreover, while solving the problem, you will be understanding what exactly this equation, right? So see, the Bellman-Ford equation is dx of y. So where x is a source and y is a destination. So d is a distance, okay, is equal to minimum of v. So here v is nothing but intermediate node. So obviously in a network, one router may not be directly involved with the other router, right? So there might be having some path. Okay, for example, if you consider A, B, C and D, so this is the information. So you can see A is not directly connected to C. So if you want to travel or if you want to transmit the packets from A to C, that should be done only in this way. So that means there may be having the intermediate nodes, intermediate hops. So here V represents such intermediate path. So minimum of what we have to do, so cost of x comma V, that means from source to intermediate plus the cost of source to intermediate plus the distance of V to Y. So this is the distance from node V to destination. This is a cost of node X to V, and this is the distance from X to Y, source to destination. So this is the Bellman-Ford equation, and we have to use this equation in order to update the routing table periodically, right? So we'll see an example so that you will be understanding perfectly. See, let us take some example. So let it be, the network is like this: A, B, C, D, 4 routers, and the distance from A to B is 5, B to C is 2, C to D is 3, and D to A is 8. Now A will be having a routing table. First one is a destination, distance, and next hop, right? Similarly, B will be also maintaining the same thing. B will also maintain the same thing, right? So the first one will be the destination, distance, and the next hop. Node C we also maintain the same thing. So first one is a destination, distance, and next hop, and router D. It will also maintain the complete information of destination, distance, and next hop. Okay. Now see, destination A to A, B, C, and D. Here there are 4 routers A, B, C, D. A, B, C, D. A, B, C, D. You know that this is a source, and this will be the destination. If source and destination are equal, the distance to be traveled is 0. So obviously A to A is 0, the next hop is none. Okay, and B to B is 0, next hop is none. C to C is 0, next hop is none. D to D is 0, next hop is none. Right? Now, based upon this information, we have to give the complete routing information. Okay. See, A to B, that's a direct link. A to B, the distance is 5 and the next hop is B. And coming to the A to C, there is no direct link. So it may travel through B or it may travel through D. So you can imagine the distance as infinity. Okay, so that means it contains some intermediate nodes, and that can be either from B or D. So simply leave blank. Okay, and here the next node is A, okay, and C and D. Okay, so because only one node, if only one node, then the next node will also be that same thing. Right. Next, A to D there is a direct link, so 8 distance, and the next one is D. Hope you understood. So there is no direct link from A to C. So if the packet if the packet want to be transmitted from A to C, that can be transmitted through B or D with a different cost. So we don't know which will give the minimum cost. So by observation, we may know that if we want to travel, if the packet want to be transmitted from A to C via B, it requires a less cost, because through D it takes some cost as 11, and if it is B, the cost will be 7. So 7 is the least when compared to the 11. So the packet can be transmitted from A to C with the help of B. But we know that, right? By observation, we can easily know. But the system doesn't know, so that just imagine that we don't know the cost, minimum cost. So simply give the infinity. Similarly, B to A, there is a direct link. So distance is 5 required, and the next one is A. Okay, and B to C, yes, 2 distance and C. And B to D, there is no direct link. It may travel through A or C. So simply you can use infinity and hyphen. Similarly, C to A, no direct link, infinity and hyphen. C to B, so C to B, so 2 distance 2 and the next hop is B. C to D, 3 and next hop is D. And D to A, 8 and D. D to B, there is no direct link, so it should transmit it through the intermediate node, so the cost may be differ, right? And D to C, and 3 and it is C. So for the first iteration, the routing tables will be this one. So A routing table of A, routing table of B, routing table of C, and routing table of D. Now in the second iteration, the routing table of A will be shared among its neighboring routers. Okay, so routing table of A is shared among, you can see what are the neighboring routers of A, B and D. So B and D. And similarly, routing table of B will be shared among A and C. And routing table of C will be shared among B and D. Routing table of D will be shared among A and C. And by sharing that one, so these routing tables will be keep on updating. Okay, now we'll see one by one. So first we'll see routing table of A, which is shared among B and D. Okay. So in this table, we got a path for everything except for C. If the packet want to be transmitted from A to C, there is no perfect path. So if the packet wants to be transmitted from A to B, we are having a path. Okay, we don't know whether it is a minimum cost or it is a maximum cost. So that should be done with the help of this one, this equation, right? So Let us try this one. Routing table A will be updated. First, you can see this is the destination, this is the distance, and this is the next hop. And this is the routing table of A, updated routing table of A shared with the B. Consider only the distance. Okay, consider only the distance. You can consider only the distance. Need not go with the all other. B distance 5, 0 to infinity. Okay, 5, 0 to infinity. And the destination is A, B, C, and D. Now, consider the source to destination with the help of intermediate node B. Okay, so here two things we have to consider. One is minimum cost, another one is minimum intermediate nodes. Minimum intermediate nodes. So if we want to transmit the packet from A to B, that can be done through A to D, D to C, and C to B. Or simply we can transmit from A to B. So we have to consider that there should be a minimum cost as well as a minimum intermediate nodes. So if A wants to transmit the data to B, this is one path, and another path is A to D, D to C, and C to B. So in this path also we can transmit the packet from A to B, right? So but here we are having a two intermediate nodes, so we should not consider this one. So this is most important here. So we have to consider the minimum cost as well as the minimum intermediate nodes. So let us check with this one. So A, destination A to A, obviously the distance will be 0, and the next hop will be A itself. Now A to B, okay, so A to B and B to B. So you can see A to B is a cost and distance of B to B. You can see the distance of B to B, and you can add. So which will give A to B cost is 5, and what's the distance from B to B? So B to B, so this is A, this is a B, this is a C, and this is a D. So this is the distance. This is the distance, right? So this will be the distance. So here we need to calculate the distance, and this is the cost. Now the cost of A comma B, okay, because we are giving A to B. What's the cost of A comma B? It's a 5 plus what's the distance from B to B? B to B, it's a 0. So it will be 5. It will be 5. Okay. So now simply you can write it here. It is a 5, and the next one is a B. The intermediate node is B. And similarly A to C with the intermediate node B. Now A to B, okay, A to B and B to C. A to B and B to C. C. Cost of A comma B plus distance of B to C, which is nothing but cost of AB, which is a 5, and distance of B to C, distance of B to C 2. So it will be 7. So directly we can get 7 with the intermediate node B. Now we can see in the first iteration, so there is no proper path from A to C. But in the second iteration, we got some distance with 7 with the, using the intermediate node B, a packet can be transferred from A to C. Right? Next, D. A to D means A to B plus distance of B to D. So A to B is a cost of 5 plus B to D is again infinite. So obviously it will be infinite and hyphen. So the new routing table of A, is A to 0A, AB 5B, C 7B, and D again we are not having a correct path if you want to transmit a packet from A to D. Now again the same routing table will be shared among the next neighboring router D. See, this we got with a B. Now the same routing table should be updated by sharing the information with the next neighboring router D. Okay, now this is a D. Same procedure will be applied for D also. Okay, consider only the distance. So D distance 8, infinity, 3 and 0. So this is A, B, C and D, and here also A, B, C and D. And this is a A. Hope you understood. First, this routing table is shared with B and we are updating the A. Same routing table is updated with the D and we are updating A. Okay, after that we have to combine these two routing tables. See, A to A, obviously the distance is 0 and the next hop is A. Now with respect to D, we have to consider with respect to D. Now A to B. A to B means A to D and plus D to B. That means simply we can say a distance of D to B. So what's the value A to D? 8 plus D to B. Say infinite. So obviously it is infinite. Okay, it is infinite. So you can say it is infinite and hyphen. Now A to C, A to D plus distance of D of C. A to D is 8 plus distance of D to C. D to C is 3, which is 11. So 11 and with respect of D, intermediate node is D. And A to D and A to D. So we know that A to D is a neighbor, so A to D plus distance of D to D. A to D cost is 8 plus D to D cost is 0, which is 8. So it requires 8 with next D. So this is the routing table we got with respect to D. Now we are having two different routing tables. So previously in the first iteration the routing table of A is this one, and after sharing this routing table with the neighboring routers B and D, the tables have been updated in this way. Now combine both and find out the least cost. Consider the least cost. So now you can observe, I'll update this one. Let me update this one. So this is the destination, this is the distance, and this is the next. So A, B, C and D. Consider both the tables. So this is the A, table A. Okay, so 0 A. If the packet want to transmit it from A to A, if the source and destination is same, the distance it should travel is 0. And if the destination is B, that means if we want to transmit the packet from A to B, so A to B takes a 5 distance and here it takes an infinity distance. So consider the least one. So B5 and with the intermediate node B, because B is a directive. Okay. Next, consider C. If we want to transmit the packet from A to C, okay, consider here it requires a 7 distance and it requires 11 distance. So with an intermediate node B, with an intermediate node D. Now we have to consider the least one. So 7 will be the least. So the packet can be transmitted from A to C with a distance of 7 through the intermediate node B. And coming to the A to D, if a packet wants to be transmitted from A to D, then you can see here there is an infinity and here we are having some 8. So consider the least one. So it requires 8 with a D. So this will be the updated routing table of A. Updated routing table of A. So you can see with your observation, if source and destination is A, it requires 0. And if a packet want to be transferred from A to B, the least distance is 5. Yes. And if the packet want to be transmitted from A to D, the least distance is 8. Okay. So also there is a path from A to B, B to C, C to D. So 5 plus 2, 7 plus 3, 10. So it's a longest path. So here 8. Okay. So we have to consider only A to D. C. And if the packet want to be transmitted from A to C, so through D it is 11, through B it is 7. So what we have to be considered? So 7 with B. So 7 with B. So periodically, time to time, the routing tables will be keep on updated. Now the routing table of router A is this one. So initially the routing table will be created here, and this routing table will be shared among two different, to all its neighbors. So in this network we are having two neighbors B and D. So we have calculated the routing table with respect to B and with the intermediate node D. So in every case we have applied the same thing. So that is a Bellman-Ford equation. So by combining these two routing tables, we are considering only the minimum cost and minimum intermediate nodes. Okay, so this is how we have to consider A. And the same process should be continued for B. So now replacing A with a B data, and the B routing table will be shared among C and A. That means the same calculations, the routing table of B will be updated with intermediate node A here and with intermediate node C here. and both will combine, and finally we'll get the complete routing table of B. Similarly C. So routing table of C will be shared among B and D, and we'll combine both and we'll get the updated routing table of C. Okay, and then next D. Again the D routing table will be shared among A and C, and still we are having such type of infinity. Again the same process will be repeated. The updated table will be again shared among the the neighboring routers. So here the neighboring routers means which are the routers or hops which are having the direct link from the source. So we have to repeat the same process and we have to calculate the routing table. So instead of calculating this one directly by observation, we can simply find out the least cost distance, and that should be applied in our competitive exams. We need not explain all these things in the competitive exams, right? So directly by observation we can simply find out the least cost distance. So based upon the distance we are calculating this one. And what is a vector? So this routing table we call it as a vector, right? So the same vector will be shared among the neighboring neighboring routers. So it is also called as a distributed algorithm, because the same information will be distributed among the neighboring routers, and also iterative. So the same process will be keep on iterating until there is no new information to be shared. So if here we are having a new information, okay, so there is no correct path, so that's why we are sharing the information to neighboring routers, right? So here we are not having any new information. So there is, for every node we are having the latest, the least distance path. So we can stop here. So this is a distance vector routing algorithm. So the main point is we have to follow this Bellman-Ford equation, and we need to remember that we have to consider only the minimum cost and minimum intermediate nodes. Okay, so I'm just stopping here. So you just continue with the same procedure by applying B, sharing B with A and C, C with B and D with A and C, and find out the updated routing tables for remaining three, B, C and D. Now we got A. Calculate and update the routing table for B, C and D. So this complete link state routing algorithm involves the two different phases. The first phase is a flooding phase, and the second one is a routing path, finding the routing path, right? So these are the two different phases involved in this particular routing algorithm. So the first step is finding distances for neighboring routers. So that means neighboring routers means the routers which are directly connected. Okay, so first we have to find the distances. So this will happen just by sending some hello packets to the neighboring routers. So from that it will find the complete distance, how long it is linked to the particular neighboring router. And the step 2, once there is a distances, now find the link state. Find the link state table for every router. So we have to find out the link state table where it contains the neighboring routers along with the distance. Okay, so this link state consists of so here we will be having the neighboring routers and the distance. Okay, so routers and distances, and apart from these, two fields will be available in this link state table. So one is a sequence number, another one is a TLN. So two more fields. So here sequence number, for every packet it gives one sequence number, right? So in order to find out the recently sent packet, so because this type of tables will be updated frequently, right? So this is a dynamic. So one, for example, so this is a normal network. Let us consider normal network. So a packet should be sent from A to C, right? A to C. So there is a direct connection. So C is a neighbor router of A, so directly it will be sent. If this particular link was not properly connected, or there might be some loss of the connection, then it will follow this path. Okay, it will follow this path through B. So in order to avoid this one, so which packet should be considered? So the sequence number will tell that the recently sent packet should be considered. Okay, the old packet should be discarded. So the routing table will be keep on updating. Okay, keep on updating. So in order to consider the recent packet, so we have to use this sequence number. And coming to the TLL, TLL is nothing but a time to live. Time to live. And this TLL will be greater than 0. And we are saying that flooding will apply the flooding. That means we have to send, every router will send the link state tables from one router to the another router. So flooding means simply passing to all the routers in the network. So A will send the link state table to D, B and C. Similarly, D will send the link state table to B and A. Similarly, B will forward the link state table to C. Like that, the link state tables will be flooded throughout the network. So every router link state table will be flooded. So where the flooding should be stopped? That's the main question. So this TLL will be always greater than 0, and once the packet is forwarded to another router, this TLL will be get decremented. So if this TLL value is equal to 0, that implies that packet should be stopped for flooding. Okay, so in order to avoid the infinite flooding, we are going to use this TLL field, right? So this is the step 2, finding the link state table, and this link state table will be having the sequence TLL and all the neighboring routers and corresponding distances. So from the first step, we will be getting the distances of the neighboring routers. So in the second step, we are creating the link state tables for every router. And coming to the step 3, so just now we have discussed that the flooding will be done. So flooding of link state table from one router to other. So every router link state table will be flooded throughout the network. Okay, and then so every router will be having the link state table of all the routers. So last step, applying the Dijkstra algorithm to find the shortest path. So every router follows Dijkstra algorithm. So we know the Dijkstra algorithm is to find the shortest path from source to destination. So the same thing will be applied on every router to find the shortest path. So these are the steps involved in link state routing algorithm. So 2 phases, flooding. So this is completely comes with the first phase, and this will be the second phase. Second phase routing path. So this will be calculated with the help of this Dijkstra algorithm, following the Dijkstra algorithm. Right? Now let us take an example so that we will see what happens. Let us take an example. Consider any random network. So, okay. So this is a network, a random network. Let us take the values. So let it be 2, 6, some 3, some 4, and some 2, 7, some 4, and 5. Right? So the first step, every router will send the hello packets to the neighboring routers. So A will be sending hello packets to B, F, and finding the distance. So how far it was linked, right? Next, B will be sending the hello packets to A, E, and C. Similarly, C sends the hello packets to B, F, and D. And D sends the hello packets to C and E. And E sends the hello packets to B, D, and F. F sends the hello packets to A, C, and E. So by sending the hello packets to all the neighboring, so neighboring means directly connected routers. Okay, so we'll be having the distances. It will find the distances. This is the first step. Second step, finding the link state table. Okay, so it will find the link state table. Let us consider A, the link state table. So it will be having the sequence and TLL. Okay, and here we'll be having A is directly connected to B with a distance 2, and it is directly connected to F with a distance 7. So next, the link state table for B, the two columns are a sequence and TLL and B, and the neighboring routers of B are A with a distance of 2 and C with a distance 6, and there is a third neighbor also, that is E with 4 distance. So like this, so we need the link state table for all the routers. See, so B with a 6 and F with a 5 and D with a 3. And similarly, there is one more. So the first two fields are sequence and TLL. Okay. So D with the C with the 3 distance and E with the 4 distance. So two fields and E. So E is having 3 neighbors. One is F, B and D. So F, B and D. So F is connected with the 2 and E is connected with the 4, B is connected with the 4 and D is connected with also 4 distance. And one more. So two fields for sequence and TLL and F. Node F is connected with the 3. One is A, C and E. A, C and E. A with the distance 7 and C with the distance 5 and E with the distance 2. So all these are the link state tables of each and every router. So these link state tables will be flooded. These will be flooded throughout the network. Okay, so that the sequence number will be used to consider the recently sent packet, and TLL is used for avoid the infinite flooding. Right? If it is 0 or less than 0, automatically that implies the packet should not be flooded further. Okay, so now the last step, every router will be having the complete knowledge of every router link state table. Okay, so A will be having the complete link state tables, B will be having the complete link state tables, similarly C, D, E and F will be also having the link state tables. Now every router will follow the Dijkstrata algorithm to find the shortest path. Let us take an example. Consider from A. Consider A. How to find the shortest path from A? So this is an initial state. Okay, initial state. Now consider A with a distance 0, it will find out the A. Okay, now with a distance 0, now A will be having 2 paths. So A can link with B with a distance of 2 and A can send the packet to F with a distance of 7. So A is directly connected to B and F. So now consider the shortest distance among these two. So because these two are the neighboring routers of A. Okay, now what is the shortest one? This one is the shortest one. Now you can see A, B. So A, B, you can observe from A and B, what are the possible paths? C or E. So C with 8 or E with 6. You can observe A, B. Now packet has been transferred from A to B. Now the packet can be further transmitted to C or E. So if the packet is transferred to C, what is the distance? 2 plus 6, 8. If the packet is transmitted to E, the distance is 2 plus 4, 6. Now consider the shortest one. So which one is the shortest? This one is the shortest. Now the next one is A, B, E. So now the packet is at E. A, B, E. Right? So let us consider this as a packet. Now A, B, E. So in this way, it got. Now the possible paths you can see either F or D. It can't be retransmitted to, it can't be transmitted back to B, right? So it can be transmitted towards F or D. So F or D. If it is transmitted to F, what is the distance here? So 2 plus 4, 6. 6 plus 2, 8. If it is transmitted to D, what is the distance? So 2 plus 4, 6 plus 4, 10. So which one we have to consider? We have to consider the shortest one. So the packet will be transmitted here. Right? Now A, B, E, F. So the packet is transferred from A, B, E, F. Obviously, the packet can't be transmitted to A because A is already visited, right? So A is an initial state. It can't be sent to the initial state, right? So it should be transmitted towards C only. There is only one path. Okay, the F can't transmit the packet to A, or it can't be transmitted back to E. So the packet should be transmitted from F to C. So only there is one path. What's the distance? 2 plus 4, 6. 6 plus 2, 8. 8 plus 5, 13. So the distance is 13. So it is transmitted towards in this direction. A to B, B to E, E to F, and F to C. Now there is only one path. So obviously we have to consider the same thing, because if you are having the multiple paths, then we have to consider the shortest path. So here we are having only one path. So we have to consider the same thing. So A, B, E, F, C. So obviously the C can't send to back to B because B is already visited, and C can't be transmitted to F because C received the packet from F only. So the C will transmit the packet to D. Okay, transmit the packet to D. So obviously D with a distance. So 2 plus 4, 6. 6 plus 2, 8. 8 plus 5, 13 plus 3, 16. 16, right? Now the path is A, B, E, F, C, and D. So from D, now the packet is here. Now D, from D, the packet can't be transmitted to E because E is already visited. Packet can't be transmitted to C because C is already visited. So once check whether all the routers has been visited or not. So A, B, E, F, C, D. So in order to transmit the packet in the network, this is the shortest path with a distance of 16. And you can check any other path. Obviously the distance will be more than 16. Okay, so the same thing we'll explain in the Discustor algorithm. Okay, I'll post the Discustor algorithm link in the description, so you can check the algorithm in that particular description box. Okay, so this is how we are implementing the link state routing algorithm. So two phases, so flooding and routing. Two phases. So flooding all the link state tables, and every router will follow the Discustor algorithm to find the shortest path. So in our previous session, we have seen a few more algorithms like distance vector and link state algorithm. So where we are creating, or we are finding the link states initially, right? Or else the vector, distance vector tables. So which gives the distance and all the neighboring routers, right? So similarly, in the hierarchical routing, the name itself indicates first the routers will be classified into different categories. Okay, so the collection of a few routers will be grouped as regions. Okay, and the collection of all the regions will be classified as a clusters, and a group of clusters is classified into zones, and group of zones will be classified as a groups, right? So this is a collection of routers, regions, clusters, and zones. So best example for getting this hierarchical routing is, so if A wants to send a message in terms of post to B, so what is required, right? Directly the A can send the post to the B? No. So it requires some address. So in the first, the country will be decided. Okay, first the country, and then in the country, state will be decided, and in the state, city will be mentioned. After that, street will be mentioned, right? After that, the door number will be mentioned. So this is a hierarchy which is used to send some message in terms of post to one person to another person. Similarly, if you want to transmit a packet from one router to another router, so it will be easy if you use these type of hierarchical fashion. That means collection of, grouping of routers as a regions, and grouping of regions as a clusters as a zones, and zones as a groups. And here one point is, every router will know the information of all other routers in the same region, right? See, for example, so A, B, C, D, E, F, G, H, I. For example, this is one region, and this is another region, and this is another region. Okay, three regions are there. So let us assume that A, B, C, D, E, F, G, H, I, all are the routers. All are the routers. So this is a region 1 and this is a region 2 and region 3. So here A knows the information of B and C, and similarly B knows the information of A and C. C knows the information of A and B, right? Because all the three belongs to the same region. So A doesn't have any information about the remaining routers of other regions. That means A doesn't know the information of D or E or F or G or H or I. Okay, so the packet will be transmitted from one region to another region, and in that region the packet will be received and will be routed through, routed in that particular region, right, to the destination. So there will be one connection, okay, there will be one connection from one router in one region with another router in another region. For example, let us consider the same example. So let us have a look. So let it be A, B and C. D, E and F. G, H, I and J. For example, this is one region and this is one more region and this is another region, right? So R1, R2 and R3. So there are three regions. Now you can see B is a router belongs to R1 and D is a router belongs to R2. So there is a connection in between these two. That means one router of one region is connected with one router of another region. So these routers we call it as a gateway routers. Gateway routers. So the packets will be transmitted from one region to another region to the gateway router, so that from that gateway router the packets will be transmitted towards the destination within that particular region. So for example, here F is one router in region 2 and G is one router in region 3. So both are connected. So one router in one region is connected with another router in another region. So these two are also called as a gateway routers. Okay, so if B want to send a packet to G, so first B will be sent to D and through D it will be sent to G. So instead of having a complete path, so just we are sending the packet to the region only. So in that region the gateway routers will route the packet to the destination. So this is called a hierarchical routing. Okay, so the advantage is it reduces the complexity, right? And also mainly it reduces entries in routing table. So obviously the routing table will be maintained in each and every router, so that it will be, the connections and the distances, right? So the entries will be reduced because here we are not sending. So for example, if A wants to send to I, A to I, then what happens? A will be sending the packet to the gateway router of that particular region, and this gateway router will send the packet to gateway router of another region D, and gateway router of D will be sending to the gateway router of R3 because I belongs to R3. So that's all. Now the gateway router of R3 will route the packet towards its destination. So automatically it will reduce the entries in routing table, and also if these entries will be reduced, the routing efficiency will be increased. Efficiency will be increased. Okay, so for that there will be levels of routing will be done. So in the two-way level, so all the routers will be grouped as the regions. Okay, in this fashion. And if there are more number of regions, again the regions will be divided into clusters. And if there are more number of clusters, again those clusters will be classified as zones. And if there are more number of zones, again these zones are grouped into groups. Right? So in this way the hierarchical routing will be performed. So we'll take one example and let us see how many entries will be there for the link state table and how many entries will be there for the hierarchical routing. Right? So Let me explain with a small example. So let us take this small example, right? So A, B and C. Okay, so 1A, 1B and 1C. 1 stands for region, right? So this is 2A, 2B, 2C and 2D. And this is 3A, 3B and 3C. Let us take this network. Okay, and one more we can have. See, this is one more network. Let us assume that, okay, 4A, 4B, 4C, 4B. Now you can see a normal link state table, right? So the source is 1A and the destination 1A, 1B, 1C, 2A, 2B, 2C, 2D, 3A, 3B, 3C, and then 4A, 4B, 4C and 4D. So this is the next hop, and number of hops, right? So coming to 1A is a source and this is a destination. Okay, so let us take here, it is a destination, and source is 1A. Okay, source is 1A and destination is 1A. So next hop will be nothing, number of hops is nothing. And if it is 1A and destination is 1B, the next hop will be 1B and it requires only one hop. Okay, that means the number of links, you can say the number of links. Okay, next 1A to 1C, again here 1C is the next hop and 1 will be the next one. 1A to 2A, via 1B. So also the packet can be transferred through 1C, but the number of hops will be increased. 1, 2, 3 hops will be there. I mean 3 hops will be required if the packet is transmitted through 1C, and only 2 hops will be required if the packet is transmitted through 1B. So through 1B and 2 hops, and similarly 2B, similarly 1, 2, 3. So via 1B it's a 3 hops. 2C. So you can see 1, 2, 3, 4. 1, 2, 3, 4. Right? So in any way it can go. So it requires a 4 hops. And coming to 2D. So via 1B, 1, 2, 3. Okay. So 1B, 3 hops. If 3A, 1A is the source and 3A is the destination, you can see 1, 2, 3, 4, 5, 6 hops. It requires 6 hops. Okay. Yeah. So 1B and 6 hops. And if you go with the 3B, 1, 2, 3, 4, 5 hops. So 1B and 5 hops. And if it is 3C, again 1B and 6 hops. If it is 4A, so from 1A to 4A, so 1, 2, 3. So via 1C, 3 hops. 4B, 1C, 2 hops. 4C, via 1C, 1, 2, 3 hops. And 4D, 1, 2, 3, 4. So 1C and 4 hops. Hope you understood. So this is a link state table for a normal this network. If you classify the same thing, as a regions, so I am classifying all these as a regions. Okay, I am classifying them as a regions. So this is a region 1, region 2, sorry, this is a region 4, region 2 and region 3. Now you can see the same thing, destination, next hop, number of hops. So source 1A. Here the source is 1A. Okay, now you can see 1A, 1B, 1C, 2, 3 and 4. So you need not go with the 2A, 2B, 2C, 2D, 3A, 3B, 3C, 4A, 4B, 4C, 4B. So just we are transmitting the packet from one region to another region. That's it. So A is in the first region, so we are giving all the hops in the particular region. So 1A, 0 hops, 0 next hop. So 1B with 1 hop and 1C with a 1 hop. And if you want to send a packet to any router of second region, it requires, so via 1B, 1, 2, so only 2 hops. So after within the 2 hops, the packet will be received to 2A. So then this packet will be transmitted to the destination by this particular gateway router. And similarly third. So third also you can see from 1B, 1, 2, 3, 4. Because here 3B is a gateway router. Okay. And then fourth one via 1C, 1, 2, only 2 hops. So this is the routing table of hierarchical routing. Okay, this is a table with a hierarchical routing. So how many entries are there? Only 6 entries are there. But here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 entries are there. Okay, so this is how we can reduce the entries in the routing table, and the routing efficiency will also be increased. So the only thing is that packet will be transmitted to that particular region, and that region will look over to reach the packet into the destination. Okay, similar to our postal department. So the postal department will be also working same. So for every street there will be a post office, right? For every city there will be a head post office. So automatically if a person wants to send a packet or send a post to another person in another city, first the packet will be received in the city, and from that it will be distributed to different streets, and from that street again it will be routed to the destination person. The same way the hierarchical routing will be applied. So here the communication model means the communication between two devices or two persons. So how it will be done? Okay, so in this particular computer networks, the name itself indicates, so all the multiple computers will be get connected to a network in order to share the resources. So here the sharing the resources means some sort of data transfer will be done from one system to another system. So here the data transfer between one system to another system, we call it as a communication, right? So if two persons were communicating each other, means attacking each other, so that we are calling it as a communication. But coming to the devices, so the data transfer between the devices, we call it as a communication. Now what is the basic communication model? So what are the elements? Okay, so basic communication model means data transfer from one device to another device. So this is most important, data transfer, right? So this data transfer will be done through a transmission medium, okay, through the transmission medium, and also there will be some protocols, some rules each device will be followed in order to receive or send the data. Okay, so now we'll see the complete communication model, how the data transfer will be done. So let it be, this is a sender, okay, and this is a message, or simply we can draw the receiver and the message, okay, and this is a receiver, and so this is a message, and through which the message has been transferred from sender to receiver is a transmission medium. Okay, and sender and receiver will be following some rules, some set of rules. Okay, and here also it follows some set of rules that we will be calling it as a protocols. protocols. Okay, so the complete components of this communication model is, I'll write the components. So first one is a sender. So sender may be a computer or a mobile or anything else, a device, we can call it as a device. And receiver is also a device or a computer or any mobile, anything else. And the message, so here the message can be in any format. It can be in a text format, audio format, video format, or image format. Transmission medium, that means through which the data has been transferred from sender to receiver. So this can be guided and unguided. The transmission medium can be guided transmission or unguided transmission. So guided means it is a wired, so using some wires. This is a wireless. So the data can be transferred from one system to another system or one device to another device through the wired connection or wireless connection. So there are different categories of wired connections. So example, twisted pair, using the twisted pair cables, or coaxial cables, or optical fiber, etc. Right? So by using any one among these wired cables, the data will be transferred. And coming to the unguided, this is a wireless, which will be in the form of radio waves, microwaves, and infrared. Okay, so through these channels, I mean through these transmission media, one among these things, the data will be transferred from sender to receiver. And the next one is the protocols. So the sender as well as the receiver will follow a few rules in order to send the data. That means how the data can be transmitted, or how, in which format the data can be transmitted. Okay, so these kind of rules will be followed in, from both the sender and the receiver, and that we call it as a protocols. So if that communication between web pages means a client and server, then the protocol is HTTP or HTTPS. Okay, and the second one, if we are sending some emails, then the protocol is SMTP protocol. So depend upon the data which we are transferring, the protocols may be different. Okay, but the protocol means a set of rules to be followed for the communication. Okay, so that will be done for both the sender and the receivers, because we are saying the sender and receivers are the devices. Okay, so this is the components: sender, receiver, message, transmission, and the protocols. And some models will be also be having two more, another component, that is an encoder and decoder. Encoder and decoder. So these are optional. So here the name itself indicates encoder and decoder, which will convert the data from one format to another format. Okay, so digital format to analog format. Example, I'm saying example. Okay, whatever the data we are giving, that will be in digital format, and that will be converted into analog format. So the conversion of the data format will be done with the help of these encoders and decoders. So encoder will be done during the sender side, and decoder will be done during the receiver side. Right? So this is the complete basic communication model. So in order to communicate between two devices, so these are the different components, and by using these components, the data will be transmitted from one device to another device. So it is mandatory to have all these 5 components, and these 2 are the optional components. Types of data communication. So we know that data communication means transmission of data between different devices. So that may be 2 mobiles or 2 computers, or in between a mobile and a computer, whatever it may be, the transmission of data in between the devices, we call it as a data communication, right? So for this data communication, there are 3 types. That means 3 ways we can communicate the data from one device to another device based upon the category. So without delay, let us see the types of data communication. So types of data communication. So the first one, based on data flow. The second category, based on transmission medium, and the third one based on modes of transmission. Modes of transmission. So coming to the data flow, again there are three ways we can transmit the data from one device to another one. So the first one is a simplex model or simplex communication. The next one is a half duplex communication, and the third one is a full duplex communication. So these are the three categories, I mean three possible ways to transmit the data based upon the data flow. And coming to the transmission media, there are two ways. One is a wired communication, and another one is a wireless communication. And coming to the modes of transmission, so one is a serial communication and another one is a parallel communication. So these many ways the data can be transmitted from one device to another device. So let us see one by one. So coming to the simplex. So in this simplex data communication, so the data can be transmitted in a one directional. Okay, so one directional communication. It is also called as one directional communication. So that means at a time one device can send the message. So for example, so this is a device A and this is the device B. So only a one-way communication can be done. Okay, the data can be transmitted in a single way, either A to B or B to A. Okay, so the example for this one is typing keys in a keyboard. So we will be typing the keys in a keyboard that will be displayed on the monitor. That is a one way. Okay, that's only one way. So only one direction communication, which we call it as a simplex data communication. And the next category, which is a half duplex. So in this half duplex communication, this is two directional or bidirectional communication. It is a bidirectional communication, but with one constraint, that at a time only one device can transmit data. That means at a time, so both the devices can't interact mutually. Okay, at a time only one device can communicate the data to another device. So for example, see, this is A and this is B. It is a two directional. So if A is sending the data to B, B should be idle. B should not transmit the data from B to A. Okay, similarly, if B wants to transmit the data to A, the A should be idle state. Okay, A should not transfer the data between A to B. Okay, so this is a bidirectional. Both the device can communicate, but not at the same time. So example for this half duplex is walkie-talkies. So in this walkie-talkies also only one way direction, I mean one way communication will be done at a time, at the same time. Okay, the mutual communication will be done, but not at the same time. So that is called as a half duplex. And the next one is a full duplex. Full duplex is also two directional communication or a bidirectional communication. So there will be no constraint. So both the devices can be communicated parallelly. Okay, so transmission of data can be done by both devices at the same time. So at a time both the devices can able to communicate. No need to wait until until other have to finish the communication. So this is the same thing. Okay, at a time A can transmit some data to B, similarly B can transmit some data to A. So example for this is phone calls. Phone calls. So phone calls is a simple example for this full duplex, that means a bidirectional communication. Okay, so these all the three are categorized based upon data flow. Okay, and coming to the second one, transmission medium, so which we are calling it as wired communication and wireless communication. So coming to the wired communication, so in terms of cables, okay, in terms of cables, and wireless communication in terms of air, okay, the data will be transmitted in terms of cables with the help of air. And here the examples: coaxial cables, similarly twisted pair cables, similarly fiber optics. So these three, we are using some cables in order to transmit the data from one device to another device. Coming to this one, air, which is a Wi-Fi, a Bluetooth. These are some examples. Okay, and IR, infrared rays, radio waves. So in all these examples, the data will be transmitted through wireless communication. So these two are the categories divided based upon the transmission medium, so through which the data has been transmitted towards the another device. So hope you understood, right? And the next one is the modes of transmission. Based upon the modes of transmission, so serial transmission, similarly the parallel transmission, serial transmissions and the parallel transmission. So here the data will be transmitted bit after bit, or simply we can say bit by bit. Okay, so once one bit will be transferred, and then only the next bit will be transferred. Okay, and but in the parallel transmission, so multiple bits can be transferred at the same time. Okay, so in the serial only one bit will be transferred at a time, and here multiple bits can be transferred at the same time. So these two categories are the examples of modes of transmission based upon the modes of transmission, right? So hope you understood the types of data communication. Data communication means data transfer between different devices. So that will be done based upon the data flow, transmission media, and the modes of transmission. Error in data transmission. So we know in computer networks, the data will be transmitted from one system to another system, or we can say one device to another device. So there might be a chance of getting this error. So in computer networks, what is an error? So if received data doesn't matches with the sender data, that means whatever the data we are sending is not matched with the receiver, so that is called as an error. For example, so sender sends some data like 100101, and receiver receives that the data 110101. So these two doesn't matches because here there is an error. I mean, here sender sends 0, but receiver receives 1 as an output, right? So this is nothing but an error. So here one bit has been changed. Okay, this is nothing but error. So error during the data transmission. So whatever the data we are sending from the sender, that should be received by the receiver exactly, so without any deviation. If there is any deviation, that is called as an error. So now what are the causes for getting these errors, right? So mainly three causes for these errors. So these are causes of error or occurrence of error. So why the error coming? So the first one is a noise. The next one is a interference, and the third one distortion. noise, interference, and distortion. So these are the main causes of getting the error. So the errors can be different ways, single bit, multi-bit, or burst errors. So that we'll see in our next session. But now we'll see about these three. What is a noise, what is a interference, and what is a distortion, which are main causes of error. So first one is a noise. Noise. So noise means whenever we are transmitting some data, if any data has been added to the sender data, that is called as a noise. Okay, so addition of data to existing is called as a noise. For example, so sender sends 10, receiver, so during the transmission, so this becomes one more bit has been added, like 1. Okay, this bit has been added. Okay, so receiver receives 101. So that means which is an error. So sender data doesn't matches with the receiver data. So that means there is an error. So addition of one data during the transmission is called as a noise. Okay, that is the one cause of getting error. And coming to the interference, hope you understood this noise. And coming to the interference. Interference means, so at a time multiple data will be transmitted in the channel, right, in the transmission medium. So in our previous sessions we have seen what is the transmission medium also. So that can be either guided or unguided. So at a time multiple senders will be sending the data and multiple data will be transmitted to the transmission medium through the transmission medium. So if there is any chance of overlapping the data from different sources, then we call it as a interference. So overlapping of data from multiple sources. So hope you understood. So at a time we are sending the data to the receiver. Similarly, some other person will send other data to the other receiver. So parallelly, much more of data from different sources will be transmitted to the destinations. Okay. So during the transmission, if there is any overlapping of data, that is called as an interference. So this is a one more cause for occurring the error, getting the error. And the third one, that is a distortion. So this is also called as signal distortion. So we know the data will be transmitted in terms of signals also, right? So if the shape of the signal has been changed from during the transmission, then it is called as a signal distortion. So for example, so if the data has been sent in this way, but during the transmission, if the data has been changed in this form, see, the shape of the signal has been changed, right? Even though the amplitude or the frequency will be changed. So such type of thing we call it as a distortion, signal distortion. It will change the shape, maybe due to the amplitude or due to the frequency also. So such case, the error we call it as a signal distortion. Okay, so this is the third cause of occurring error. So these are the three different causes to occur an error. So that means if the sender, the data which we are sending is not matched with the data which the receiver received, is called as an error. If it doesn't matches, then we can say it as an error. So what are the reasons of causing this error? Means due to either noise or interference or distortion. Right? So hope you understood about this error in data transmission. So I'll stop here, and in the next session we'll see what are the different types of errors. So now we have seen what is error and what are the causes. In the next session we'll see what are the types of errors that can be occurred during the data transmission. Types of errors. So these type of errors during the data transmission. So the first one is a single bit error. So there are mainly three types of errors that may be possible. So one is a single bit error. So we are saying an error means the bit has been flipped. Okay, so simply we can say error means flipped bit. So flipped bit means 1 becomes 0 or 0 becomes 1 during the transmission. So here the single bit error, the name itself indicates, so during the transmission of data, so we know the multiple of bits will be transmitted. So among the multiple bits, only one bit, if only one bit has been flipped, then that is called as a single bit error. So here only one flipped bit will be there.
or we can say only one bit is flipped. Okay, for example, if sender, so this is a sender, right? If the sender sends the data to the receiver, for example, the data is 1010, and if the receiver receives the data, okay, if the receiver receives the data like 1011, okay, this is a sender data, this is the data which has been received by the receiver. Okay, I'll write here. Okay, so this is the data sent by the sender, this is the data received by the receiver. So you can observe there is only one bit has been changed among sender data and the receiver data. So such type of error we call it as a single bit error. Okay, if one bit is flipped. Next, second one, the second category is multiple bits error. Multiple bits error here, as the name itself indicates, multiple bits are flipped. Multiple bits are flipped. For example, if the sender sends the data like 10101 and here it receives 11010, right? Yes. So here you can observe the sender data 10101. So actually the data should be reliable and without any error that data should be transmitted to the receiver. But receiver receives the data 11010. So you can see this is a flipped and this bit is a flipped and this bit is flipped and this bit also flipped and this is correct. This is correct. So how many bits have been flipped? There are multiple bits. Okay. For example, let us take yeah, so multiple bits. If more than one bit has been changed, that is called as a multiple bits error. Okay, during the transmission. And the third category, let us check with the third category. So let me tell you one more example in this multiple bits. So if the sender sends the data 11010 and if receiver receives the data like 10101, right? Okay, like this. So how many bits have been changed? 1 1. Okay, 0 becomes, this is a flipped bit. The third one, correct one, and the fourth one, again this is a flipped bit. This is a one more example. So here also more than one bit has been flipped, right? So multiple bits, if the multiple bits have been flipped, then we can call it as a multiple bits error. And the next one, that is a burst error. Third one, burst error. So here the burst error means this is also one category of multiple bit error, but here if the consecutive bits, the multiple consecutive bits have been changed during the transmission, then that comes under this category, burst error. Okay, so in the second category, multiple bits, it doesn't mean that only the consecutive bits should be flipped. So the bits anywhere can be flipped, but it should be more than one. So that we call it as a multiple. But here in the burst error, if the consecutive bits have been flipped, multiple consecutive bits, then we can say it as a burst error. So the first example we have seen in multiple bits comes under this burst error. So here the multiple consecutive bits are flipped during the transmission. For example, sender sends the data 100110. 01, right? And the receiver receives the data like 111 0, sorry, 10101. Okay, so 8 bits. Now you can observe the first one, correct? Second one, flipped. The third one, 0, and here it is flipped. Fourth one, correct? Fifth one, again here it is a flipped. And sixth one, here it is flipped. Okay, this one correct. So the consecutive bits, you can observe the consecutive bits. If the consecutive bits have been flipped, then we can call it as a burst error. Okay, burst error. So these are the different types of errors that may occur during the data transmission: single bit, multiple bits, and burst errors.
Checksum. So let us start. So here, as the name itself indicates, this is an error detection mechanism. It will only detect the error. That means whether the data which was sent by the sender
is received by the receiver exactly or not, if there is any data corruption during the transmission or not. So for this, so there are few steps involved in this checksum. So one is a sender side, another one is a receiver side, sender side and receiver side. So coming to the sender side, first it will divide the complete data into different blocks. Okay, so step 1 divides data into n blocks. Okay, divides the data into n blocks of fixed size. Okay, all the n blocks will be of fixed size. And after that, step 2, perform once complement arithmetic or addition on all n blocks. So this is not a binary addition, but it is an once complement arithmetic addition. Okay, arithmetic or addition. So that means if you add 2 bits, if you had one carry, and that carry should be again added to the LSB of that particular result. That is called as a once complement arithmetic. Okay, so for example, let us take bits 1, 0, or simply we can say 1, 1. Okay, so if you add here 1, what happens? This is a 0 and it will go here, and it again 0, it will go here and it again 0, and this is a carry bit. Okay, this is called a binary addition. This is called a binary addition. Okay, so if this happens, okay, if this happens 1, 1, 1 and 1, 0, 0, 1. So this is in this one. So this, if you apply the binary addition. So if you apply the once complement addition 1, 1, 1, 0, 0, 1, and if it is once a complement arithmetic, so what happens here? See, this is a 0 and this 1, this is 0 and this is 1, 0, and this is 1, this is a carry. So here also it is a carry. So we'll just ignore this carry if it is a binary arithmetic, and if it is once complement, this 1 should be again added to LSB of the result. So here it will be 1. So 1, 0, 0. So this will be the once complement arithmetic for these two things. Okay, if it is a binary arithmetic, this is the result. If it is a once complement, whenever the carry is obtained, that carry will be again added to the LSB of the result. So this once complement arithmetic should be applied on all n blocks. Okay, so once it was done, we will be getting the result, final result. Okay, so we'll get final sum after step 2. After step 2, we'll be getting the final result. And step 4, apply once complement to final result. So this is nothing but our checksum. Then what is the step 5? Add data, or we can simply send data plus checksum to receiver. So this should be sent to the receiver. Okay, so hope you understood this one. So first we will divide the complete data into n blocks of fixed size, and then perform the once complement addition or arithmetic on all n blocks, so that we'll be getting only one result, that is a final step, final sum, and apply once complement to the final result, which is nothing but a checksum. And now we have to add the checksum to the data, and it should be sent to the receiver. And at the receiver side, so what is the step 1? Again same, divide data plus checksum into n blocks. This is also fixed size. So the same steps, whatever the steps we have done in the sender side, the same thing. So again, perform once complement arithmetic. Okay, on all n blocks.
step 3, what we have to do? So final step. Step 3 is a final sum after step 2. Step 4, what we have to do? Apply once a complement. Apply once a complement. Okay. So step 5, this is the most important in the receiver side. Step 5, verification. Verification. So if result of step 5 is all zeros, that implies no error. So that means if we perform the sum, okay, once complement arithmetic on all the n blocks on the receiver side and applying the first complement, once complement, if you get all zeros, that implies there is no data error. I mean, there is no error done during the data transmission. And if result of step 5 is not all zeros, then it implies this is an error. There is an error. Okay, so during the transmission, some bits have been errored. Okay, flipped. Error means the flipping of bits. Right? Hope you understood these steps on sender side and the receiver side. So now we will check one example. Okay. So let us solve this example. So data here, the data block, 4 blocks are there. So in each block, the block size is 8 bits. Okay, fixed it is an 8 bits. So here you might be having one doubt that if the complete data is not able to divide it into fixed number of blocks, then you can apply the padding. So that means adding the dummy bits, zeros. So where you have to pad these 0 bits. So you should pad these 0 bits on the right hand side only for this checksum in order to find out the error detection. Okay, so that means, for example, if the number of bits are 12, number of bits are 11. Okay, number of bits are 11. Then and these bits are divided. If you want to divide these bits, okay, into 3 blocks. So how many bits you can have? Here 4 bits, here 4 bits, and here 4 bits. But unfortunately, here we are having only 11 bits. So here we will be getting only 3 bits. So what we have to do? So we have to pad 1 bit. Pad zeros on the last, that means right hand side. Okay, so that should be done. And if the number of bits are able to divide into fixed number of blocks, there will be no problem. So here there is a data. Now sender side, during the in the sender side, what we have to do? So we have to apply the once complement addition. So I am taking B1 10 10 10 10 and B2 1100 1100. So I need to use once complement arithmetic. So once complement arithmetic, this is 0, this is 1, this is 1, and this is 0, and here it is 1. So it is 1 1 1, and here it is 0 and carry. So what we have to do? We have to add the carry onto the left LSB. So now I am adding the carry here. So this is a carry. This is a carry. So 1 1 1 0 1 1 1 0. So this is the result of B1 plus B2. Okay, B1 plus B2. Now what we have to do? So I'll write here B1 plus B2. So there's a once complement. Now what we have to do? The result of B1 plus B2, we need to apply the B3. So B1 plus B2, which is 0 1 1 1 0 1 1 1, and B3, which is 0 0 0 0 1 1 1 1. Once complement arithmetic. So it will be 0 and 1, and again what happens here? 1 and 1 and 1 and 1, and here again it's 0 and 1, 0 and 1, 0 and 1, 0 and 1, and here it is 1. Okay, so if it is 3, okay, if it is 3, we'll be getting 1 and carry 1. See, I'll write here. So if it is 0 plus 1, we'll be getting 1. 1 plus 0, again we are getting 1. 1 plus 1, we'll be getting 0 and 1 as a carry. And if we are applying 1 plus 1 plus 1, we'll be getting 1 and 1 plus carry. Because see, the representation 8 4 2 1. So here it is 1, here it is 1. If it is 2, 2 means, see, 0, sorry,
1 and 0, so that will be carry. And if it is 3, 1 and 1, so 1 will be the result and 1 will be the carry. Sorry, 1 will be the result and 1 is the carry. So the same way we are applying. Hope you understood this one, right? So we are getting this one, right? So this is B1 plus B2 plus B3. Now we have to apply this one. So 1 0 0 0 0 1 1 0. So this is the same thing, right? And with this the last one. So 1 1 1 1 0 0 0 0. So 0 1 1 0 1 1 1, and here it is 0 and 1 carry. So this should be added to the LSP. So I'm adding to the LSP. How much we are getting? So here it is 1 1 1 0 1 1 1 0. So this is the result. Okay. So what's the result of B1 plus B2 plus B3 plus B4? So what is the result? 0 1 1 1 0 1 1 1. Okay, this is the result. So what we have to do, we have to apply the ones complement. After applying ones complement, after adding all these things, we have to apply the ones complement. So which will become 1 0 0 0 1 0 0 0. So because it becomes 1, it becomes 0, it becomes 0, it becomes 0, 1 0 0 and 0. So this is the ones complement. So ones complement is this one. And what we have to do, so we have to add this one to the data and it should be sent to the receiver. So during in the receiver, see again, I'm writing here B2 1 1 0 0 1 1 0 0, B3 0 0 0 0 1 1 1 1, and B4 1 1 1 1 0 0 0 0. Okay, and checksum. What is the checksum here? So whatever the result we are getting and ones complement, this is the checksum 1 0 0 0 1 0 0 0. Okay, now what we have to do, we have to again add all these things. So far we have added all these things and we got the result as this one, right? This one. And for this, if you add this one and do the ones complement, you need to get zeros. Okay, so the same, perform all the same things. So I have performed all these things here. So B1 plus B2 plus B3 plus B4. So how much we got? This one 0 1 1 1 0 1 1 1. So for this we need to add the checksum also. What is the checksum here? We got checksum 1 0 0 0 1 0 0 0. How much? 1 1 1 1 1 1 1 and 1. And we need to apply the ones complement. We need to apply the ones complement. So what? If you apply the ones complement, what we got? So all zeros we are getting. All zeros. So if we are getting all zeros, that implies there is no error during the transmission. You can observe B1 is same, B2 is same, B3 is same, B4 is same, and checksum we have said. For example, if there is any modification in this data, okay, if there is any modification in this data, let us check. See, in B3, instead of getting all 4 zeros and 4 ones, so if the data is in this way, okay, if the data is in this way, if the data is received in this, now what happens? Again, apply the same B1 plus B2. So B1 plus B2. So 1 0 1 0 1 0 1 0, and B2 1 1 0 0 1 1 0 0. So you can apply 0 1 1 0 1 1 1 1 0 1 carry. So I need to add here 1 1 1 0 1 1 1 0. Now I will add a B3 also here. So B3, I'm adding B3 also here. 0 0 0 0 1 1 0 0. How much? 1 1 0 1 0 1 0 1 0 1 0 1. I'm getting B3. Next, add B4. 1 second. 1 1 0 1 0 1 0 1 0 1 0 1, and here it is 1. Okay. Now add B4. Add B4. What is the B4? 1 1 1 1 and 0 0 0 0. How much? 1 1 0 0 1 1 1 0 and 1 carry, and this should be added here. 0 1 0 1 1 0 1 1 1 0. So this is the thing we got. And checksum, we also have to use a checksum. What is the checksum here? 1 0 0 0 1 0 0 0. We need to add the checksum also. Okay, we need to add the checksum also. So 0 0 1 1 1 1 1 and 1. Okay,
So this is the result of checksum, right? Now we need to apply the ones complement. Ones complement of result. What is the result here? So result is 1 1 1 1 1 1 0 0, and here we are applying the ones complement, which becomes 1 1 0 0 0 0 0 0. So this is the ones complement. So if we are getting all zeros, that implies there is no error corruption, right? There is no modification of error. But here we are getting to non-zero value. It's a non-zero value. So if we got the non-zero value, that implies there is an error during the transmission. You can observe in B3, in this block B3, in the sender we are having 4 zeros and 4 ones. In the receiver we are having 4 zeros, 1 1 and 0 0. That means here 2 bits have been corrupted, 2 bits have been changed. So for that reason, if you apply the same procedure on the receiver side, we are not getting all zeros. If you got all zeros, that implies there is no error. Okay, so this is how we can detect the error. Okay, the error detection can be done. That means whether any bits have been corrupted during the data transmission or not. So here it is a simple example. So hope you understood.
So HDLC, high level data link control. So this is a protocol used in data link layer. Okay, so the main design issues of a data link layer is a flow control and error control that we have already discussed, right? So flow control and error control. So the main purpose of this particular protocol is framing. Framing means if the data is more, and that data will be divided into different parts, and each part we call it as a frame. So that framing, and as we know, the flow control, error control. So already we have discussed about this flow controls and error control, right? So all these things will be managed by this HDLC protocol. Okay, and mainly this protocol will be used in transmitting the data between point-to-point communication as well as multi-point communication. Point-to-point and multi-point communication, where point-to-point communication means there will be a dedicated path between source and destination. Okay, there will be one destination and there will be a dedicated path. And coming to the multi-point, here the name itself indicates a shared link will be given to multiple receivers. The sender will be one and receivers will be more, which are sharing about the common link. So this HDLC protocol will be used to transmit the data in both the communication, that means a point-to-point communication as well as multi-point communication. And also the main feature is it supports half duplex and a full duplex mode of communication. Half duplex and full duplex mode of communication, right? Yes. Now we will see the HDLC frame, how the HDLC frame will be represented, and we'll see each and every field of that HDLC frame. So HDLC frame. So the first one, that is a framing, right? So the data, and one more, this is a bit oriented protocol. It's a bit oriented protocol. Bit oriented protocol. So we know that the lowest layer of OSI model will be the physical layer, and from the physical layer it moves on to the data will be moves on to the data link layer, right? Yes. So HDLC frame, the fields are the flag. The first one is a flag, address, control, payload, FCS, and a flag. So these are the fields available in HDLC frame. See. So here the flag represents starting and ending of a frame. So in order to recognize the starting and ending of a frame, the complete frame will be added with flag on left hand side and flag on right hand side. So it begins with the flag and it ends with the flag. And this is a fixed format. So it is 0 followed by 6 ones and 0. So here the value of flag is 0, 6 ones and 0. Here also 0, 6 ones and 0. And the length of the flag will be 1 byte. The length of the flag is 1 byte. Okay, and coming to the address, here the name itself indicates address means the address of the receiver station. Okay, so it is an address of receiver station or host, whatever it may be, the receiver from which we are sending, right, to which we are sending, right. So address, and it will also be represented with 1 byte. So sometimes it will be also the multiple of 8 bits. Okay, it usually represents 8 bits. So 1 byte means 8 bits, and sometimes a multiple of 8 bits also. And the next one is a control. So the name itself indicates it is responsible for flow control and error control, and specifically it gives types of frame, type of a frame. So this is a normal frame format. There are multiple frame formats. So the type of frame will also be represented by using this control bit. Okay, let us see what are the different types of frames here. I'm erasing this one, right? So control bit, we are discussing about the control bit. Control. So there are 3 types of frames. So I'll write here types of frames. So frame is this one. So types of frames, there are 3 categories. One is I frame, S frame, and U frame. So I frame stands for the information frame. Okay, so information frame. And this information frame name itself indicates it will send the actual data which user wants to send to the receiver. The actual data will be sent to the I frame. So whatever the frame we have drawn on the board is an information frame. So in this information frame itself, it also have the control of flow and error control. So bits represent the flow of control and error control. How to know whether this frame is an I frame or not? So the first bit of this particular control control field is 0, then it specifies this is a I frame, information frame. And coming to the next one, that is a S frame, which is a supervisory frame. So the name itself indicates it supervises the information frames. So that mainly concentrate on the flow control and error control. So sometimes it may send the data, and mostly it doesn't send the actual information. So there will be an absence of this payload here. It will only send the flow control and error control bits. Okay, so there will be no data, no actual data. So I'll write here, no data will be sent here. And how it represents, I mean, how we know that frame is a S frame. So first 2 bits are 1 0. If the first 2 bits of this control field is 1 0, that implies this is a S frame. And the next one is unnumbered frame. So this frame will give the link management. So here the link management means, the name itself indicates it will be giving about the connection establishment and connection termination. Okay, so apart from the data, actual data, it will also give the information regarding the connections. So it's a connection establishment and connection termination. So both connection establishment and connection termination. So here, how to recognize this unnumbered frame? So similar to our supervisory frame, if the first 2 bits are 1 1, that implies this frame is an unnumbered frame. Okay, and the size of this control bit will be 1 byte or 2 bytes. 1 byte or 2 bytes. Okay, and so this is about the control bit, which is mainly used for the flow control and error control. And apart from the actual data which we are sending, it will also send the information regarding the error control and as well as the link management. And our next category or next field is a payload. So the next one is a payload. So here the payload is the actual data. So payload is an actual data or information which the sender wants to send to the receiver. So that actual information we call it as a payload. So this will be the actual data which the sender wants to send. And the size of this particular payload will be a variable size. So we can't say the size of this one. It's not a fixed, it's a variable that depends upon the bandwidth. Okay. And the next one is a FCS. FCS means frame check sequence. Frame check sequence. So here the name itself indicates this will be used for error correction. Okay, so error control, simply we can say error control, because the error control itself gives both error detection and error correction. So mainly this is for CRC bits for error correction. Okay, and the size of this FCS will be 2 or 4 bytes. 2 or 4 bytes. That means either 16 bits or 32 bits. Okay, and flag as usual, whatever the flag we have included in the beginning, the same flag will be included in the end in order to recognize the frame. Okay, the starting and ending of the frame. And it is a fixed, as we said, so it is a fixed value. The flag will be 0 followed by 6 ones and followed by 0. So in both the cases, in the starting and ending, that will be appended with this one. So hope you understood the complete structure of the frame. Okay, so flag, address, control, payload, FCS, and a flag. Now, what are the modes of operation that this HDLC protocol can be implemented? So, modes of operations. So, mainly this HDLC can be implemented in 2 modes of operations. The first one is NRM. NRM means normal response mode. It's a normal response mode. So normal response mode means if there are a primary and secondary or sender and receiver, so receiver doesn't have any permission to send the data on its own until it gets the permission from the sender. Okay, simply we can say it as a half duplex. Okay, at a time only one way of communication can be done. So similarly here normal response mode, the sender will send the data and the receiver will be sending the data only with the permission of the sender. So simply we can say it is a master slave architecture, master slave architecture, until the sender gets the receiver gets the permission from the sender. The receiver can't send the information. That's a normal mode, response mode. And the second one is ABM, which stands for asynchronous balanced mode. Asynchronous balanced mode. So it is a quite opposite to the NRM. So at a time the sender can send the messages as well as the receiver can also send the messages. So this is similar to our full duplex. Okay, so here we will be calling it as a master. So both the sender and receiver will be having the same privileges. So at a time both can send the messages. Okay, so these are the different modes of operation that HDLC protocol can be implemented. So quick recall the frame structure, which is the first one is a flag which represents the starting of the frame. Address, it gives the receiver's address, and control bit specifies the type of a frame. So whether it is a I frame, S frame, or a U frame, and a payload, which is an actual data which we want to send, and FCS frame check sequence, which is used for error correction bits, and finally the flag. Once again the flag. Network layer design issues. The first design issues of a network layer is logical addressing. So logical addressing means assigning the IP address for the devices. That means to source, it also helps to identify the source and destination while we transmit the data over the network. So this is assigning IP address. To identify source and destination. That's the first design issue of network layer. So that will be done by the network layer. And the next one, store and forward packetting. Store and forward packetting. So here the data will be represented in terms of packets. Okay, so every router will store the packet and then it will forward to the next router. So we are saying that the main thing is transmitting of data over the network from source to destination. So if the data is larger than the bandwidth, then the data will be divided into different parts, and each part we call it as a packets. So while transmitting the data over the network, it have to travel through the routers. So first a router will store the entire packet and then it will forward to the next router. That is called a store and forward packetting. So packets will be stored in a router and then packets were forwarded to another router. So this is the second issue, store and forward packetting. And the third is, the main important thing is type of service. The type of service provided to upper layer. So what is the upper layer of network layer? That is a transport layer. To transport layer. So what type of service it will be providing, right? So here there are two types of services provided. So one is a connectionless and another one is a connection oriented. So connection less service, connection oriented service. So what's the difference? Connectionless service. Connectionless, the name itself indicates the packets will be transmitted independently. So packets will be transmitted independently. And also there will be no connection establishment before the data transfer. So I am erasing this one. No connection between source and destination, right? Connection, as it is a connectionless, right? So then the connection oriented, I am erasing this one. The another type of service it provides is connection oriented. So here the name itself indicates connection oriented. The packets will be transmitted in a single path. So here packets will be transmitted in a single path or same path, and also connection establishment will be there. Connection establishment will be there as well as connection termination will be there. So once the packets will be transmitted, immediately connection termination will also be there. So connection establishment and connection termination. So as it is a connection oriented, the connection is established, all that packets will be transmitted in the same path. So these are the two services provided to the transport layer. It says the type, what type of service it was providing, either connectionless or connection oriented. So that is a one more design issue of network layer. And then the next design issue was routing, most important. Routing. So routing means choosing the best path to transmit the packets to destination. So selection of best path to transmit the packet. So in order to transmit a packet from source to destination, it have to choose the best path. So there are a lot of routing algorithms will be there. So with the help of routing algorithms, this best path will be selected. Routing algorithms like shortest path, okay, flooding, link state routing, distance vector routing. So like adaptive, non-adaptive, hierarchical. So it will choose one among those in order to select the best path to transmit the packets to the routing, to the destination. And the next important point is a congestion control. One more service or one more design issue, congestion control. So what is meant by a congestion? Congestion means if more number of packets were being transmitted to the destination, there might be a data loss or a delay of receiving the packets. So simply we can say there will be a more traffic in the bandwidth. So in order to avoid that one, so there are few congestion control algorithms. So by using those congestion control algorithms, this congestion can be controlled. Okay, so the first congestion means transmitting more packets may lead to delay on receiving or data loss. So simply for understanding, I'm writing heavy traffic. So if we are traveling from one place to another place, so if there is any heavy traffic on the road, obviously there will be some delay to reach the destination. The same thing happens in the network, so that we call it as a congestion. So this is a one more design issue of a network layer. So in order to control this congestion, we'll be having some congestion control algorithms. So we can prevent the congestion control, and then that is also one design issue of network layer, right? So hope you understood the design issues of network layer, right? Routing, store and forward packetting, IP, logical addressing, congestion controls, and type of service provided to the transport layer, either connectionless or connection oriented. Congestion means having a more number of packets in the network which goes beyond the maximum capacity. So having more packets in a network beyond maximum capacity. Okay, so just an example for this congestion is a traffic jam. Okay, if more number of vehicles try to travel on the same road, automatically there will be a traffic jam, and that kind of traffic jam we call it as a congestion in networks. So heavy packets, overloaded packets will be there in the bandwidth. So what is the main cause, or what is the impact if a congestion occurs in the network? What is the impact? So obviously one is there will be a lot of delay, right? So imagine that you are traveling from one place to another place, and suddenly in the middle there is a heavy traffic jam. Obviously it will take more time to reach the destination, so there will be a delay to reach the destination. The same thing here also. The first impact is delay, more delay. Okay, so obviously there will be some sort of delay, but there will be more delay. So we can write it as increased delay to reach the destination. Okay, to reach the destination. And the second one, loss of a packet. Packet loss can also be done with a congestion. Whenever the congestion occurs, the automatically packet loss may also happens, and then automatically throughput. If there is an increase in delay, there will be less throughput. So at particular time period, how many packets have been transmitted successfully to the destination is the throughput. So automatically it will be reduced because of increased delay. So these are all different impacts. Okay, different impacts. Now we will see the principles of this congestion. So simply just remember, congestion means a traffic jam. So traffic jam of packets over the network. So let us see the principles of this congestion. Principles. So the first principle, prevention. So prevention means before the congestion occurs, we need to prevent the congestion. So we need to design the network so that the prevention should not occur, right? So design a network that avoids congestion. So how it happens means, so more bandwidth, using a more bandwidth, and using the buffers in the routers, buffer size in routers, increasing the buffer size, okay, increasing the buffer size, right? So by using all this, and also routing algorithms, using efficient routing algorithms, we have seen a lot of algorithms, right? So by using these efficient routing algorithms also, we can prevent the congestion while designing the network itself, okay? So that's the first principle. Next one is detection. Detect early. That means once the congestion occurs, so how fast we are able to detect the congestion, so that is very important. So how fast we can detect congestion once it occurs. So that means in the first principle we are seeing, so congestion, how to avoid getting the congestion, and second one, already if congestion occurs, how fast we can detect the congestion. And the next one, feedback mechanism. So this is also, once the congestion occurs, so how it can be detected and how it can be sent to the sender, because the sender will be sending the packets continuously. So regarding the information about the congestion, it should be clearly delivered to the sender itself. Sender have to know that there is a congestion in the network, right? So sender should know about congestion once it was occurred. So there are two types of feedback mechanisms. So one is a implicit feedback. So what is implicit means? So based upon few information, the sender will be knowing that there is a congestion in the network. So what happens? So based on delay, packet loss. So these are a few informations based upon these data, okay? Based upon the delay and packet loss, the sender will came to know that there is a congestion. And another one is explicit. So here the name itself indicates explicit means the nearest router where the congestion occurs, that router have to send the feedback to the sender knowing that there is a congestion. So the routers send a choke packet or control packet to sender to know about the congestion. Okay, so these are the two feedback mechanisms. So first one, prevention, second one, detection, and the third one, after detecting, how far we can send the information to the sender, right? Next, I'm erasing this one. Next, so once the packet or once the information is sent to the receiver, so receiver have to, sender, so the sender have to reduce the transmission rate. So if the sender is keep on sending the packets to the network, automatically the congestion will be more and the packets will be lost, because the routers can't handle all the packets. So some of the packets will be lost. So in order to avoid that, reduce transmission rate. So once sender came to know about congestion, automatically the transmission rate should be reduced. Transmission rate should be reduced. So obviously, then the data will be, the congestion will be slowly vanish out. And the next one, fairness. That's also more important. So many senders or many users can send the data or packets to the network. So the bandwidth should be clearly organized to all the users. So bandwidth should be equally utilized to all users. Okay, so we should not give the complete bandwidth to only particular user. So all the users should use the bandwidth equally. So that is more important, fairness. And the last one, the last principle, adaptability. Adaptability. So what is this adaptability? That means dynamically the allocation will be changed. Okay, so if network is, I mean, the number of packets are more, what should we do? Transmission rate should be decreased. That means if the number of packets means nothing but a traffic over the network. If the traffic over the network is more, automatically the transmission rate should be decreased. Okay, and similarly, if the number of packets over a network are less, that means if the traffic is very less, automatically the transmission rate can be increased. The process can be increased to reach the destination. So dynamically it have to change. Okay, so whether the transmission rate should be increased or decreased based upon the traffic over the network. So this is the called as a adaptability. So all these are the principles. Okay, prevention, detection, feedback mechanism, reduce the transmission rate, fairness, and adaptability. And congestion means heavy load over the network, so which beyonds the maximum capacity, right? So that is called as a congestion, and example, the traffic jam. Okay, so hope you got an idea about what exactly means the congestion, right? And in our next session we'll go with the congestion control techniques. There are two control techniques, open loop and closed loop, so which we have seen in our principles like prevention, detection. So those two techniques are open loop and closed loop. So in our next session we'll discuss about that congestion control techniques.
So congestion control techniques. So there are mainly two techniques that controls the congestion. So one is open loop technique, and another one is closed loop technique. So the difference among this open loop and closed loop means, open loop, this is a prevention based. That means before designing the network, so whatever the precautions we are taking in order to control this congestion is called as an open loop. And closed loop means once the design was completed and once the congestion occurs, then what type of things we have to take to control the congestion is closed loop. So here the congestion doesn't occur, but here the congestion occur, and we are supposed to take the precautions. I mean whatever the things we need to consider in order to avoid the precautions. That is a closed loop. So this is prevention based. That means designing of network itself will be controlling the congestions, whatever the things we need to consider. And here what should do if congestion occur? What should do if congestion occur? That means in this case the congestion occurs and we have to take care about that congestion. And here the prevention based. So here there will be a lot of policies we need to consider once we are designing the network. So here while designing the network, itself, there are a lot of policies. Okay, so the first one is retransmission policy. So the name itself indicates here the retransmission policy means, so once the data packet has been lost, then when and where the retransmission should be done. Okay, so we know that if the data packet is lost during the transmission, and the same packet should be retransmitted. So when that retransmission should be done is called as a retransmission policy. So all these policies will be taken before
the design of a network. And the next one, window policy. Window policy. So while retransmission of any packet, so that will be done with respect to the acknowledgement received from the receiver. So at a time, how many packets can be transmitted? How many packets can be transmitted without the acknowledgement? Because we have seen a lot of techniques like selective repeat, go back in, stop and wait, all these congestion control algorithms, right? So these kind of congestion control, these kind of protocols, while using these kind of protocols, how many packets can be transmitted without receiving the acknowledgement? So that is the window policy. Okay, and all these things we need to take care while designing the network. And the next one, acknowledgement policy. Acknowledgement policy. So we know that once a packet is sent to the receiver will be sending back the acknowledgement of received packet. So when these acknowledgement should be sent to the receiver, to the sender from the receiver. So that is an acknowledgement policy. The name itself indicates for every packet received by the receiver, it will send back an acknowledgement to the sender. So acknowledgement policy. Next, discard policy. So if a network is having a lot of congestion, automatically some of the packets will be get discarded. So which packets should be discarded? So there are a lot of parameters. So sometimes if you look about highest priority packets and lowest priority packets will be discarded, and sometimes randomly the packets will be discarded. So which packets should be discarded if the congestion occurs? That is a discard policy. And the next one is admission policy. So admission policy means, so before accepting the request, it will check whether everything is fine. So if any one of the thing is in a problem, that means either bandwidth, okay, either bandwidth or transmission rate or the current network traffic, everything will be checked, and based upon that, the new request will be accepted. So if there is any violation, automatically the request will be rejected. So that is called as an admission policy. So all these policies should be take care while designing the network. So there will be no feedback about the congestion from receiver to sender. There will be no feedback from receiver to sender in the open loop. And coming to the closed loop, so here what we are saying, what should we do if the congestion occurs? That means already the congestion is occurs in the network. That means heavy traffic in the network. Now what we have to do, right? So here automatically there will be a feedback. Here we'll see the first one is a back pressure. Back pressure. So back pressure means automatically one router will be receiving the packets from another router, right? So if the current router is in a congestion, automatically it will send a small signal to the previous router to reduce the transmission rate. And if that previous router is having the congestion, it will send one more signal to its router, okay, neighboring router, to reduce the transmission rate. So this is a chain process, and like that it will reduce the transmission rate. So if the transmission rate is reduced, automatically the congestion will be controlled. So that is called a back pressure. So one router sending a signal to reduce the transmission rate to the immediate previous router, so from which it was receiving the packets. And the next one, choke packet. So choke packet means if there is a congestion in the network, the receiver or the router will be sending a small control packet back to the sender, so that the sender will identify that there is a congestion in the network, and it will automatically reduces the transmission rate. So a separate control packet will be sent back to the sender, indicating there is a congestion. So that is a choke packet. Next, implicit signaling. Implicit signaling. So there will be no choke packets and anything. So based upon the packet delay and based upon the packet loss, so based upon the retransmissions, the sender will know about the congestion over the network. So if many packets were being lost, and if the delay of receiving the packets is more, automatically that gives a signal to the sender that there is a congestion, so the sender have to reduce the transmission rate. So that is called implicit. There is no choke packet and there is no another separate control packet sent to the sender, right? So that is the implicit signaling. So the sender will be knowing to reduce the transmission rate. And the next one, explicit signaling. So this is also similar to our choke packet. So this explicit signaling will be sending a signal back to the sender, so regarding the congestion and to reduce the transmission rate. So that is called as explicit signaling. It will be giving a control. So here there will be a feedback as well as monitoring of a network. So continuously the network will be get monitored, and immediately once the congestion occurs, then it will follow any one of these things, either back pressure, so sending a signal to immediate router, previous router, and choke packet, some control packet will be sent, and implicit signaling based upon the data loss and delay, it will be knowing, the sender will be knowing about that, and explicit signaling giving the feedback to the sender to reduce the transmission rate. So here the common thing is reduction or reducing transmission rate. So this is important, very important. So if the transmission rate is reduced from the sender, automatically the congestion will be less, right? And here, so one thing, open loop means prevention based, so congestion doesn't occur, so we are taking some precautions to avoid the congestion. And coming to this closed loop, congestion will already occurred, so what we have to do in order to control the congestion? Okay, and here there is a one more thing called a traffic shaping. So where it will be using two different algorithms like leaky bucket and token bucket algorithms. Okay, so that we will discuss in our next further sessions. So today we'll see one more concept in computer networks, that is a traffic shaping in a congestion control. So in our previous session we have seen the congestion control techniques, right? So whenever there is a heavy traffic in the network, automatically the router will be sending some choke packets and or any feedback or any acknowledgement to the sender in order to reduce the retransmission rate. Okay, so like that we have seen some techniques for the congestion control, and now we'll see the traffic shaping in that congestion control. So here mainly there are two techniques in traffic shaping, that is a leaky bucket algorithm and a token bucket algorithm. So two algorithms. So what is the procedure here? The name itself indicates the leaky bucket algorithm. Imagine there is a bucket which is filling with the water from the tap. So here the incoming, whatever the incoming packets can be of unregulated. So sometimes the transmission or the water flow will be fast, sometimes the water flow will be very low. But if the same bucket is having a small hole at the bottom, so irrespective of the content in the bucket, the flow of water comes out in an equal interval. So from that particular hole. So the same concept applied here. Here you can replace the bucket with a queue. So we'll be placing a queue so that whatever the data or packets sending from the host will be inserted into the queue. So here you can see there is some gap between the packets. So this is an unregulated flow of packets. Unregulated flow of packets. So there is no packets. That means the flow of or transmission of packets are irregular, so not in an equal interval. So we are placing some queue, and whatever the incoming packets coming from the host, that will be placed in the queue, so that the outgoing packets will be in an equal intervals, equal rate. We can say it is an equal rate. So with the equal transmission rate, the packets will be sent to the network. So this is a network. Imagine this is a network, right? So we are placing a queue in between the host and the network. So here the queue is replaced, the bucket is replaced with a queue. So this is called as a leaky bucket algorithm. So imagine if there is a flow, if suddenly the flow of water becomes very high immediately. So what happens? The water inside the bucket will be filled, and obviously the excess water will come out from the bucket. The same thing happens if there is a bursty traffic. So bursty traffic means all of a sudden transmitting a very huge traffic. So in such bursty traffic appears, immediately the queue will be filled, and whatever the packets receiving after queue filled, those packets will be discarded. So bursty traffic appears, then packets will be discarded. Excess packets will be discarded. So here this leaky bucket algorithm is not suitable for bursty traffic. Okay, and there will be a packet loss once the queue is filled, right? And coming to the second one, the token bucket algorithm, here also we'll be using the bucket, but here instead of water, here we are using the term called tokens. Okay, so for every equal interval, the tokens will be generated. For example, for every second, a token will be generated. Okay, and the tokens will be placed inside this bucket until the bucket becomes full. Okay, so here the packets were not transmitted, but tokens were generated and placing in the bucket. So what happens if the packet wants to be sent through the network? It will check for the tokens in the bucket. So if there are no tokens, the packet will not be transmitted. So if there is a tokens, depends upon the packet size. If there are enough tokens in the bucket, those tokens will be taken from the bucket and the corresponding packets will be transmitted to the network. So based upon the availability of the tokens, the packets will be transmitted to the network. So this is a token bucket algorithm. So even a bursty traffic can also be accepted here, because for every interval of time, tokens will be generated. So every equal interval of time, sorry, not a packets, tokens will be generated. So if one packet should be transmitted through the network, so it will check whether there are enough tokens or not. So if there are enough tokens, automatically those tokens will be taken out from the bucket and the corresponding packets will be set. For example, if there are only two tokens, so we are having some three packets. Okay, we are having some three packets. Sorry, this is a packets, and this is a token for every interval. For example, there are two tokens available in the bucket. So now what happens if we want to transmit the three packets? Only two tokens are available, so those two tokens will be sent out. So these are the tokens, and two packets will be transmitted to the network. So here one packet have to wait until the another token is generated in the bucket. Okay, so here also you can consider a bucket as a queue. Okay, so here you can compare these two things, leaky bucket algorithm and token bucket algorithm. So this is not suitable for bursty traffic, and this can be suitable for bursty traffic, because for example, if for a particular interval of time there are no packets to be transmitted, still the tokens will be generated and it will be maintained in the bucket. So bursty traffic can be suitable for this token bucket. And the packet loss, so here whenever the queue is full, immediately the packet will be lost. Okay, whenever the queue is full, the packet will be lost because there is no place to accommodate the packet. So obviously the packet will be lost. But here, if there are no tokens, then the packet will be have to be wait or discarded. The packet will not be lost, but the packet have to wait until a new token is generated, or it can be discarded. So that is the difference among the leaky bucket algorithm and token bucket algorithm. Okay, so whatever the input packets are in an unregulated way, okay, uninterval way. So, but the outgoing packets will be in a equal intervals. That is the main concept in this traffic shaping. So this is called as a traffic shaping. This traffic shaping is also useful in the congestion control. It will be also be useful in congestion control, right? So leaky bucket and token bucket algorithm, very simple and a small concept. So hope you understood this leaky bucket and token bucket algorithms. So here IP datagram is itself is a packet. Okay, so this is a packet which we want to transmit towards the receiver, and this is a combination of both the IP header as well as the data. So the IP header as well as data. So it is having a two fields. This packet will be having a two fields, and this is the data which comes from the higher layer, goes to the lower layer. So to that particular data we need to add this IP header. So we will be focusing on this particular IP header. Okay, now so what are the different fields that are available in this IP header? So we'll write here. So the first one is a version. The first field is a version field. So it represents which IP version it was using for transmitting the packet. Either it is a IP version 4 or version 5. So here the size to represent the version is a 4 bits. And the next one, IHL. IHL stands for internal header length. So it will give only the header length, okay, not the packet length. So packet length means both the header as well as data. But here IHL means only the header length. So this IHL, the header length will be a minimum of 20 bytes and a maximum of 60 bytes. Minimum of 20 bytes and maximum of 60 bytes. Okay, only this one, the length of this one. Okay, the length of this one. And to represent this header length, it also requires 4 bits. And the next field is type of service. So this type of service means, in our previous sessions we have studied about the quality of service. So in order to provide the reliability of a packets, I mean without any error loss or without any delay, without any jitter. So we have seen 4 parameters in the quality of service. So regarding the type of service, that based upon different type of applications, the quality, I mean the service parameters will be different. So this type of service indicates the quality of service. It depends upon the application which we are forwarding. So this type of service, in order to represent, it requires 8 bits. Next one, total length. So this total length means the complete length of IP header as well as data. This is the total length, and this is the IHL. So I'll write here. This is the IHL. This is the total length. Okay, the total length means the complete header as well as the data. So in order to represent this total length, it requires 16 bits. So actually the IP header is represented in terms of words. So this is the first word. So word means 32 bit. Okay, this is the first word. And the second word. In the second word, the first one is identification, which requires 8 bits to represent. So we know that if the data is very large, that data will be fragmented into different parts. So the packet, the fragments, each fragment of the same packet or for same data will be having the same identification number. So to identify the original IP packet, to which IP packet this particular fragment belongs to, right? So that is the identification of fragment. So it represents 8 bits. And the next one, flags. 3 flags will be there. So these flags are mainly used to know whether there is a fragmentation or not. So if the data require fragmentation, if it doesn't require fragmentation, so that will be represented by using these flags. 3 flags will be there. Okay, and the next one, fragment offset. So this indicates the current position of the fragment in the IP packet. So as we said that the complete data will be divided into segments, so that we call it as a fragmentation. So this identifies the correct position of the fragment to which IP packet it represents. So for this, it requires around so this is 16 bits and this is 13 bits to represent the offset. So this is second word. So this is a second word. So it is also 32 bit. And the next one, TLL. The one first field is a TLL. TLL means time to live. So as we have discussed in our earlier session, the packets will be transmitted from one router to its all neighboring routers. So how long the packet will be transferred or transmitted to the neighboring routers? So in order to avoid the looping, this time to live, TTL, not TLL, time to live. This time to live will be used. So initially the time to live will be set with a few number, one number, and once it visit any other router, immediately the value of TTL will be reduced by 1. So whenever the TTL becomes 0, the packet will not be transmitted forward. Okay, it will stop transmitting the packet in the network. So in order to avoid the looping, this time to live will be used. So this is 4 bits. And the next one is the protocols. So we know that every layer will be having their own protocols. So the data which we are sending in this network layer, so all this will be happens in the network layer. So the data from the network layer will be sent to the upper layers. So in the upper layer, which protocol this particular data have to be sent, that information will be available in this particular protocol. So that means higher level protocol to which the data should be sent. So here also it is 4 bits. Okay, and the next one is a checksum. Okay, so actually this is 16 bits, and this is 8, and this is 8, I think. Okay, yeah. So checksum. So this checksum will be used for error detection. This checksum will be used for error detection. So we know that the checksum, some value will be evaluated, and that will be attached to the packet and actual data, and that will be sent to the receiver. Again, the same checksum value will be calculated at the receiver side, and it will be compared. When it mismatch the checksum is done, that obviously that some data loss has been done, right? So there is some error. So in order to detect the errors, this checksum will be used. And the next one, source IP address. Source IP address, which is 32-bit. We know the 32-bit. If it is a 32-bit, we know this is a IP version 4. So this particular thing is a IP version 4 header. IP version 4 header. And this one is a third word, and this is a fourth word. And the next one, obviously for every packet, there should be source IP as well as destination IP. 32-bit. So this is a fifth word. Okay, this is a fifth word. So source IP, destination IP, and then the last one is a options. This is an options, and this is an optional field. Okay, which will be having the sender route and receiver routes, right? So optional field, this will be 40 bytes. Okay, so this is a 40 bytes, right? So this implies this is the complete IP header. Okay, IP header, not without the data. So the header length, see, internal header length will be of minimum of 20. So minimum of 20 bytes. So here you can see this is an options. Okay, this is an options and optional. So apart from this is a 32-bit. This is 32. This is 32. This one is 32, and this one is 32. So total 5 words. We can say 5 words. That means 5 into 32. So which is nothing but 160 bits. Okay, these are mandatory. These complete 5 words are mandatory. So that's why we are saying minimum is 20 bytes. 20 bytes means 160 bits. And next one, maximum. What is the maximum? If options were also there, obviously it will be 40 bytes. 40 plus 20, that will be 60 bytes. Hope you understood. This is an optional one. So apart from this, it is 20 bytes. So this is a mandatory for every packet, for every IP packet. So if you include these options, obviously the maximum size is 60 bytes. So that's why the header length will be minimum 20 and a maximum of 60. And all these things is just an IP header, only the IP header. And that data is completely different. So here we are not including any kind of data. So data is a variable size. So the IP header is this one. This complete portion is the IP header, and this complete thing we call it as a IP datagram or datagram packet. We can also call it as a datagram packet. So hope you understood this one about IP datagram or a packet, IP packet. So we are having a 5 words. Okay, each word is divided with a different fields, version, internal header length, type of service, total length, and next identification, flags, fragment offset, and time to live, protocols for the upper layers, checksum, and source IP address and the destination IP address. So here we are saying the packet will be sent to the receiver, so it requires the unique IP address, destination IP address. So once the packet has been sent, in order to perform the mutual communication, the sender will receive some data from the receiver also. So the source IP address is also mandatory. For every packet, these two things were compulsory. We need to give source IP address and destination IP address, and this is an optional thing, right? So hope you understood this IP datagram, which is in the network layer. Sorry. So quality of service. So we can call it as QoS, right? So this service means reliable communication, reliable communication. So coming to our computer networks, right? So reliable means error free, and the data should be transmitted to the receiver without any error or without any delay and everything, right? So this quality means how the network will be maintained for reliable communication. So how the network will be maintained for reliable communication. So without any errors, the data should be transmitted. So here mainly there are 4, for example, in the same house, one person is using conferencing. So he or she is in conference. So it will be a video conference meeting, and another one playing game online, another one sending email. So in the absence of quality of service, so the bandwidth will be equally distributed bandwidth, so that automatically video conferencing can have some delay, and playing the games can have some delay, and email also can have some delay, right? So in absence of quality of service, and when coming to the quality of service, it will give a priority for different applications. So video conferencing, compulsory in the video conferencing, the bandwidth should be high. Okay, the data transfer should be high. Okay, and also less delay. There should not be delay in video conferencing. That means whenever you are communicating, immediately the receiver have to get that information. So if you communicate here, after 20 to 30 seconds, if that communication has been sent, that is not a proper conferencing. That is the delay. There is a delay. So there should not be delay. Okay, there should not be delay in video conferencing. Coming to this email, so delay can be tolerated. Delay can be accepted. So what we are saying means, in order to achieve this quality of service by the computer networks, first it will prioritize the applications, so which needs the heavy traffic or which requires the heavy traffic, so for which the bandwidth should be increased, for which the delay should be reduced. So like that, it will prioritize the applications, and then the bandwidth will be distributed. Hope you understood, right? Yes. So prioritization should be done. In QoS. So which should have the highest priority? First priority will be given to video conferencing, and medium priority will be given to the playing games, and low priority will be given to the email, because here the delay is accepted. Okay, but here there should not be delay. And coming to the file sharing, if you want to share some files, so it requires a high bandwidth. So like that, there are different parameters. Okay, so in order to get the quality of service, okay, there are different parameters. So now let us see what are the parameters we need to concentrate in order to improve, or which gives the impact on quality of service. which gives the impact on quality of service. So the parameters that affect the quality of service. So the first one is a bandwidth. Bandwidth. So we know that a bandwidth, if bandwidth is more, automatically more number of data can be transferred. So even in our mobile communications also, we are using the data pack like 1.2 GB. Okay, so like that, the complete data and the speed of internet will be measured with the help of a bandwidth, where we will be saying around 30 Mbps or 40 Mbps or 20 Mbps, right? So you need to check the, you can also check the speed of internet by using internet speed test in the Google, right? So once you go through that, you can find the complete speed of data transfer. So the speed of data transfer will depends upon the bandwidth. More bandwidth, more data can be sent. Okay, so this is amount of time, amount of data transferred per second. Okay, that's called as a bandwidth, right? And the second parameter, so also the bandwidth also is one of the major parameter to give the quality of service. Okay, and the second one is delay, or we can also call as latency. Means time taken to travel a packet from source to destination. So the total time taken to send the data from source to destination, that is a delay. So in some cases the delay can be accepted, in some applications not the cases, and some applications the delay should be very less. And the next one, jitter means variation in packet delay. So we know that if the packet is of a large size, the packet will be divided into segments, and that will be sent to the receiver, and receiver may receive in a different order, but they have to reassemble them. So the variation in packet delay, so every packet will be received in different time interval, so that particular thing we call it as a jitter. So this jitter, if the jitter is more, obviously there will be no synchronization between audio and video in the video files. So always, if you download any movie or video songs or video clip from internet, or if you are streaming, so there should be a proper synchronization between the audio and the video. So if this jitter is more, obviously that synchronization will be disturbed. Okay, so the third parameter is jitter. And the next one is packet loss. So during the transmission, the packets can be lost because due to the excess of packets, or due to congestion. So whatever the reason, the packets may lost during the transmission. So how many packets lost? The number of packets lost during transmission. So these four are the parameters that impacts the quality of service. So bandwidth, delay, jitter, and the packet loss. Okay, now what are the different techniques to improve the quality of service? So all these things already we have seen, and once again we are just revising that thing. Okay, so techniques to improve quality of service. The first one is a traffic shaping. Already we have seen traffic shaping. Traffic shaping means controlling the data transmission. So controlling rate of data transmission. So how we can control this one? By using two algorithms we have seen. So the one is leaky bucket, and the another one is token bucket algorithms. So this is a one parameter or one technique to improve the quality of service. And the next one, scheduling algorithms. So in order to process the packets, we'll see the scheduling algorithms, which packet should be sent first. Okay, so by using the scheduling algorithms also, that means simply prioritizing. Okay, scheduling algorithms means prioritizing. So if you are prioritizing the applications, automatically the bandwidth will be given first preference to that application which is having the highest priority. The next one, resource reservation. So hey, as the name itself indicates, the resources will be reserved for the applications which are being come afterwards. Okay, before the application starts, some sort of resources will be reserved for that particular application prior to sending to the receiver. Okay, and the last one, admission control. Admission control. So here also the name itself indicates admission means accepting the request. So based upon the available resources, it will decide whether the request can be accepted or rejected. If the available resources are quite enough, then the request can be accepted. Otherwise, the request will be rejected. So all these things already we have seen, right? So traffic shaping, scheduling algorithms, resource reservation, and the admission control. So these are the main techniques to improve the quality of service. So 4 parameters, I'll write here again a parameters and I'll stop. The 4 parameters that gives an impact on quality of service. So which is a bandwidth, delay or latency, jitter, and packet loss. So these are the parameters and these are the techniques. So there are mainly 4 protocols which will be used in the part of IP. So that is a network layer, in the network layer. So one is ICMP, so which stands for Internet Control Message Protocol. Next, IGMP, Internet Group Management Protocol. ARP, Address Resolution Protocol, and RARP, Reverse Address Resolution Protocol. So mainly these will be used for controlling the messages, control messages. So for example, this ICMP will be used for sending error messages, and this IGMP is used for multicasting. So multicasting means sending the information in a groups, and this ARP is used for converting IP address to MAC address, and this RARP used for converting MAC address to IP address. Okay, so the data will not be sent in these protocols, in any one of these protocols. Now today we will concentrate on the first kind of protocol, that is Internet Control Message Protocol. So we'll see the remaining things in our further sessions. Okay, now let us start the first thing, ICMP. ICMP stands for Internet Control Message Protocol. So this mainly used for sending error messages. So error reporting, network troubleshooting, or connecting devices. These are all simple functionalities of this ICMP. So let me tell you in clear. So if sender sends the data to the receiver, and due to some reasons receiver doesn't receive the data which was sent by the sender, so then the router where the problem arises, that will send some message to the sender related to the issue. So that kind of things will be take care about this particular protocol called ICMP protocol, right? So that's why we are saying it is a error reporting, and also the network troubleshooting. So whatever the reason it may be, so whatever the problem it may be, so that will be sent to the sender. And similarly, connecting the devices, it will also know whether the device is active or not. So these are the main protocols. And one more, actual data will not be transferred. So only the error messages or troubleshooting messages will be sent, but the actual data will not be transferred, in this one. Okay, now, so what kind of messages it will be sending? Okay, what kind of messages? So actually this particular thing will be sending the ICMP messages. So let me write the complete steps. Okay, so step 1, sender sends the data packet, and step 2, due to some reason packet have not reached destination. Immediately step 3, the router where the problem occurs will send ICMP message to sender. So this is the steps it will done, right? So maybe due to congestion, okay, the data may not be received to the destination. At the same time, so where, in which router the problem arises, that router will be sending this ICMP message. So it will be having 4 fields. One is type, which gives the type of message. So whether it is an error message or it is a status of the network. Okay, the type of message. Code, some additional data, additional information regarding the message. And checksum for error detection. So here, see, we are saying it is a error detection, but it doesn't mean that actual data is transmitted. So whatever the information is transmitted, for that the error detection will be applied. And then, so data, so information regarding original packet. So the message, ICMP message, will be having all these 4 fields. Right. So let us see what are the different messages, ICMP messages. ICMP messages. So there are a lot of messages. Okay, so let us see a few. One is echo request. Okay, so this message to know the status. Example, you can use a ping in order to check the connection. The command ping to check the network connection. So just try this one. So just go to the run command, okay, in your system, and apply this ping, so that some request will be sending to the server, and at the same time the response will be getting. Okay, you can try it at home. Use the thing ping followed by, you can write a google.com. So request and response, it will check the status whether they are alive or not. Okay, and I'm saying it's a request and response. The response is an echo reply. So response for the request. Okay, so just try with this one, ping google.com, whatever the website, not a google.com, you can use any website. So it will check the status, it will send some data, and it will get the response. And destination unreachable. So when we will be getting this message, the name itself indicates, so the data have not received or have not reached the destination. So if the data is not reached to the destination, then automatically we'll be getting this one. And time exceeded. Time exceeded means the time to live. So it gives when the TTL, time to live, has expired. So we have studied about this time to live. So time to live means So how far the packet should be transmitted or routed in the network. Okay, so before reaching the destination, if the TTL of any packet has been expired, then automatically the packet will not be moved forward. In that situation, this particular thing will be applied. Okay, next, parameter problem. Parameter problem, when this one means there is a problem with a header. Problem with a header field. So header field is very important in any aspect, because header field itself will be routing the packet towards the destination. So here we are giving the IP addresses, MAC addresses, etc., etc. in the header field itself. So header fields is very important. If that header field was not properly given, this kind of things will be sent. This is the ICMP message. Okay, if the header field is with a problem. Okay, parameter problem. So these are very few messages. So like this, the messages will be sent if there is any problem with the packet or in the network. So that's why we have said that network troubleshooting is also one functionality of this particular ICMP. And this protocol, ICMP protocol, works with internet protocol. So that's why we are saying internet control protocol. All these will be working along with the internet protocol. So why these control messages means, mainly this IP protocol is unreliable. So it will be using the UDP, connectionless. So if it is a connectionless, automatically that is an unreliable. So there is no guarantee of sending the packet to the destination. So that's why. So this control message protocols, group management protocols, ARP, and all these things comes under. Okay, so this will be taking care about the error messages, the ICMP, Internet Control Message Protocol. It works with the Internet Protocol, and this is a network layer protocol. All these are network layer protocols. So IGMP stands for Internet Group Management Protocol. So what is this group management? So we have seen different kinds of communications. In that we have seen a unicast communication, multicast, and a broadcast. So in that, what is a multicast? So multicast communication means, so sending messages, sending the data to multiple devices simultaneously. Okay, so sending the information to the multiple devices simultaneously. Best example is a video live streaming. So the live streaming can be accessed to the different devices. Okay, so sending data to multiple devices is simultaneously is called as a multicast. This main IGMP protocol is mainly, it is a network layer protocol, because we are discussing about the network layer protocols. So it is a network layer protocol mainly used for multicast communication. Okay, so here the communication will be between, so this protocol will be used between the host and routers, not in between the routers and not in between the host. So it will be used in between a host and routers. So how it will be used? So here the host sends the message to the router telling the willingness of receiving the data. So here the host will send the IGMP message to the router that that particular device is ready to receive the message or to involve in the multicast group. Okay, so it will send the message. Here the message is nothing but our IGMP message. Okay, so the main functionality, the main functions of this particular IGMP are so managing entry and exit from multicast groups. So this main function of this HDMP protocol is for managing the entry and exit from the multicast group. So what entry and what exit? So the device or host, okay, it will allow the host to entry and exit from the multicast group. Now we'll see functions. What are the functions of this particular IGMP protocol? So mainly it is having the three functions. So the first one is joining the group. Joining the group. So here, as the name itself indicates, the host sends IGMP message to the router. So everything will be done by the router. So it will send the IGMP message to the router to receive data in multicast group. So automatically the router will add this particular host to the multicast group. And the second functionality, leave the group. So here also the name itself indicates. So the host gives the information, or router removes, that means exits, removes the host from the group if host doesn't want to receive the data. Okay, so joining the group as well as leave the group. Joining means the host wants to receive the data, so it will give the request message to the router to add that particular device to the multicast group. And if the the device or host doesn't want to receive the data, so the router will remove that particular device from that multicast group. And the third one is a membership management. So here the name itself indicates the router keep tracks all the active members. Here members itself is a host, active members in the group. So it will maintain the active members who are ready to receive the message. So these three are the functions of this particular IGMP protocol, Internet Group Management Protocol. Right? So we'll see the steps, the working of IGMP protocol. Okay. Simple. Whatever we have seen so far, that itself is a working of IGMP. So working. So the first step, host sends the membership report. To router. Okay, this membership report itself means the host is ready to receive the messages sent in some multicast group. So the router immediately adds this host to the multicast group. Next, router sends query message. Okay, to all the hosts. So it will send some message to host to identify which are active and which are not active. That means which wants to receive the data and which doesn't want to receive the data. And for this particular query message, if host replies to query message, implies still host wants to receive the message, wants to stay back in multicast group. So it will wait for this message. Okay, so the router waits for the host reply. If router gets the reply from the host for this query message, that implies host still wants to be remains in the multicast group and wants to receive that data. And if no reply, so that indicates host doesn't want to receive the message in multicast group. That means the host doesn't want to continue in the multicast group. So immediately the router will remove that host from the multicast group. So this happens. This is a working. Okay. The main functionality of IGMP is to manage the host which wants to receive the data, which wants to add or leave from the multicast group. So mainly this protocol is used for multicast communication. In the multicast communication. So one example just now I have said for this multicast communication is live streaming. Okay, so those who've registered for that particular router, they can only be available to receive the data in that particular group. So this is the IGMP protocol, Internet Group Management Protocol. It's a network layer protocol. ARP, so which stands for Address Resolution Protocol. So here the name itself indicates address resolution. So address should be changed. So what kind of address? So this address resolution means mapping of IP address to MAC address. So we discussed in the earlier sessions like IP address is a logical address and MAC address is a physical address. So for every physical device there will be a unique MAC address. So it will not be changed. But coming to the IP address, that's a logical thing. Okay, so the IP address can be changed. So the mapping should be done between IP address and the MAC address, and this mapping will be done by using this address resolution protocol. So here discussing about IP address and a MAC address, we know that IP address is in a network layer, and MAC address is in data link layer. So that means this address resolution protocol works in between the network layer and the data link layer. Okay, so ARP, that is the address resolution protocol, works in between the network layer and data link layer. See, in order to receive the data or send the data, the sender have to know both the logical address and the physical address. So only knowing the logical address is not sufficient to send the data to the destination. So the sender have to know both logical address as well as physical address. So just now we have seen what is a logical address. Logical address means IP address already that will be done in the network layer and it will be routed. The packet will be routed in the network. So now the packet comes to the local area network. So it will be routed to the correct local area network where the destination system resides. Okay. So logical address means IP. Physical is a MAC. So what happens? So immediately whenever the data, so knowing about the IP address, the packet will be routed to the LAN in which the IP address is available. So here in order to receive the data, the sender have to know the MAC address. So because the MAC is a physical address, so that gives the exact computer or exact device to which the data has to be transmitted. So that will be done by this address resolution protocol. So we'll see how it will be finding the MAC address after reaching to the LAN. So this ARP will be working on only within the LAN itself, only within local area network, right? So let us check what is the procedure. Okay, how the packet or how the sender knows the MAC address of the destination. So it will send a few messages. So first the sender reaches to the LAN. Okay, the sender sends the packet and it will be reached to the LAN because it knows the IP address. Now sender sends ARP request. So this is important. It sends the ARP request. Okay, so which is a broadcast message. So I think all of you know about the broadcast message. That means sending the message to every device which is connected towards the LAN. So that is a broadcast. Every computer, the same message will be sent to the every computer that has been networked in the LAN. So it says, this request says, So tell me the MAC address which IP address is some 192.168.10.1, for example. Okay, let us take one simple IP address. So this is the ARP request. What's the ARP request? So the sender sends the ARP request to everyone, so broadcast. So like a similar kind of message like tell me the MAC address, which IP address is, which system is having the IP address. So which system is having IP address so and so. So it was asking about the MAC address. So now I am having some IP address. I need to know the MAC address. So what happens? Immediately the system, the destination system responds to sender by giving its MAC address. So obviously one system, the destination will be having the MAC address and that particular IP address. So that particular system will respond to the sender, so for this message, by giving its MAC address. Okay, so this is a unicast. This is a unicast. That means it will send only one message, okay, to the sender. So here this is called as a ARP reply. So first one is a ARP request. ARP request is a broadcast message, and ARP reply is a unicast message. So it will respond to the message which was sent by the sender. Next one. So once the MAC address was there, what happens? Immediately the sender stores the MAC or the mapping. So here mapping means IP address to MAC address, mapping into ARP cache. So similar kind of table, okay, table which consists of all the IP addresses and MAC addresses. So the mapping will be stored in ARP cache, because if it wants to send one more message, it doesn't require this broadcast and unicast. Directly it will check with the ARP cache and it will send the message directly to the destination. So actually this is the first step. That means the first step is sender checks mapping in ARP cache. So first whenever the sender sends the data and it reaches to the LAN, immediately it will check the mapping in ARP cache. If it is there, directly the data will be sent to the destination. If it is not there, then the ARP request will be sent, and then ARP reply will be there, and then the mapping will be done, and now data transmission will be done. Now the data transmission will be done. Okay, right? So I'll write the steps, don't worry. So this is the step 1. I'm extremely sorry because I have written the steps in a jumbling order. So step 1, sender checks the mapping in the ARP cache. If it is not there, then step 2, sender sends the ARP request, and step 3, sender gets the response. And then step 4, sender stores the mapping into the ARP cache, and step 5. See, very important, just observe the steps. Okay, so step 1, step 2, step 3, step 4, and step 5. This happens in the ARP. Now there is a mapping between IP address and the MAC address, so the data will be transmitted from source to destination. So very important point, in order to send the data in the network, it requires both logical address and physical address. So logical address is used to reach the local area network, and in that local area network, in order to find the device, so it requires the MAC address, right? So this is about our address resolution protocol. And there is a one more protocol, very simple protocol, that is a reverse address resolution protocol. See, hope you understood this one. So just take care about these steps 1, 2, 3, 4, and 5. Now so this is how the data will be sent to the destination. So it requires both IP and MAC. Now the next one, very small protocol, which is a RARP. So RARP means reverse address resolution protocol. So what it happens means, now the device is having the MAC, but it doesn't know the IP address. Okay, the reverse of the ARP. So system know the IP, sorry, know the MAC, but don't know the IP address. So this case is called as a reverse address resolution protocol. Okay, so getting the IP address by knowing the MAC. So here, sorry, the system sends a RARP request. So here also the same request, which is a broadcast, so it will be sent to everyone in the network. So telling this is my IP, sorry, MAC, this is my MAC address, what is my IP. So this kind of message will be sent to every device. Then server checks with a database for mapping and responds to the system. So this is a unicast. So this is a unicast, which is also called as RARP reply. This is a unicast. So in this way, the system will be knowing about the corresponding IP address. Okay, so the address resolution protocol and reverse address resolution protocol. Okay, so I think all of you understood about this concept, very simple and a very important concept. So this is also, these two protocols comes under the internet control protocols. So we have already seen 4 protocols so far: ICMP, IGMP, as well as ARP and RARP. So these are the 4 protocols comes with the internet control protocol. So transport layer services provided to upper layers. So the first one is a process to process delivery. The first service is a process to process delivery. So this process to process delivery means the data should be transmitted from application to application. So here, for example, we are using an email to send the data, and at the recipient also will be using the email to receive the data. So here sending will be done and here receiving will be done, but both are using the same application. So application to application delivery of data. So how these applications can be identified, and these applications can be identified by port numbers. For every application there will be a port number. So with the help of port numbers, the applications will be identified and the data will be transferred between the applications. And the next one, segmentation and reassembly. Segmentation and reassembly. So here the segmentation and reassembly means if the data is beyond the bandwidth, so the data cannot be sent at once. Okay, so sometimes this happens. So if in that case, that means if the size of the data is beyond the bandwidth, so automatically the complete data will be divided into different parts. So that we call it as a segmentations. So data is divided into small parts, which we call it as a segments. Okay, and in order to identify the segments, okay, because at the receiver side again these segments should be assembled to get a proper message. Okay, so in order to group these segments at the receiver side, so it will be using some sequence numbers. Okay, so sequence numbers will be used. Sequence numbers will be given to segments, each segment. So what is the purpose of giving this sequence number means? It will be used for proper reassembly at the receiver side. So segments will be assembled to get proper message. So we are sending the data to the receiver, so the data should not be lost. So here in the sender side, if we are dividing the data into segments, obviously at the receiver side all the segments should be reassembled, so that the same data should be appeared at the receiver side. Okay, so that will happens, and here the major role is the sequence numbers in order to reassemble the segments. So we need to order it. Okay, and the next one, connection control. Connection control. So here there are two kinds of connection mechanisms. So one is a connectionless, another one is a connection oriented. So connection oriented. So anything it can be used, connection oriented and connection less. So coming to the connection oriented, obviously there will be reliable data transfer. It's a guaranteed of delivery of packet. So reliable data transfer if it is a connection oriented, right? But in case of connection less, there is no guarantee of receiving the packet. Okay, but fast transfer. So fast transfer will be there. Fast transfer of data will be there in a connectionless, but reliable data transfer will be coming from the connection oriented. So two kinds we can use, connection, either connection oriented or a connection less, right? So next, flow control. So already we have seen a different flow control mechanism. So in order to maintain the sending speed and receiver speed, so the transmission rate should be reduced. So transmission rate should be reduced. Okay, so this will be done with the help of sliding window protocols. So already we have seen in this flow control, we are using sliding window, go back in, selective repeat, so such kind of protocols. Okay, sliding window protocols. So these sliding window protocols will be used to control the flow of data. Next, error control. So obviously if you are trying to send the data from source to destination, there might be a chance of losing the data. So the data can be corrupted also. So error correction. So how the data, I mean how the error will be corrected, how the corrupted data can be received. That means retransmission. So we can use a retransmission of packets. So this also already we have seen, retransmission of packets. So some packets we have seen the choke packet. Okay, choke packet will be there, a separate packet which gives the status of the current traffic. Okay, so like that, based upon the choke packet, the data will be retransmitted. So that will be a combination of congestion control and error control. Okay, so how we can, so it also detects the error, so already we have seen the error mechanisms. So to detect that one, checksum, okay, CRC, right? So all these methods we can detect the error. And congestion control. So here the congestion control means controlling the traffic over the network. Okay, so controlling the traffic over the network. So in that also we have seen a lot of mechanisms, right? So we have to use a lot of mechanisms of controlling the traffic. So just now I have said one example is a choke packet. Okay, and automatically giving the status, the router will give the status to the sender. Okay, slow down the process. It also slow down the process, that we call it as a back pressure. So from which router it receives the packet, that will be slowed down, right? So by using all those techniques, the traffic should be controlled. So there should not be collision. Okay, traffic should be controlled with no collision. So I'll post the link of the complete computer networks in the description box, so you can check out exactly. Okay, so more number of algorithms we have discussed earlier, right? So I'll post the link in the description, just go through that. So traffic control should be traffic should be controlled with a no collision, then only there will be no collision, no congestion. Okay, and multiplexing and demultiplexing. This is related to our first thing, process to process delivery, multiplexing and demultiplexing. So coming to the multiplexing means, it doesn't mean that only one data or one application will be using at a time, right? So there is a chance that multiple applications will be communicated, right? So the data can be transferred. Okay, the data can be transferred. That means email, we can use an email or we can share the files. Both can be done at a time. So in such case, we have to collect the data from multiple applications, and it forms a single data, and it will be sending to the receiver. And while receiving, while reaching to the receiver, again the complete data will be divided into different parts, and it will be reached to the appropriate applications. So that is called as a multiplexing and demultiplexing. See, for example, so transport layer, let us take. So here different applications, it forms a single thing and it will be sent, and from again on the receiver side, whenever it goes with the transport layer, one data will be sent, and from here again the data will be divided and it will be forwarded to different applications. So here different applications it seems. So here the different applications means how it will be identifying the correct application, right? So that will be depending upon port numbers. For every application there will be a port number, right? So based upon the port number, the data will be reliably sent to that particular application. So when we are using an email, whatever the data we are emailing, that should be received to the email only here. Similarly, if we are sharing one file, that file will be shared with receiver itself, right? So application to application, what I have said just now, so this is a similar to our application to application, that means a process to process delivery, right? So this is a multiplexing and demultiplexing. So all these are the different transport layer services provided to the upper layer. Okay, so process to process delivery, segmentation and reassembly, connection control, flow control, error control, congestion control, and multiplexing and demultiplexing, right? These are all services. And now we'll see the transport layer primitives. So what exactly means these primitives? So these primitives are nothing but commands which are being used for communication between two different systems. Okay, so we'll see what are the primitives and what is the usage. So let's start the session. So transport layer primitives. Transport layer primitives. So what we said, primitives are commands. So these are nothing but commands, or we can also call as operations. So what's the use of these operations? So these commands or operations are used to communicate between two systems, that means a sender and receiver. Okay, so these particular commands or operations are used to establish the connection. So first a connection will be established, establishing the connection, sending and receiving the data, send and receive the data. So this is done in between two different systems. Now what are these primitives? So let us see what are these primitives. So primitives are, first one, listen. So I am writing all the primitives with capital letters. I am representing with the capital letters. So because we are calling them as a commands or operations, so you need to write them in the capital letters itself. Listen. So this will be done by the server. So what exactly means this listen means the server is able to accept the connection. So it was inviting the connections from the client. Okay, so let us take these two systems as client and server architecture. Example, client and server. So as we know, the client will send the request to the server and server will respond. Okay, so here this is done by the server, and the server will be waiting for the connections from the client. So waits for the connection from clients. So example, you can take a website. So the website, all the web pages related to that website will be kept in a web server. Okay, cloud. So that will accept the request from different clients. Okay, so here also similar. Listen means it is done by the server and it will wait for the connection from the client. And the next one is connect. Here the name itself indicates the connect means it is done by the client. It is done by the client. That means it wants to, it sends the request to the server. Okay, it sends the request to server. That means ready for communication. Ready for communication. So that means connection establishment. Connection establishment. The connection establishment will be done in the connect method. Okay, connect operation. So which is done by the client. And the next one, once the connection was, I mean, the request has been done, then accept. What does it mean? Accept means who will do this? This is done by the server again. This is done by the server. What it will do? So whatever the request it gets from the clients, it will be accepting. So accepting the request from the client. So here it will accept, so it will be connected to the client. So accepts the request came from clients. It will accept. So ready for communication. So this is a ready for communication. So connection here establishment. So here it is not an establishment, connection request. We can say it as a connection request. It's a connection request, and here it is a connection establishment. So once the server accepts the connection, so connection establishment will be done. Connection establishment. So once the connection is established, what happens? Now both the systems are ready to share the information. So send and receive. I'll erase this one. Okay. So listen, connect, accept, and send. So the work is done by either client or server. So both, because client and server are ready to send the information. So whatever the, if the client sends a request, so that means the client is sending some information to the server, and whenever the server gives a response to the client, that also means the server is giving some data to the client. So request and response means sending and receiving the data will be done from both the sides. Both the sides means it will be receiver and sender. So client and server. So send means send data to client, send data to server. So it will be done by both client and server. And the next one is receive. Receive means here again the name itself indicates it is accepting the messages. Okay, so when sender sends the data, the receiver will accept the message. So receiving data from server as well as receiving data from client. So both sender and receiver, I mean send and receive, will also be done by both the client and server. This is done by both client and server. And the last one is terminate. So once the sending of messages was done, automatically disconnects the connection which was established. Disconnection. Okay, disconnects the connection which was established between the client and server. So these are all the primitives. Okay, transport layer primitives. So these transport layer primitives are used for establishing a connection between two systems, and also to send and receive the data between two systems. Okay, hope you understood this one. So these are all the primitives. The first one is a listen, next connect, accept, send, receive, and terminate. Elements of. So first I'll list out all the elements, and then we'll see what is what. The first one is a addressing. So that means the data should be reaching exactly to the target application. So here we said one of the service of transport layer is a process to process communication. So the data should be shared to the correct application. So that is important. Next, connection establishment. Connection establishment. So this already we have seen in our previous session, that is a primitives, right? Connection establishment. Next, connection release after completion of sharing of data. Connection release, and all the remaining are same, which is a flow control. So in order to reduce the data transmission rate by using sliding window protocols, and error control. So first the error should be detected by using different detection mechanisms like checksum, CRC, Hamming code, like that, and we need to send the data reliable in a reliable format. That means without any error the data should be reached to the destination. And the next one, multiplexing. Multiplexing means we need to accept the data from multiple applications at a time. So only multiple applications can be run in the system, so that for multiple applications the data should be transferred without any error. So that is called as a multiplexing. So multiple sources, allowing the data from multiple sources. So these are all the elements of transport protocol. So I'll be concentrating on addressing connection establishment and connection release, because already we have seen all these things in our services, okay, services of transport layer. Now coming to the first one, that is addressing. So as I said that the data should reach the correct application. So what we are saying is application to application, the data will be sent from application to application. Example, let me take you an example. So let us, an application is an email, okay, and parallelly we are using some WhatsApp. So the destination is also email and WhatsApp, right? So whenever you send an email, okay, sending an email, send email and send some data, send data through WhatsApp, okay. So this is a system 1 and system 2. So S1 and S2, system 1 and system 2. So what should be done? So send email to S2, send data to S2. So from S1 to S2. So what happened? This email should be sent to this email in the second system only. So the email should not be sent to WhatsApp of the second system. Emails should be sent to the email of another system. Similarly, the WhatsApp should be sent to WhatsApp on another system. So WhatsApp, whenever we are sending some WhatsApp message, it should not go to email of the other system. So application to application. So what application we are using in the system 1, the same system, same application should be used in the system 2. The data should be received there. Okay. So how it can be identified? So with the help of a port numbers. So we know port numbers for every application. There will be a port number. So identifying the port numbers, the data will be reaching towards the correct destination. See, so far we have seen the data has been reached to the system, okay, reached to the LAN through a IP address, and after that it will verify the MAC address. It will check the MAC address to identify the device in the LAN to which it have to be entered. So after that, in that particular system, it need to identify the port numbers to which the data should be sent. Okay, so IP address to identify the LAN network and system, and in the LAN, MAC address is a physical address to identify the device, and port number is used to identify the application. So for every application there will be a port number. So this is how the addressing will be done in transport layer. Next, the second one is a connection establishment. So we have seen the different primitives, right? Connection establishment. So before sharing the data, first the connection should be established. After connection establishment, then only the data will be shared between two different systems. So connection establishment means here, so what happens? Let us take a client and a server. Let us take the two systems as a client and server. So this is a timeline. Okay, this is a timeline. So first the client will be sending one synchronized message, SYN, synchronized message. Okay, in order to, that means it is ready to connect with the server. So initially what we have studied is server will be in the listen phase. So listen primitive means the server will be ready to accept the request from the client. Then connect will be done. So connect means this one, the synchronized message will be sent from client to server, and here the sequence number will be also sent to the server. Sequence number. okay, in order to get the acknowledgement. So sequence number is very important. And after receiving this one, the server once again sends a response that is an acknowledgement which is x plus 1 and also one sequence number y. So this is a sequence number of server and this is a sequence number of client. Okay, so first synchronize message, that means I want to connect with you, I want to share the data with you, so please establish a connection. So like that, a message will be sent to the server, so with the sequence number. So for that, the acknowledgement will be done. For which acknowledgement is done? X plus 1. Previous message is x, the sequence number is x, so x plus 1 is the acknowledgement given from the server to client. Along with that, it will also send the sequence number of server, that is a y. Again, the client will send one more message, that is an acknowledgement with y plus 1. So then it is nothing but ready to send the data, ready to share the data between client and server. So three messages will be sent for connection establishment. One is a synchronization and acceptance with another synchronization, and again the acknowledgement. So two acknowledgements. So server will acknowledge the client and client will acknowledge the server. So here three messages are there. So that's why this is called as three-way handshake. Three-way handshake. Three-way handshake. So three-way handshake, after completion of these three messages only the connection will be established. So once the connection is established, then both the systems are ready to share the data. So the next primitives are send and receive. So those two will be active stage, right? So this is a connection establishment. So once the connection was done, the data will be shared among the client and server or two systems. And after completion of that, the next one is a connection release. So we need to release the connection. Okay, once the connection is established, why the connection is established means to share the data or to share the resources. And after completion of that, why we have to release the connection means we need to release all the resources which are being holded during the connection. So connection release is must and should. So how it will be released? Similarly, similar to our connection establishment, there will be a client and there will be a server, and there is a timestamp. Here there is a timestamp. Okay, so first the client will be sending a message to the server with a message called fin. Fin stands for finish. So that means the client wants to say to the server that I am done with my all requests. So the communication was done. Okay, about to close. For that, the server will be giving a response, that means acknowledgement. Okay, acknowledgement to the message given by the client. So similar here also, you can give a sequence number with x, acknowledgement with x plus 1. That is done. And once the acknowledgement was done, again the server will send one more message to the client to accepting the finish. So this is also finish. Now the server was sending a finish message to the client, so that okay, I am not able to receive any more messages from the client, because client first sends the finish message. And here again it may also send the sequence number y. Again the client will be sending one more message called acknowledgement of the message, for acknowledgement for the message sent by the server. So acknowledgement of y plus 1. Y is a sequence number given by the server. So acknowledgement y plus 1. So here, in order to release the connection, it needs a 4 messages. In order to establish the connection, we have seen 3 messages. So here it requires a 4 messages. So that's why this is called 4-way handshake. 4-way handshake. So 3-way handshake is to establish the connection, and 4-way handshake is to release the connection. Okay, right? So mainly these three. Apart from these three, the flow control, already we have seen the sliding window protocols. So the same concept, in order to reduce the data transfer, we are going to use the flow control. And coming to the error control, error detection will be done by using different techniques like checksum or CRC, like that. So it will be done. And also multiplexing. So at a time, multiple applications can send the data. So previous example we have seen email and WhatsApp. At a time, both the applications must use the internet, so that some type of data will be shared at a time. So email sharing one data and WhatsApp sharing another data, right? So that is called as a multiplexing. So accepting the multiple inputs from multiple applications, and make sure that the correct data should be sent to the correct application. So the data should be sent to the correct application. So this is the elements of transport protocols. These are all the elements of transport protocols. UDP protocol. So UDP stands for User Datagram Protocol. User Datagram Protocol. So here the datagram means it is a data transmitted in connectionless network. Connectionless network. So we have seen two different types of networks, that is a connection oriented and connectionless. So in the connection oriented, so we are supposed to establish the connection before sending or receiving the data, but here it doesn't require. So datagram means data which is transmitted in a connectionless network is called as a datagram. So we should not call it as a packet. So as we discussed it just now, it is a connectionless protocol. So connectionless protocol and transport layer protocol. It's a transport layer because we have seen one service in the transport layer, that is a connection control. So two types of connections, connection oriented, connectionless. So transport layer protocol. So what are the characteristics? What is the use of this protocol? So it is a very fast protocol. It's a very fast. Okay. So fast delivery of packets. Fast delivery will be there, but there is a one drawback, which is no guarantee of delivery. Okay. So no guarantee of delivery. So it will deliver the packet very fast, but there is no guarantee of reaching the destination, and also may not reach in same order. So whatever the order we are sending from the sender side, the same order it may not reach at the destination. So this is also one point. So majorly this UDP is used to transfer data between the devices very fast. Okay, so it is a very fast one, but no guarantee of delivery and may not reach in the same order. So that's why we call it as a unreliable. So because we are not giving a guarantee of delivery, so unreliable. It's an unreliable protocol. Okay, so here the datagram, whatever you are saying it as a datagram, will be having two parts. One is header, another one is a data. So here the data may be in the text format, in the image format, in the video format, or in audio format. Any kind of information can be passed, right? So that can be any kind of data. So this is the data, and for that data some header will be included. So what are the different fields of the header? Okay, let me tell you. So the fields of a UDP header, so we call it as a UDP header. So the first one is source port number. So in our previous session we have discussed about port number. Port number means to identify the particular application. So source port number, destination port number. So both must be included. Destination port number, total length, that means including the header as well as data. So here total length means header and also data, both will comes under the total length. And the next one is a checksum. So here these are the four fields involved in the UDP header. So it occupies some 16 bits or 2 bytes. So it occupies 6 bits, and here also it is a 16 bits, sorry, 6 bits, not 16 bits, and this is a 16 bits. Okay, so that means 32 bits, that means 2 words we can say it as. So the importance of source port address means from where the data has been sent should be known. So that's why the sender port number, it means it will identify the application, from which application the data has been sent. Similarly, the destination port number means at the destination side also to which application the data have to be received. So we have seen in our previous session the services like multiplexing and demultiplexing. So the data from multiple ports or multiple applications can be combined and the data will be transferred to the destination, and at the destination itself again the multiple data will be divided to different applications. So here the destination port will be identifying the destination application, that means to which application the data has to be transferred. And total length means the header length as well as the data length. Always the data length will be a variable that depends upon the system, so it will be variable, but header length is fixed. And checksum, here the name itself indicates that checksum means error detection. So it will check whether any error occurred during the transmission of data or not. So that will be done. Okay. So retransmission is not possible here. Acknowledgement is not there. Retransmission is not there. So only checksum. That means once data is received at the destination, it can have, or it can identify whether the data has been modified or not by calculating the checksum at the destination and comparing the added checksum into the datagram. Right. So these are the only 4 fields which are available in the header. Now I'll show you the header format, how these will be organized. Let me tell you. So header format, we'll write here the source port, destination port, total length, checksum. So this is a header format. This is a header format of UDP, or you can say UDP header format. So the total length is 16 bits. Oh, sorry, 32 bits. Sorry, 32 bits, and the individual length is 16 bits each. Each is 16 bits. Okay, and what we are saying is the data and datagram. So if you consider it as a datagram, so we'll be having some header and the data. So this header format is in this way. This is the header format. This is the header format. Now we'll see working, how it will be worked. So simple steps, working of UDP. What is the first step? So application. So the main service of this one is application to application. That means a process to process communication. So application will create a data. Application creates a data. Second one, UDP header will be added. Added to data. And third one, directly this particular UDP header and data, which is a datagram, will be sent through internet. So datagram will be sent to destination, and at the destination application will receive data. If it is successfully transmitted. So we are saying it is no guarantee. So here there is no concept of connection establishment. So in connection oriented, first a connection should be established, then only the data will be transferred. Okay, we have seen the service primitives also. Listen, connect, accept, then only the send and receive will be there. But here there is no concept of connection establishment because it is a connectionless protocol. So what are the applications where these UDP protocols will be used? So applications means particularly one-way communication. So if any application wants to give a one-way communication, that means one-way sending of data, in such applications we can use this UDP protocol. So one such application is online gaming. So while playing the game, there will be different characters moving around the screen. So if some kind of data is lost, there will be no problem. Still the game will be playing smoothly. So online gaming, or even video streaming, also one type of application, video streaming. So attending the live sessions are simply used by, this UDP protocol will be used in these online gamings and video streamings. Particularly the application which requires the one-way communication, that such type of applications will be using this UDP protocol. So no connection establishment. So directly the data will be created, header will be added, and directly it will be passed to the destination. The destination will receive the data. Okay, it will receive the datagram, and it will again calculate the checksum, and it will compare the checksum whether the data has been modified during the transmission or not. So this is about the UDP protocol, user datagram protocol. See, here the name itself indicates the procedure means some function or any service. Procedure means some function or any service. So what is the remote procedure call? That means calling a procedure which resides in a remote computer. So we are having two computers connected over a network. So if one computer wants to access the service provided by the another computer, so we are giving some work and that work will be executed by another computer and we are getting the result. So that is called a remote procedure call. So this process is similar to our user defined functions. So whenever the control executes the function call, it goes to the function definition and result will be getting to the calling function. The same way here we are having a two different systems. If you are talking about the functions, functional programming in C, so the complete functions will be in the same computer, but here the remote procedure call, so the function definitions will be available in another computer. So we are acquiring the services of another computer. So the definition means calling a function or a procedure, you can write it anything, function or procedure or a service, calling function which is available in another computer. So in another words, in a simple words, what we can say means a computer acquiring the services. So one computer using the services of another computer over a network. So the network is most important. Okay. So here mainly it involves some 4 steps. Okay. So let us write that steps. So one is a client program, client stub, network, server stub, and server. So this is the process done in RPC, remote procedure call. So we'll see what exactly the steps will be done in all these cases. Okay, so client stub, network to server stub, and server stub to server. See what happens. I'll give you a simple example. Let us tell you an example so that you can understand. So you are going to an ATM and you are just using get balance function. So if you are using the service called get balance function, so what happens here? So automatically one procedure will be called like get balance. So where our accounts will be stored, that will be stored in the bank server. Okay, not in the ATM, right? So in the bank server, our details will be there, our account details will be there. But we are using this get balance in the ATM machine. Okay, ATM machine is not a server, right? So what happens? This request will be went to a bank server, and we are getting, and process will be executed, and immediately we will be getting the balance, whatever the balance we are getting towards the ATM. So that means one computer, that means ATM, using the services of another computer just by accessing a small function. So yes, so hope you got some idea about remote procedure call. So I'll write a steps. Step 1. What's the step 1? Let us take a client as one computer and a server as another computer. So client calls a function. Let it be this get balance function. What's the step 2? What we are saying? So the process will be executed on another computer over the network. That means the system should be connected to the network. So what is the step 2? So the request will be sent to the client stub. Request will be sent to client stub. So here the another term called client stub. So what is the client stub? It is a representative, just acting like a representative of server. You are correct, the representative of server on client side. And server stub is representative of client on server side. Okay, so these two will be on client side, these two will be on server side. So client side, server side. Okay, so client stub is a representative of server or client side, representative of client on server side is a server stub. So request will be sent to the client stub. Now what happens? So here the function will be in this format. That means there will be some function name as well as some parameters also. Here the parameter is an account number, right? So along with the function name there will be some parameters. So that will be converted into message which can be transmitted towards the network. So the same thing cannot be transmitted over the network, right? So there will be one format that will be accepted to transmit in the network. So that work will be done by the client stub. So here, so it converts function with parameters to message or network message. So we can simply write it as network message. So unless you convert this particular function name and parameters to the network message, it can't be passed through the network because it should be passed through the network. Next, step 4. Step 4. Now network message will be passed to server. That means it transmitted to server. So now what happens? Server stub will be giving the response for this one, right? So receiving the request. So server stub will receive the message. Whatever the network message we are sending, that will be received by the server stub. Now what happens? Again, the server stub will be extracting the data from the message, because in order to execute in the server, that should be in the form of function call, but we are getting in the form of message. So that extraction will be done by the server stub. So server stub converts message to function with parameters, function along with parameters. Now step 7, so function call will be sent to server. Now the function call will be sent to the server, right? Next, step 8, what happens? Server executes the program. Server executes the program and return the result. Return the result. So where the result will be gone? So the result will be sent to again server stub. Now server stub will change the result into the network message, and that will be received by the client stub. So that will be transmitted towards the network, and client stub will be receiving the message got from the server. And now the client stub will be extracting it to send the result to the client. So this is the procedure, and here the conversion of function along with the parameters, right? So we are saying the client stub will be converting the function with parameters to the network message, and this is called as a marshalling. This process is called a marshalling. And here in the server stub will convert the message to functions, and this is called unmarshalling. Unmarshalling. So simple example for this marshalling means, so before you send any courier, what happens? The complete data will be packed with the labels, right? So that is called a marshalling. So once the packet or the order received, the receiver will be unboxing the data, right? So that is marshalling, unpacking the data. So packing of data or unpacking of data, we can also write in this way. Packing of data is called a marshalling, and unpacking of data, unpacking or extracting, unpacking of data is called unmarshalling. So this is the process of this particular remote procedure call. So the first, there will be a client program, and it will be sent to the client stub, just now we have said. So that will convert into a message, and that particular message will be routed to in the network, and it will be received by the server stub, and it will be sent to the server. And once again, the server execute the program, and it will be sending to the server stub, and server stub to network, and network to client stub, and client stub to client. So this is a process of remote procedure call. With a single sentence, we can say that one computer using the services of another computer. So in one computer we are calling the procedure, and that will be executed by another computer, and we are getting the result. So this is called as a remote procedure call. Real-time transport protocol. So similar to our UDP protocol, so this is represented with the RTP, real-time transport protocol. So main goal is to deliver multimedia content over a network. So here the multimedia means the two things. One is video content, another one is a audio content. So mainly this protocol is to deliver the audio and video content. So if you are giving some audio or video content, if you are delivering the video or audio content, compulsory that should be fast delivery. The packets should be fast delivered, and also low delay. So these two are most important, right? So the application where we are going to use this RTP is simple. So video streaming. Okay, so video streaming in the sense you can see Zoom meetings or WebEx meetings, etc. Okay, online meetings. That's nothing but our video streaming will be done. So that there the protocol used is a real-time transport protocol. Now what are the functions? What are the functions of RTP, real-time transport protocol? Okay, so the first function is sequence number. See, before going to the functions, if you see this fast delivery and low delay, so previous protocol which we have used is a UDP protocol. So we have discussed about this UDP protocol, that is mainly for fast delivery, and also it doesn't guarantee that packet is delivered. So if the packets are lost, that doesn't impact on the application. So here also the same thing, but there will be a slight difference among these UDP and the RTP protocols. So let us see. First one is a sequence number, which is not included in the UDP, but it will be included in the RTP. So sequence number is to identify lost packets. So if there are any loss, if there are any packets lost in the transmission, that can be identified by using the sequence numbers. And also reordering. So the data may be sent in a different order and they may be received in different order. So based upon the sequence number, they will be reordered so that they will identify which packet has been lost during the transmission. So that is the first function of RTP, so which is not available in UDP. And the next one is a timestamp. So here timestamp means it will be used for making a synchronization. So the packets should be delivered at an equal interval of time, or so synchronization, mainly it is for synchronization. So what is this synchronization? So example, if you are getting some video file, so there will be both video and audio. So there should be the synchronization between a video content and audio content, so that the data will not be mismatched. So if there is no synchronization, so the video will be lagging when compared to the audio, or audio will be lagging when compared to the video. There should be perfect synchronization between audio and video. So for that purpose, we are going to use this timestamp. And the next one is a payload type. So what is meant by payload? Payload means some data. So payload is a data which we are transmitted from one system to another system. So here the type of payload will be either audio or video, audio content or video content. Okay, so these are the three main functionalities of RTP, and all these three are not available in the UDP. So particularly these two, sequence number and the timestamp. Okay, but in RTP, real-time transport protocol, we will be having this sequence number and timestamp. So if there are any packet lost, the receiver will be knowing which packets has been lost. Okay, yes. Now how the RTP packet will be represented? So RTP packet will be represented with RTP header. That's a common. We have seen this kind of thing in previous classes. RTP header must be there, and then payload. The payload can be either audio or a video. So this is the packet. Okay. Now what is this RTP header? what are the different fields available in the RTP header. So in our last class, we have seen the header of UDP and in header of IP also, IP protocol also. Similarly, RTP header will be having different fields. Okay, so we'll see those fields. The first one is a version. First, I'll write here, then we'll see. The first one is a version. So version means it gives the version of RTP protocol. So it gives version of RTP protocol, and the size of to represent this version is one bit. Next, padding. Padding means sometimes the data will be transferred in a blocks. So for every block there will be a fixed size. If the data is not equal to the length of the block, some dummy bits will be added. Mainly this kind of padding will be done in the encryption algorithms. Okay, so we will be padding some extra bits, dummy bits, to make the length of the content equal to the block size. So that type of padding. So adding dummy bits. So it represents whether it was added or not. Okay, dummy bits. Size is again 1 bit, and I think this is a 2 bits. 2 bits. Okay, padding. Next, extension. So some header formats will be having some extensions, right? So such type of extension, is it available? So we have seen this extension in IP header also. So whether it is having some extension or not. So it is also the size to represent this one is a 1 bit. Next, CSCR count means contributors count. What we are saying means contributors count. So here what is meant by contributor? So we are giving an example of video conferencing. So video conferencing. Okay, so in this video conferencing, this will be the source, and so this is the target audience, user 1, user 2, user 3, user 4, and so on, right? So here the contributors count means at a time all the users can communicate with the source. So these particular contributors, that means at a time how many of the users are being active, inactive, right? So that is a contributors count. So the size to represent this contributors count is 4 bits. So you can imagine here we are saying it as a 4 bits means the total number of combinations will be 15. That means 0, 0, 0, 0, 2, 1, 1, 1, 1. So this is 0 and this is a 15. So total 15. So at a time only 15 contributor count can be represented. Okay. Next, marker. Marker means in order to represent important events, whether there are any important events, that means high priority events. So that will be represented with a marker. So size is here 1 bit. So how it can be represented, you can see, you can observe here adding dummy bits. So that means here it is represented with only 1 bit. That means if this particular padding bit is 1, that implies padding exists. That means there is some padding. If padding bit is 0, that implies no padding. There are no dummy bits. So in such a way, this will be represented. And here also the same thing. Extension. If the extension bit is 0, there is no extension. If the extension bit is 1, there is an extension. So similarly, contributors count, that can be, the maximum count can be 15. It can be from 0 to 15. And here also marker representing the important events, priority. So for which kind of data the priority should be given. If there are any prioritized events, then it can be represented with a 1, otherwise it will be represented as 0. So next, marker, and the next one is payload type. Just now we have seen payload type means whether it is sending audio or video, and the size here it represents as 7 bits to represent the payload type. Okay, and then sequence number in order to rearrange the packets at the receiver side, reordering, and also identify the packet loss. So the size to represent this one is 16 bits. 16 bits. And the next one, timestamp. This also we have seen just now. So in order to synchronize the audio and video, okay, so this timestamp will be there, and the size is representing is 32 bit. And the next one is SSCR. So that means source identifier. Okay, yes, identifier. This is a source identifier. Okay, source. That means source ID. From how many sources the video or audio is coming, right? Similarly, CSCR. Sorry, CSRC. SSRC, source RC. This is a contributors identifier. Contributors identifier. That means we have seen, so these are all at a time how many users are interacting. So that is a contributor. So source identifier and the contributors identifier. So all these are in a RTP header. So version, padding, extensions, contributors count, marker, payload type, sequence number, timestamp, source identifier, and the contributors identifier. So we'll arrange all these things in this RTP header. Hope you understood this one. So everything will be represented in a 32-bit word. Okay, 32-bit word. So let us represent this one. So version, next padding, extension, contributors count, payload type, and sequence number. So here 1 bit, sorry, 2 bits, 2 bits, 1 bit, 1 bit, 4 bits, 7 and 16. Yes. Okay. And then here it is a timestamp. One more bit is here, that is a marker. This is 1, right? Now it was done because 2 plus 1 3, 3 plus 1 4, 4 plus 4 8, 9, 16 and 32. Total it should be 32. So this is a 32-bit word. So every header formats will be in a 32-bit words. Okay, so timestamp, and it is also 16-bit. 32-bit. And then source identifier. This is also 32-bit. And contributors identifier, and this is also 32-bit. So this is the header, and here the payload will be either audio or video. That will be this one, and total this will be calling as a RTP packet, real-time protocol packet. Okay, so the difference among this RTP and UDP means, so in UDP we are not having the sequence number, particularly the sequence number and the timestamp. It cannot detect the errors, but here in the RTP, real-time transport protocol, it will identify the lost packets. So whatever the packets has been lost, so that will be identified by using the sequence number. And also here we are delivering the audio and video, so there should be a synchronization between the audio and video. For that purpose we are using this timestamp. TCP Service Model. So what are the key features of this particular TCP service model? The first one, this TCP protocol is a connection oriented protocol. So the first key feature is a connection oriented. So here the connection oriented means before sending and receiving the data, the connection should be established. So here before send or receive data, connection should be established. So already we have seen earlier, so this is called as a three-way handshake protocol. Three-way handshake. Already we have seen in our previous sessions. I'll post the link in the description, so just go through that. So The first key feature is a connection oriented. So TCP is a connection oriented protocol, transport protocol. So whereas UDP is a connection less protocol. And the next one, reliable data transfer. So as we are saying it is a connection oriented, the next feature of this TCP protocol is reliable data transfer. That means the data can be transferred to the destination without any loss, without any error, and without any delay. So receiver receive the data without any loss or error, without any loss or error. So the data will be transferred reliably. So whenever the data is transferred to destination without any error or without any loss, that we call it as a reliable data transfer. So here for this particular reliable data transfer, it will use retransmission. So if any data is get corrupted during the transmission, so the same data will be retransmitted. And acknowledgement. So how can we know that the receiver will receive the data? So acknowledgements. So usually we'll call it as a ACK, acknowledgement. And another one, checksum. So we need to know whether data has been there is any error in the received data or not. So for that, that is a checksum, right? So these three are mainly used to send the data without any loss or without any error. Okay, this is the second one. Next, congestion control. So it have to reduce the traffic, network traffic, in order to send the data or in order to receive the data, right? So for that we have seen a lot of congestion control algorithms like back pressure. One is a back pressure, choke packet by using the choke packet, etc., etc. So with the help of all those techniques, the network load should be reduced. So reduces network traffic using back pressure or any other technique. Okay, right? So this is a third key feature. Next, flow control. Flow control also. So in order to maintain the consistency between the sender and receiver, so it have to reduce the transmission rate. Okay, so reduces transmission rate. So in order to do this, what we have seen different sliding windows. We have introduced a sliding window. So we have seen a different techniques like go back n or selective repeat, like that we have seen a different technique. So with the help of those techniques, the flow will be controlled, the data flow will be controlled in between sender and receiver. So it means the consistency of sender and receiver. Next, multiplexing and demultiplexing. This one also we have seen in our previous session, multiplexing and demultiplexing. So here the multiplexing and demultiplexing means at a time multiple applications can send the data and they can receive the data. So when the senders wants to send the data from the multiple applications, all the data will be packed to one packet and it will be sent, and the receiver side that will be extracted and the data will be received to the sent to the appropriate applications. So accepting, simply we can say accepting data from multiple sources, multiple applications, not the sources, applications. We have to call it as applications because we are saying from application to another application the data will be transferred, right? So multiple applications. So for this they require a port numbers. They need to identify the port numbers, and with the help of port numbers the data will be accepted from multiple applications and it will be received by the multiple applications at a time, right? Port number is to identify the application. Next, byte stream service. Byte stream service. So the data will be transmitted in a byte by byte. Okay. So continuous data will be transmitted. Continuous data will be transmitted. Right. Next, ordered delivery. This is also very important. So as this is a connection oriented, so if the data has been sent in some order, in the same order the data will be received in the destination. If not, it will be using some sequence number concept to arrange the packets which were received in the same order. So data can be received in same order in which they have sent, or rearrangement can be done. Rearrangement, right? So this will be done with the help of sequence number. So this is the most important. This will be done with the help of sequence number. Sequence number should be there, right? Next, full duplex. So in our earlier sessions of computer networks, we have studied the mode of communication, data communication. So that is a half duplex, full duplex, right? So half duplex and full duplex. Here the full duplex means the data flow can be done on both sides. So data flow can be done on both sides. So here both sides means sender and receiver. So the sender can send the data as well as receiver can also send the data. Okay, sender to receiver as well as receivers to sender. So we have seen this one. So this is a device A and this is a device B. So A can send the data to B as well as B can send to data to A, right? So this is a half duplex service. So all these are the different key features, or we can say the services of TCP service model, which is a TCP protocol. It's a TCP protocol. So one important thing is TCP protocol is a connection oriented. Simply we are telling, so connection oriented, and why we are saying, I mean, if we are saying is a connection oriented, it is a reliable data transfer. Reliable data transfer. So what happens? Before sending and receiving, the connection will be established. Then only the data can be transferred from one device to another device. See, the segment means TCP header which is added to data. So this is called a TCP segment, okay? And this header, so data can be a variable length because depends upon the application. The data size may be varied. The system or application, the data size may be varied. But the TCP header is fixed. Okay, TCP header is fixed. So the size of TCP header is minimum 20 bytes and a maximum of 60 bytes. Minimum of 20 bytes and a maximum of 60 bytes. Right? See, here we'll see what is the TCP header. Okay. So it will be having a 5 32-bit words other than the padding one, right? 5 32-bit words. So every row which I am specifying here will be 32 word. Okay. So the first 32 word will be consist of source port number as well as destination port number. Source port number as well as a destination port number. So this is the thing. Yes. So this will be of 16-bit and this will be of 16-bit. Okay. Next. So source port number and destination port number. As we said that there will be a delivery of data between application to application, right? So that is a one service we have discussed. So here every application will be uniquely identified with the help of a port number. So source port number and the destination port number are important. Then the next one is a sequence number. Sequence number. So what is the sequence number? So the size of this one is a 32-bit. What is the help of this sequence number? Sequence number means to reorder the data. So the number of segments that are being passed to the receiver is the thing. So sequence number mainly used for reordering the data at the receiver side, because we are sending the data. So whatever the data we are sending, that may reach in the same order or in different order. So in order to make that sense, the data should be reordered there. So for that purpose, every packet will be given one unique sequence number. So with the help of sequence number, the packets will be, the data will be reordered. And the next one is a acknowledgement. Acknowledgement. So here the size is again 32 bit. So what is the use of this acknowledgement? Acknowledgement means, so in order, the receiver will be giving an information to the sender that the packet has been successfully received. That is called as an acknowledgement. Okay, so feedback, simply we can say, in our understanding words, we can say it is a feedback, or so telling the sender the packet which it has sent has been received successfully. Okay, so along with the data, the acknowledgement will be set. Okay, in our last session we have seen three-way handshake in the connection establishment. The first one is a synchronization and sequence number, and next acknowledgement along with a sequence number plus 1. Right, so that means the acknowledgement is alone not sent, it will be added with the some information and it will be sent to the receiver. And the next one, H length. H length means header length. So whatever the header we are using, the length of the header. So here we have seen the size, header length size is minimum 20 bytes and the maximum 60 bytes. So whether this header is having 20 bytes of data or 60 bytes of data. So to represent that, it will be of 4 bits. Next, reserved bits. Reserved. So these bits will be used for future purpose. So the size is 6 bits. And there will be different flags. Okay, each flag is having a 1 bit. Okay, so the first flag is a urge flag. So URG means urgent pointer. So if it is set to 1, that indicates, so urgent pointer should points to important data. That means whatever the data which is being delivered urgently, so to that particular thing the pointer will be points. If it is 0, there is no urgent, that means there is no priority. Simply we can say priority. Next, ACK, which is nothing but acknowledgement. ACK, which is nothing but acknowledgement. That means it will, if it is set to 1, that implies the information, the data will be having some acknowledgement. So it has acknowledgement. If it is 0, no acknowledgement. Okay, the data or information doesn't have acknowledgement. Okay, so this is the representation. Status, we can simply say it is a status. Next, push. So if it is 1, that implies it says the receiver to push the data to the buffer. Okay, push the data without buffering, push the data without any buffering. Okay, next, RST means reset. So if it is 1, connection should be restarted. So as we said that this is the connection oriented. So before sending and receiving the data, the connection should be established. So if this reset is set to 1, it indicates the connection should be restarted. If it is 0, that's not required. Next, SYN. So this particular thing, SYN, is synchronize. What does this synchronize means? We have seen in connection establishment. So if it is 1, that is connection establishment. Connection establishment. Connection establishment, right? And the next one, FIN, which is a finish. It indicates connection release. So connection should be released. So this also we have seen in our connection release. Okay, connection establishment we have seen SYN, and connection release we have seen FIN, which is a 4-way handshake. This is a 3-way handshake. And the next one is a window size. So window size which is of 16 bits. So all these are 1 bit. All these flags are 1 bit. So all these flags, these are all flags. The size is 1 bit, which gives the status, simply which is a status. Okay. And the next one, so this window size, window means how many bits can be received by the receiver. It shows that we have seen the sliding window, right? So without any buffering, without any delay, without any acknowledgement, how many bits we can transfer to the receiver. So that is the window size. And this is a checksum in order to find out the error correction or error detection. Simply we can say error detection. 16 bits, checksum is 16 bits. Okay. So this checksum is for error detection. Okay, checksum is a error detection. And the next one is a urgent pointer, URG pointer. So here we have seen one flag, URG. If it is set to 1, that means urgent pointer should point to important data. So this is the pointer which is of 16 bits, and if this bit is 1, that implies there is some important data which must be pointed. So this urgent pointer will be pointing towards that particular data. If it is 0, there is nothing. If it is 0, there is nothing. Okay, this is also 16 bits. And all the remaining are optional. Option and padding. Option and padding. So this is of 40 bytes. 40 bytes of data. Okay, so this is a 32, this is a 32, this is a 32, 32 and 32. So 32 bits, it's not bytes, 32 bits. So how much? 32 bits means 4 bytes. 4 bytes. Okay, this is also 4 bytes. This is also 4 bytes. 4 bytes and 4 bytes. See, you can see 1, 2, 3, 4, 5. So 5 fours are 20. So this is an optional one. And apart from this, what is the size of header? Which is a 20 bytes. And the size of this one is 40 bytes. So this is the 40 bytes. Total 60 bytes. So minimum is 20 bytes. So this is a minimum. This is a minimum up to the urgent pointer and checksum. This is a minimum. And there is an option which is a 40 bytes. Optional information. Okay, optional information. If the information is less than 40 bytes, then the padding will also be done. Padding means adding some zeros, dummy bits. Okay, so these are all flags. Very important. Urgent flag, acknowledgement, push, reset, synchronize, and finish. So source port, destination port, sequence number, acknowledgement, header length, reserved bits, flags, window size, checksum, urgent pointer, and options and padding. So hope you understood. This is a TCP header, and the complete thing is called as a segment. TCP header and the data is called as a segment. So this we can call it as a TCP header segment, or simply you can call it as a TCP header. So we have studied that TCP is a connection oriented protocol. So connection oriented. So connection oriented means a connection should be established before the data should be transferred, right? So there are 3 phases of this connection oriented. So first one is a connection establishment. Connection establishment. And the second phase is data transfer. So once the connection was established, then the data will be transferred between the 2 devices, and afterwards connection release also very important. Connection release. See, coming to this connection establishment, we have studied that this connection establishment is a 3-way handshake protocol. So 3-way handshake protocol means the client will send the synchronous. That means, see, both the devices should be ready. Both devices should be ready, and both the devices should share their sequence numbers. So sharing sequence numbers. and then allocation of resources. Allocation of resources. So in order to complete the task, so some resources may be required, so that allocation will also be done in the same phase. Okay, connection establishment phase. So first devices should be get ready, and then sharing of sequence numbers. So sequence numbers should be shared among those two devices, and once they are shared, it seems the connection is established and they are ready to transfer the data, and also allocation of resources. And coming to the connection release, so we have studied that connection release is a four-way handshake protocol. So client sends the FIN to server, and server sends the acknowledgement to client. Okay, so client to server and server to client, and then again server will be sending its finished message to client, and client will be sending acknowledgement to server. So this is a connection release. What happens in this connection release means it will deallocate all the resources. During the connection establishment, we have said that allocation of resources was done, and once the work completed, the connection should be released so that the deallocation of all the resources should be happens. And see, all these three phases, whatever we have studied so far, so connection establishment, data transfer, and connection release, this is called as connection management. This is called as connection management. And during all these phases, the TCP will be moving on to different states. The TCP moves with the different states. So from the beginning, that means from the connection establishment to this one, sending the acknowledgement to release the connection, to finish the connection. Okay, so we'll see what are the different states of TCP. So this process we call it as a connection management. So all these three phases. Now let us see the states. What are the different states the TCP will be moving on from connection establishment to connection release? So the first one, closed state. So closed state means here whenever the system is idle, okay, there is no active connections. That means no active connections. There are no active connections. That implies system is in idle state. So that we call it as a closed state. Next, the next one is a listen state. So already we have seen this listen state in the TCP service primitives. So listen means server is ready to accept request from client. So that stage we call it as a listen state. Next, SYN underscore sent. So the next, what happens? A client will send the request. Client sends the request of synchronization, right? So then immediately it moves to the client underscore send. So all these are states. Okay, all these are states. Next, SYN received. So once the server gets the request from the client, so immediately the server will respond to the client by giving the acknowledgement. So server send the acknowledgement to client. So that is a synchronization received and ready to data transfer. So that means after this one the connection has been established, right? So closed, listen, synchronize, send, synchronize, received. So what we said in the first phase is the connection establishment. In that first, both the devices should be ready, and second, the sequence number, both sequence numbers should be synchronized. So here synchronized sent means the sequence number will be sent to the server, and server will be responding with the acknowledgement to that particular sequence number to the client. So here up to here the connection establishment is completed. Next, established state. What is this established state? So this is actual data transfer. data transfer. How the data must be transferred? So it should be reliable. We have studied about this one, reliable. Reliable means the data should be received without any loss or error. Okay, if there is a lost, if packet lost, what happens? A retransmission will be done. Retransmission will be done if it is lost. If unordered, next, with the help of sequence number, it will be ordered, right? So like this, the data transfer will be done in this established state. Okay, so the first four were connection establishment, and the next one is a data transfer. Now, once the data transfer has been completed, what should be done? So that is nothing but connection release. So the next one is FIN underscore wait 1. So what does this mean? When the client, whenever the client wants to stop communicating, immediately the client will send the finish message to the server. So client sends finish message to the server, and it will be in the waiting state. The client immediately goes to the waiting state. Fin wait 1. The next one is fin wait 2. So here the server will send an acknowledgement. Okay, sorry, client receives acknowledgement from the server and waits and waiting for fin message from server. What we have said. So immediately whenever the client's first message is the client sending the finished message, and for that the server will respond with the acknowledgement, and immediately the server will again send the finished message from server side. So that's what happening here. So first client sends the finish message to the server, and it moves to the finish wait 1 state, and immediately client receives the acknowledgement from the server, and again the client will wait for the finish message from the server. That is a finish wait 2. Next, close wait. So server receives fin message from client and send acknowledgement to client, and immediately that moves to the close wait. Next, last acknowledgement. So here the server will be waiting for acknowledgement from client. So immediately whenever the server sends a finish message to the client should also send the acknowledgement. Okay, so whenever the server will be waiting for acknowledgement from the client, that comes with the last acknowledgement. And the next one, the last one, is a time wait. So once the server sends, once the client sends the acknowledgement to the server, okay, immediately sometime the client will be waiting for receiving any delay packets. So waits for delayed packets. For example, see, if server, whenever the server, I'll draw the diagram so that you can understand. See, first client will be sending the fin message, and the server will be sending the acknowledgement message, and again server will be sending the finish message, and now the client should acknowledge that, and it will be waiting. Okay, it will be waiting, because if this particular acknowledgement is lost during the transmission, okay, hope you understood. So actually this is the happen in the connection release. The first one is fin, next acknowledgement from the server, finish message from the server, and for that finish message client should give the acknowledgement. So whenever the client gives an acknowledgement to the server, if this acknowledgement lost during the transmission, packet loss, what we have said, if there is any packet loss, the retransmission should be done. So the client should be ready to retransmit this acknowledgement to the server. So for example, if it is lost, so still it have to wait some time. The client should wait for some time to release all the resources and connection release, because if there is any loss during the transmission, it must be ready to retransmit the acknowledgement to the server. Okay, so for that the time wait is there. Okay, immediately the connection will not be released. Some time it will be taking and to receive the delayed packets, and then the connection will be released, and all the resources which are allocated to that will be deallocated. So the TCP will be moving towards all these states during the connection management. So what I said, the connection management means 3 phases: connection establishment, data transfer, as well as a connection release. So TCP congestion control. So already in our previous sessions we have discussed about this congestion, what exactly mean the congestion and how to control this congestion. So we have seen a lot of techniques. So quickly I'll recall this one. So congestion means having more number of packets over a network is called as a congestion, and simply we can say congestion is a traffic jam. So in the network the packets will be keep on moving, and if a lot of packets came into the network, immediately there will be a congestion, which is a traffic jam. So what is the impact of congestion? Once congestion occur, what happens? The first one, packet lost. There might be a chance of losing the packet. Okay, packet lost. Delay will be increased. A simple logic. So if we are traveling from one place to another, if there is no traffic, we will be reaching the destination within a time. If there is a heavy traffic, automatically there will be some delay to reach the destination. The same concept. And if the packet is lost, automatically the sender have to retransmit the data, I mean the lost packet. So there will be a lot of retransmissions. So one more disadvantage is, already the network is overloaded, and these retransmitted lost packets will also be come to the network, or that may lead to more congestion. Okay, so this is the impact. Okay, and also slow internet. The result will be slow internet. So obviously efficiency will also be less. So in order to maintain all these things, okay, the TCP will be using a process. TCP controls the congestion with a simple process. What happens? So the TCP will start sending packets slowly, because the TCP doesn't know how much traffic a network can hold. Okay, how much traffic a network can hold, the TCP doesn't know. So always the TCP starts sending the packets slowly. So if network is fine, TCP increases sending packets. First one. And if network is about to overload, what happens? The TCP decreases sending packets. Okay, right? So if we are traveling from one place to another place, if there is no traffic and roads are empty, automatically we will raise the speed. Okay, we'll increase the speed which we are traveling. And if the roads are having a somewhat traffic, automatically will decrease the speed to reach the destination. So same concept here also, the TCP will be starting sending the packets first very slowly. If the network is fine, then automatically the TCP will be keep on increasing sending packets to the destination. And if the network is about to overload, automatically the TCP will be decreasing the sending packets. Okay, so for this particular congestion control mechanism, it will be using a term called CWND. So what it means congestion window. So we know this window, we have seen this window in a flow control, right? So window is a buffer. Imagine it is a buffer to accept the number of packets that can be sent to the destination without the acknowledgement. So we have studied in our earlier sessions. So for every packet we are sending, we'll be getting the acknowledgement. Then only we need to send the packet. So it will be a very time-taking process. So that's why we are maintaining a window, so that the window specifies number of packets can be sent without acknowledgement. So without receiving the acknowledgement, the number of packets we can send to the destination. So this is a congestion window. The TCP will be maintaining this congestion window. So initially the congestion window will be small, and later, depends upon the network, the congestion window will be increased. So initially this is CWND is less in size. So depends on network status, CWND will be increased or decreased. Anything can happen. If the network is about to overload, it will be decreased. If the network is fine, it will be increased. So the TCP will be maintaining this congestion control in 4 phases. 4 phases. So what are those phases? 4 phases. What are those phases? The first phase, just now we have seen, that is a slow start. Slow start. So in this phase, CWND will be very less in size. Very less in size. For example, let it be CWND will be 1. 1 means only 1 packet can be sent. If we get the acknowledgement for that packet, okay, immediately the CWND will be increased. So after getting acknowledgement, then CWND will be 2 times of CWND. Okay, double. So for example, let us take round 1 and CWND, the packets. First, only 1 packet will be sent. If we get the acknowledgement, okay, we get the acknowledgement. Next, the round 2, in the second round, 2 packets in the CWND, that means window size will be increased to 2. If we get a 2 acknowledgement for this, in the third round, this will become 4. If we got a 4 acknowledgements, then immediately in the 4th round we'll be getting 8. Okay, and in the 5th round, okay, it will be 16. So this is called exponential growth. This is called exponential growth. You can imagine this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. It's an exponential growth. Okay, so this depends upon the network. Okay, if the network is about to overload, the CWND, that means congestion window, will be increased. So this is a slow start. This is a slow start. In the slow start, slightly the window size will be increased in an exponentially. Then second phase. Second phase. What's the second phase? Congestion avoidance. Congestion avoidance. That means if the network is about to overload, okay, if network is about to overload, what we have to do? We have to reduce CWND, that means a congestion window. So previously we are increasing the CWND exponentially. Now also it will be increased, but the window size will be somewhat reduced. Okay, reduced and increased slowly, not exponentially. For example, here if round, it is round and this is a window size. What happens? First round 1, second round it will be 2, third round it will be 4, fourth round it will be 8, fifth round it will be 16. Now here we observe network is about to overload. network is about to overload. What happens? Next, in the sixth round, the window size will be increased, but it will be increased to only 1. Seventh round, it will be 18. So here you can observe the window size is increased with 1. Okay. So this kind of thing we call it as a linear growth. Linear growth. So always the window size will be increased, but coming to if the network is fine, the window size will be increased exponentially. But if the network is about to overload, not overloaded, is about to overload, then the increase of congestion window size will be linear. So one step. Okay. So this is the second phase, and the third phase. Fast transmit. Fast retransmit. So for example, if the client, and let it be, it's a server, okay, or you can simply we can call it as a sender, and it is a receiver. What happens? If sender wants to send 1 to the receiver will receive and it will give the acknowledgement of 2. That means I got 1, I am waiting for 2. Okay, that implies I got a 1 and I am waiting for 2. So in our previous session, connection establishment also, we have seen the sequence number will be added with 1, incremented, right? The same case. So if the second packet is sent, whenever the second packet is received at the receiver, it will send an acknowledgement asking for third packet. And if it is 3, it will be asking for fourth packet. Okay. So for example, 4, 5, 6, 7. So here the data is lost. The packet 4 is lost. Okay, packet 4 is lost. What happens? Again, the acknowledgement 4 will be sent, because at the receiver side, it have to reorder everything. Right? So whenever it goes here, again it will be asking about 4 only. Again, whenever it goes, it asks for 4 only, right? It was asking about 4. That implies the packet 3 is received and I'm waiting for packet 4. Packet 4 is not received. So whenever the retransmit will be done, so whenever the packet timeout, so every packet will be having some timestamp, right? So if the timestamp goes out, then immediately the sender will know that the packet has been lost and it will be retransmitted. So there will be a lot of waiting time. Okay, so it have to wait until the time is out. So instead of that, whenever it receives the acknowledgement 4, sorry, this is the process. Okay, acknowledgement means this one, acknowledgement 3, acknowledgement 4, and here it is again acknowledgement and again acknowledgement. Okay, hope you understood. One will be received by the receiver will be sending the acknowledgement, right? So whenever this acknowledgement 4 received by the sender, okay, sender receives the 3 duplicate acknowledgement. These are called as a duplicate acknowledgement. So whenever the receiver, sorry, who will receive that duplicate acknowledgement? Sender. Whenever the sender receives 3 duplicate acknowledgements, then retransmission will be done. So what it implies means, if it receives 3 duplicate acknowledgements, that implies the packet has not been received by the receiver. So the packet has been lost. So if the packet is lost, immediately there will be a retransmission will be done. Okay, so without the packet 4, it can't be reordered that. Okay, receiver. So receiver will be keep on asking for the packet 4. So this is how the faster retransmit will be done. So it will not wait for the timeout. So it will wait for the 3 duplicate acknowledgements. Whenever it receives the 3 duplicate acknowledgements, immediately that packet will be retransmitted. And the fourth phase, fast recovery. So whenever there is a congestion, for example, if the network is congested, overloaded, that means congestion occur. What happens? Immediately the TCP reduces the window size and not start from the beginning. It will not start sending, retransmit the packets from the beginning. Okay, so which packet has been lost, that packet will only be retransmitted. So that is a fast recovery. So whenever the network is overloaded, that means if the congestion occurs, immediately the TCP will be reducing the window size, reduce the window size, and it will not start from the beginning. So it will retransmit the packet only which has been lost. Okay, so these are all the different phases involved in the congestion control. So by using all these phases, the TCP will be taking care about controlling the congestion over the network. Okay, so it will start slowly and it will be based upon the status of the network, it will increase or decrease the window size. I'll write here TCP and UDP. Okay, so here I'll write the category. So first one is the name. So what's the full form of this one? This is a transmission control protocol. Transmission control protocol, and here it is user datagram protocol. And the next, connection type. So this is a connection oriented. So this will be used in connection oriented. So that means before starting the sending and receiving of data, the connection should be established, and immediately after data transfer, connection should be released. But here there is no connection. There is no connection establishment and connection release, only directly send and receive. So this is a connection less networks, connection oriented and connection less. Okay, next, flow control. That means the rate of transmission. Okay, so from sender and receiver. So there is, so available, the flow control will be available in the TCP because based upon the receiver's side, so the sender will be keep on reducing the transmission rate. So if receiver wants to receive the messages, so the sender will raise or increase the flow of packets, right? But here it's a connection less, not available, no flow control. No flow control. Next, ordering. Ordering means here the packet ordering. So in TCP, the packets will be received in the same order. So follows the order. Follow ordering. So whatever the order the sender sends the message or packets, the receiver will be receiving in the same order. But here, no ordering. So the packets may reach in any order. Okay. Next, speed. So obviously the TCP will be low speed. Okay, less speed, and here it is fast, because here we'll be using the acknowledgements, okay, retransmissions and everything here, but here there is no acknowledgement, no retransmissions, so automatically it will be very fast delivery. And packet delivery. Coming to the packet delivery, guaranteed. So here we are establishing some connection and we are sending the packets. If any packets are lost during the transmission, automatically those packets will be get retransmitted. But in this case, there is no connection establishment, right? Directly we are sending the packets, so there is no guarantee of delivery. No guarantee of delivering the packets, right? Next, suitable for, so for which purposes it will be suitable. So whenever the accurate transmission, so without any error, okay, accuracy, more accuracy, but here no accurate, so fast transmission. So if you want to send the data in a very fast mode, so if you're not bothered about the guarantee of delivery, so you can use this UDP. Acknowledge. That means if the sender sends a packet to the receiver, receiver have to acknowledge the sender so that I have received this packet and I am expecting the second packet. So here it is a connection oriented. So the acknowledgements are available. So it will send the acknowledgement. The receiver will be sending the acknowledgements. Here, no acknowledgements, no acknowledgements, no guarantee, no acknowledgements. Reliability, reliability. So how far the data can be received without any errors, without any errors. So during the transmission, some data may be corrupted or some data may be lost. So if that situation happens in TCP, it will be retransmitting the packets. So whatever the packets that has been lost during the transmission, those packets will be retransmitted. But here there is no retransmissions. So this will be reliable and this is unreliable. Unreliable. Okay. The next one is a congestion control. Congestion, that means heavy load in the network. Heavy load in the network. So this is the connection oriented. So there will be a connection establishment between the sender and receiver. So there might be a chance of having the congestion. So yes, congestion is available in congestion control can be available in TCP, but here there is no congestion. No congestion control. There is no fixed path. The next one is a header size. So both the protocols are having the header size. In our previous sessions, we have seen the headers, TCP header and the UDP header. So this size of UDP, TCP header is around 20 to 60 bytes. So we have seen some 40 bytes are the optional. Okay, so 20 bytes, 32-bit words will be there. So 20 to 60 bytes, and this is only 8 bytes, very small, very small. Okay, next examples. Examples, simply we can say email, mailing. Okay, and here live streaming. Live streaming is an example for UDP. So it doesn't bother that data has been really received by the receiver or not. Okay, it will be keep on moving, right? If any one packet has been lost, that doesn't affect the particular streaming data. Okay, so that's why this will be an example for a UDP and email. So that is an accurate. So whatever the data you are sending from here, so the receiver will be receiving the same data in the same order. So email is an example for TCP. So these are the major differences among the TCP protocol and the UDP protocol. So if you know about the connection oriented and connectionless, every point you can write on your own, right? So connection oriented means there should be a connection establishment before sending and receiving, and after completion of that, connection release should be there. So definitely there will be ordering, whatever the order we are giving, the same order the receiver will be receiving, and if there is any packet loss, automatically the lost packet will be retransmitted. And as this is a connectionless, all those things are not possible in the UDP protocol. But this is a very fast transmission and this is a slow transmission. So TCP Timer Management. So what it means? So here the name itself indicates a timer, means the TCP will be using certain amount of time to perform any action or before performing any action. Before performing any action, any kind of action. Okay, any kind of action. So what type of action it may take, right? So action means it can detect the lost packets. It can detect lost packets and it can retransmit the packets. Retransmit packets. Similarly, connection. Okay, so avoid or identify the dead connection. We can simply say identify or detect dead connection. Dead connection. Okay, so to avoid waiting time, continuous waiting time, and etc. So all these kind of actions, before doing all these kind of actions, some certain amount of time it will spend some time, which is with the help of timers. So here we'll be using, I mean the TCP is using different timers in order to perform all these actions. Okay, so mainly there are 4 timers the TCP will be using. The first one is a retransmit timer, retransmit timer, persistent timer, keep alive timer, keep alive timer, time wait timer. So here the retransmit timer will be identifying the lost packets and also retransmit the packets. Similarly, persistent timer, it will avoid the waiting time. That means it will avoid the deadlock situations. Keep alive time will be identifying the dead connections. And finally, the time wait timer will be used to close the connection properly. Okay, so we'll see one by one. So first, let us start with the retransmit timer. So we know that if the data, or that means if any packet is lost, automatically the packet should be retransmitted. So when it should be retransmitted? So initially there will be some timestamp. Whenever the timestamp expires, immediately that implies the packet has been lost and that the same packet will be retransmitted. But in that case there will be a lot of waiting time. So to avoid that one, so what happens means when the packet, so I'll write the steps. So sender send the data, sender sent a packet and wait for acknowledgement, wait for acknowledgement. Immediately TCP starts the timer, starts this retransmit timer, retransmit timer. So here two cases will be done. If acknowledgement received before timer expires, before timer expires, then timer will stop, timer will be stopped, because the receiver, the sender have received the acknowledgement from the receiver. And the second case, if acknowledgement not received, not between, before timer expires, what happens? Then retransmission will be done. Okay, so if the acknowledgement was not received before the timer expires, that implies, that will tell the sender that the packet has been lost. So immediately the retransmission will be done. So this particular retransmission timer is used to detect the lost packets before, in this case, second case, not received before time expires, automatically it means the packet has been lost and automatically it will retransmit the packet. Next, hope you understood this retransmit timer. Next, persistent timer. The next one is a persistent timer. So, for example, let us take a sender and here it is a receiver. So, sender keep on sending the packets. Okay, keep on sending the packets, and at one moment, receiver sends a packet with a message buffer full. Okay, buffer full. Until the receiver sends a buffer full message, the sender will be keep on sending the packets to the receiver. Okay, so here I'll write sending packets, send packets, right? Buffer full. Then what happens? The sender will stop sending the packets. Sender will stop sending the packets, and after some time, so this buffer is empty. Buffer is empty. Okay, so this particular thing called as a zero window. That means there is no space to accommodate the packets into the window. So after some time, buffer is empty, and it will send a message to the sender. So I am ready. So I'll write here. So for example, after some time, buffer becomes empty. So what happens if it is empty? It will send some message, I am ready to accept the packets. But unfortunately, it was disconnected. that means this packet has been lost. Okay, this packet has been lost. So whatever the message the receiver was sending, it was not received by the sender, received to the sender. So sender will be keep on waiting for the update message, and receiver will be waiting for the packets, waiting for packets, waiting for update message, update message. So update message was already packet lost, right? So this is called as a deadlock. This is called as a deadlock situation. So in order to close this deadlock, avoid this deadlock, that's a waiting time. So this persistent timer will be used. And after, I mean, whenever the sender starts sending the packets and whenever the buffer becomes full, automatically this timer will be started. And after this time, the sender will be sending. So here the sender sends a probe packet to receiver. What is this probe packet? This implies, shall I send packets? Simply this message will be sent to the receiver. Okay, so the receiver will respond and immediately the packets will be again start sharing between the sender and the receiver. Okay, hope you understood. So here there is a deadlock situation. In such case, this persistent timer will be on, and after this persistent timer closed, that means expires, immediately the sender will send some probe packet to the receiver mentioning, shall I send the packets? So if the receiver is ready, automatically it will give a reply to the sender so that the sender starts packets to the receiver. So this is the persistent timer to avoid this waiting time. So deadlock is nothing but a waiting time, mutual waiting time. So here the sender is waiting and receiver is waiting. Okay. Next, the next one is keep alive timer. The next one is keep alive timer. So this is to identify the dead connection. For example, so here the sender is there and here the receiver is there, and it was keep on messaging, and unfortunately the system crashes. Okay, so this particular source or sender, the sender will be treating that still the connection is alive, but unfortunately the system crashes or the connection disconnected or hang up. Okay, the connection hang up, right? So in such case, this particular keep alive timer will be on, and if the system is in idle, so if the system is in idle for some time, then immediately sender will send a message to the receiver, and if there is a response, connection is alive, and if there is no response, what happens? It's a dead connection. So once again it should be reconnected. That implies once again it should be reconnected. So this is the use of keep alive timer in order to check whether there is a dead connection or still the connection is alive. Okay, so mutual, if any one of the device is disconnected, so it have to know that the connection should be re-established. So for that purpose this keep alive timer will be used. And coming to the fourth one, the last timer, time wait timer. So this time wait timer means it is for proper close. This will be used for closing or terminating the connection properly. So used to terminate connection smoothly. So in our previous session we have seen one state called a time wait state. That means once the server sends the finished message to the client, and the client have to send the acknowledgement, and it moves to the time wait. It never closes immediately. Okay, the connection will not be closed immediately. So it will be wait for some time to receive any delay packets in the network, to avoid the delay packets in the network. So the connection never closes immediately, waits for some time to get delayed packets, So for that, this is a time wait timer. Okay, in order to close or terminate the connection smoothly, right? So these are all different timers that will be used by the TCP protocol. So in order to perform some action, so these are the timers used to before performing any action, the TCP will be taking care. So it is a domain name system. So what is this domain name system? So in our daily life, we are using a lot of websites. Okay, so example, we'll be using some google.com. Okay, so what happens? So some message will be sent from our system to the Google server. Okay, so this is our system. Okay, I'll give it as A, and this one is a Google server. Okay, so from our system, some request will be sent, and as a reply from the Google server, we will get the response. So this usually we call it as a client server model, right? Client server model. Now, so this is called as a communication. This process we call it as a communication. So communication in our computer network means sharing upon some data, so exchanging some data. So request and response. Now, in order to communicate between two devices, compulsory there should be some identifier, unique identifier, which is a IP address. So with the help of IP address only, we can communicate with one system can communicate with another system. But here we are using google.com instead of the IP address, right? So this DNS will translate readable domain into IP address. Okay, so that is the purpose of domain name system. So it will convert the URL. So we are calling it as a URL, or we can call it as a domain. Okay, this is a domain. So whatever the human readable domain is there, that will be converted into IP address in order to communicate with the server. So this process is called a DNS, which is a domain name system. So this will be acting like phone book of internet. So actually we'll be having some phone book where we can store the contacts and their numbers. If you want to call to one person, we'll go with the telephone directory and we'll be finding the number, or we'll finding the name and corresponding the phone number. So similarly, this particular thing will be acting as a phone book of internet. That means first, whenever we send a request to the Google server, immediately that will send a query. We call it as a DNS query to one more system called DNS server. So immediately the DNS server will check this domain and it will identify the IP address and it will give response to this particular system, right? So IP address. Okay, so for example, some 75.10.25.4, this is some IP address. So we have seen how the IP address looks like, right? So this is a IP address of version 4. So immediately it will go to the Google server and it will check it out. Okay, so first it will not go to the Google server. See, I'll give you the complete steps. Okay, I'll give you the complete steps. So this is a system user. Whenever it sends a request, so which is nothing but, let us take an example, google.com. First it will check with the DNS server. So whenever the user types to google.com in the browser, it will check with the Google DNS server and it will give a response. Okay, it will give a response with an IP address. With a IP address. Okay, then with that IP address, it will send the actual request to the Google server. It will give the actual request will be sent to the Google server. Okay, and it will get the response. This is how it will be working, right? So whenever we type the domain, immediately that will be converted into IP address, and then only the client or our user will be communicating to that particular server. Okay, this is called a domain name system. So hope you understood. So whatever the domain we are giving, that will be converted to IP address. So conversion of domains to IP address is the working of DNS. So hope you understood, and I'll stop here. This is completely introduction about the DNS, and in further session we'll go in deep how it will be finding the IP address and everything, right? DNS namespace. So here the name itself indicates where the domains will be saved, right? So actually this particular thing is in hierarchical fashion, hierarchical structure. Okay, so you know that hierarchical structure, right? So the top level is a, the first level is a root domain, So this is the highest level. Okay, topmost is the root level, and usually represented with a dot. Okay, so I'll write here. So dot is a root domain, and the next one is a top level domains. Usually these top level domains are again classified into two categories. One is generic TLDs. Okay, this is usually called it as a TLD, top level domain, and another one is country code TLDs. Okay, so generic means, see, .com, .org, .net, and so on. All these are the generic domains. Coming to the country code domains, those are .in, specifying the India, .us, .uk, etc., etc. So these are the top level domains, just below the root domain. So here you can say, so .com, .org, .in. This is next level, right? And the next one is second level domain. The next order. Okay, the next order. So these are the names registered under top level domains. So you need to select the top level domain, and after selecting the top level domain, we need to register the names for the top level domains. So example, you say google.com, okay, bing.com, yahoo.com. So all these are the names registered under top level domains. Okay, so you can simply write Google, similarly Yahoo, etc., etc., different. Okay, and the next one is a subdomains. Okay, so these are the domains registered under second level. Domains registered under second level domains. These are SLDs. You can simply use these words, SLDs. Okay, so example, so if you use a google.com, there are a lot of applications, right? So you can use mail.google.com. Similarly, maps.google.com. Similarly, images.google.com, right? All are the same thing, right? So different subdomains. So under google.com, mail, maps, images, all these are different subdomains. Okay, so here you can see maps.google.com, Google, mail.google, similarly images.google, photos, etc., all these comes under the subdomains. All this comes under the subdomains. Okay, so this is the hierarchy it will be following. So this will be the root, this is the top level domains, and these are the sub level domains, second level domains, and these are the subdomains. Okay, so just remember this structure. Okay, hierarchical structure. Now we'll see how the IP address converts to the, how the website URL converts to the IP address. So let us see step by step how it will be happen, right? So very simple and important thing. So the first step, user enters in the browser. So if you want to access the internet, we know compulsory there should be one browser. It can be Chrome or Edge or Safari or any kind of web browser, right? So first the user enters this particular website. Now what happens? Browser will check. This is important. Browser will check IP address for given website in local cache. Okay, so browser will be maintaining some cache, okay, cache memory, right? So if the browser local cache is having the IP address for Google, automatically the browser will be connected to the Google. Okay, so if found connects to Google. If not, then operating system will check in OS cache. So operating system will also be maintaining some cache. So the next step is OS will check in the OS cache. So here also, if found connects to Google, connects to the Google. If not, then what happens? So recursive DNS resolver will be initiated and check the ISP. ISP means Internet Service Provider, okay, or public domain service. Okay, public domain name service. So if the OS is also not having this website IP address, it goes to the, so this particular recursive DNS resolver will be initiated. So recursive means until it gets the IP address, it will be keep on calling. Will be initiated and checks the ISP cache. That means Internet Service Provider, or it will check with the public DNS service. So if found connects to Google. If not, what happened? If not, then it will check the root domain. It will check the root domain. Okay, so it will go to the root domain. What is the root? This one is the root. Okay, the top level, topmost level, right? For top level domains, and then it will check top level domain server for authoritative DNS server. So it will check for the top level domain, right? For example, this is a .com. So first it will check with the root and it will move on with the .com server. So whatever the names registered for this particular .com will be available in this .com server. So it will find with a Google DNS server. So Google will also be maintaining different servers. So that is called as an authoritative DNS server. Okay, this Google is a authoritative DNS server, and here it will find the IP address of google.com. It will find the IP address of google.com. Okay, this authoritative DNS server will send IP address of Google to where? To browser. It will send the data to the IP address to the browser, right? So once the browser get the address of Google, automatically the browser will connect to the google.com. So this is actually happens in the DNS namespace. So how the google.com will be converted to the IP address. So identifying the IP address. Okay. So I'll write, hope you understood this one. I'll write the same procedure in a short way so that you can get a more clarity about this one. See, first google.com, it will check in local cache. If not found, it will check with OS cache, and if it is not found, it goes with the root or internet service provider, and then it moves to the top level domain server, and from here it goes with the authoritative DNS server, and from here it will be having, it will collect the records which is IP address. Okay, so in the browser we are going to type this one. In the browser we are going to type this one, and this will be directly went to the browser. So IP address will be sent to the browser. Now the browser will be connecting to the Google server, right? So once it gets the IP address, for example, let us take some 75.102.10.4. This is the IP address of Google. For example, let us imagine whenever the IP address get to the browser, then it will send a request. It requests to not google.com. It will go with the 75.102.10.4, right? So then the request will be sent. Okay, so hope you understood this DNS namespace. So how the URLs will be converted into IP addresses, and that is the first step happens when you open any website, and everything, this complete process will be done in a fraction of seconds. So what we are doing, so we are opening the browser, and if you type google.com, immediately within a fraction of seconds we are getting the Google page. That is because of the same process happens in a very fraction of seconds, very fast. So here the complete domains, we have seen a lot of domains, right? So top level domain, second level domain, and subdomains. So whatever it may be, the complete information about the domains will be maintained in the DNS record, which is called as a resource record. So it stores the complete information about domains, okay, complete information. These are called as a records, right? So here, what are the fields which are available in this record? So fields, the first one, name, it gives a domain name, actual domain name. Type of record. So here for every domain there will be different types of information like IP address, similarly alias, that means a duplicate names, and the naming servers, okay, and the pointer for reverse mapping of IP to URL. So like that we will be maintaining a lot of records. So for every domain there will be different records. So which type of record it is? So this is a type of record. Class, what's a class of domain? So usually it is an internet class, so it will be represented with IN. IN stands for internet, okay. And next, time to live. This is a timer, okay, until when the record has to be in a cache. So what we have said, so whenever we type some URL in the browser, so it will search in the DNS server, right? It will go to the DNS server. Before going to the DNS server, first it will check in the local cache. So if the website IP address is available in the local cache, directly it will be connecting to the local cache, I mean that particular IP address. So how much time it should be available in cache. Okay, and the next one is a value. So this is a actual information of a domain, right? So these are all the different fields of DNS resource record. Okay, so for every domain there will be different records. So now we'll concentrate on what are the different types of records, because everything is common. So domain name is common, internet is common, time to live, the timer is common, and the value, the actual information is common, but there is a difference on type of a record. So we have said that there are different types of records, so that specifies this field. So we'll focus on that particular thing, the types of records. So what kind of information available on domains? So types of records. See, if the type of record is a record, so the name is a record, that means it is an address in IP version 4. So if the type of record is a record, it is an address in IP version 4. For example, if it is a, so 4 A's record, this means it is an address in IP version 6, so version 6 address. Okay, and if it is MX record, so it gives the information about mail server or mail exchange. Okay, mail server or mail exchange of that particular domain. So all these records will be belongs to one domain. So every domain will be having a different records. Okay, next, CNAME record. CNAME record. So CNAME record means alias name. So another name. Okay, and also we can call it as a canonical name. Right? Next, PTR record means reverse lookup. What is a reverse lookup? Means IP to domain. So actually DNS works with a conversion of domain to IP address, but here the PTR means reverse lookup, which is a IP to domain. Okay, so these are all different kinds of records. Okay, so very few records, and there are more number of records available. So some important records. So IP address is most important, and then the mail exchange records and the canonical records are most important. Okay, so these are types of records which are stored in DNS server. So who will maintain all these type of resource records? So these are not resource records, these are the types of records. So resource record means for every domain it will be having a different fields like name of the domain, type, similarly time to live, etc, what we have seen. And who will maintain all these things means the DNS server will maintain the resource records. So I'll write here, DNS server maintains all the resource records, and every domain will be having multiple records. Record is different and resource record is different. Okay, so hope you understood about this DNS resource record. So I'll stop here, and if you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.